in a couple of minutes. And you make sure the things that we share that can ask you. They will be here, make sure that would be all together. Don't go. Yeah, everything is
Bok oldu benim ya.
Yeah.
Bok olmadı. Açıyorum. Bak, öyle bir yamak atın.
It's Spanish, when you or manufacturer,
Okay. So there will be lots of mics.
Is okay. You can see that we put the insert. This is also.
Yeah, so this will for the local mics. So. Just working out. You can put it in your pocket, so. It's always sitting there if you need to change.
Yes, right.
Okay, welcome to day 2. This morning we'll start off with this slide of looking off. Telling us about resolving singularities and general relativity. Hopefully it's safe and very much. Orientation rate with it's like in sound for free. So, and what I'm talking about is actually not historical, but motivational, historical. You know that most of the discoveries in science made with wrong motivation, because a good friend of mine, Igor Platan, was saying once that if you take first phase of Dirac about Dirac equations, there is no single wrong formula and no single correct sentence, because as you know, for Dirac, it was completely wrong motivation to discover his equation, as you know very well, or maybe you don't know. For Einstein was the same story, this Mach principle, whatsoever, which everybody forgot about, but the result came good finally. You are looking for one thing, you can find the others. Now, about quantum gravity. I recall Brian David was saying, 40 years passed since he wrote this equation of canonical quantum gravity. When people speak about topology changing, etc., but everything it was reduced to the hand wave. No result. Then I recall that once I was in some panel, in survey, and I asked, guys, tell me, why do we need quantum gravity at all? The answer was unbelievable. People blow up and told me, you want to claim that we don't need quantum gravity? I thought, no, I just ask you, why do we need quantum gravity? And of course, two natural equations which would be resolving singularity. I know, some guy told, we want to explain nice CND maps. I thought, come on, this already was resolved, so your help is not required. Moreover, when, for instance, we obtained long ago, 1980, the spectral length at 0.96. The 0.96 was something extremely non-trivial, because what was 0.04 is 2 divided by logarithm of the ratio of galactic scale to CMB, millimeter scale. And it's the only formula in the nature which was experimentally verified and which contains simultaneously Planck constant and gravitational constant. But for that, we don't need so-called non-perturbative quantum gravity. But what for you would need non-perturbative quantum gravity? For instance, you could say me to resolve the problem of singularity, which John Wheeler was telling one of the crises in physics, or the question about final fate of the evaporating black hole, because people say, what will happen with black hole of Planckian scale? First of all, you cannot define the black hole of Planckian scale because fluctuation of the metric are of the order of metric on the horizon. And therefore, there is a different approach, which actually we were trying to exploit. Maybe actually when we go to very high curvatures, nobody told us the general relativity should be correct. It's finally not biased. And maybe things becomes more classical there. Quantum effects become less relevant. And therefore, the question was to find some modification of Einstein equations at very high curvatures, which would allow us smoothly to go through the singularity. And I remember that I was working on this thing with Marco at the beginning since 1982, till 85, from 85 to 87, I was spending time on interpretation of quantum mechanics. But we did some partial success, but in fact, actually, we never resolved the whole thing. Then 2016, we came back to this question in relation with the other thing, this so-called mimetic dark matter. And then, okay, in some time, we found that the things can be done like this one. The question is how to verify it experimentally. What I will tell you what was the general idea. But first, let me remind you about singularity, because as you know, there are famous theorems by Penrose and Hawking about geodesic incompleteness of manifold under certain conditions. First of all, you have to postulate the existence of the horizon. And second thing, you can prove that space-time will be geometrically incomplete where energy dominance conditions are satisfied. Namely, energy density should be positive, energy density plus pressure should be larger than zero, and energy density plus pressure should be larger than zero. It's a good strong energy dominance condition. But we know right away that the third condition, this one, is already violated, and it's experimentally verified because it's nothing more than just dark energy, which violates this strong energy dominance condition, the zeta space. This was in particular the reason why Stravinsky at the beginning also was more interested in the solving singularity problem, was considering passing through the singularity using this de Sitter stage or de Sitter-like stage, because on de Sitter-like stage, gravity becomes anti-gravity. Therefore, it can slow down your expansion and can lead to the further expansion. And the most amazing thing that one of the papers which he wrote was about M squared phi squared theory, where you can imitate cosmological concept. The paper was written in 1978, where he obtained all inflationary solutions in this theory, but in contracting universe. You see all the formulas which we see now for the expanding of square phi squared inflationary solution are in the paper by Stravinsky, who has considered field larger than the Planckian scale. Therefore, the paper was rejected from Jet Letters and was published in Astronomical Journal. But he also calculated that, of course, for the measure, this kind of solution which pass through the singularity, measure for these solutions is equal practically zero, because during contraction there is other mode, which instead of leading you to the equation of state pressure is equal minus energy density, which would allow us to avoid singularity, gives us equation because of kinetic pressure is equal plus energy density, which gives you the strongest possible singularity, like in an isotropic universe, okay? Because in an isotropic universe, the term which leads to a singularity grows like 1 divided by scale factor in power 6. Then, at the same time, because I started to work with Markov in 82, Markov just was taking Friedman equation and was suggesting this kind of modification of Friedman equation. So 3 double constant squared is equal energy density 1 minus energy density divided by limiting maximal possible energy density. You understand that actually here the sign cannot be changed. So energy cannot exceed this limiting energy density. But equation was coming from nowhere. Second, Rosen wrote more or less singular equation at the same time. Then the equation also was what will happen with the highest derivative, because okay, everything will go smoothly, but for instance, if second derivative would be singular, it would not resolve anything. And also it was not covariant. Then we wrote this Markov couple of papers where we considered also these things which as certainly at the beginning was completely irrelevant because it was not justified by anything when we considered gravitational constant as a function of energy density, and then required that at limiting energy density, so at large energy density, the gravitational constant is vanished. So called realization, some kind of realization of asymptotic freedom, the only thing which we were able to show that in this case automatically generated cosmological constant, but nothing was coming from any Lagrangian. No, this last thing was coming from the effective Lagrangian, but the rest was not from the Lagrangian, etc. Then, when in 92, 91, I came to United States to write with Robert Brandenberg physics reports, then we came back to, I came back to the idea, but at this time, we came back to the idea, we decided to limit curvature by the Planckian value using some kind of function of the curvature invariant. But you understand the curvature invariant always involves higher for the curvature invariant at least fourth derivative of the metric. So which makes a lot of headache, as you know. And here, after thinking, also we found, of course, that curvature square term you could limit, but the first derivative was blowing up, so it was singularity. But then we came to some idea that why we would not just force solution somehow to go to the theta automatically. And with this purpose, we took this invariant. No, here. Okay, we took this invariant, which vanishes just in two cases. In isotropic case, for the de Sitter universe and for Minkowski space. And then we selected here appropriate function of this curvature invariant in such a way to force universe finally during collapse to go to de Sitter. And we succeeded in isotropic case. Irrespective of the matter which you are adding, if matter, okay, has equation of state, pressure is smaller than energy plus energy density. But of course, if you would add a little bit anisotropy, like you have in black holes, then it was catastrophic. You could not invent any invariant which would allow you to pass through the singularity. And then by accident, then after that, actually, by the way, when we first wrote this paper, Brandenberg told me, let's send it to his ref letters. I told him, come on, why should we send it to his ref letters? I never published that. Then we sent it to his ref letters, and it was published immediately, without any referee comment. What is the reason for that? Very simple, nobody cared. Because after that, we discovered that for 20 years, there was no single paper about singularity. In this case, this is a good way to publish the paper. If somebody cares, they put on you infinite number of troubles. You see, then there was Nevertheless, string equation of Heisenberg universe and two-dimensional black hole. Four-dimensional. In two-dimensional black holes, everything was very easy. We wrote it on paper with Mark Troden, because in this case there was only longitudinal mode and everything was going on, but about Heisenberg and four-dimensional black holes, there was no idea. Then, if you remember, those of you who are older, that in 90s there was a lot of activity about singularities in string theory. These guys came in the field, did practically nothing there, and then left successfully. There was loop quantum gravity, as you know, but loop quantum gravity is a strange science from my point of view, because what they are doing, they are quantizing Einstein equations, the Planck and curvatures, when you know for sure that Einstein equations are not applicable. Why? Because quantum corrections, okay, generate new terms which are quadratic and high order in curvatures. Therefore, what they are doing, I have no idea. It's precisely like in BKL also, when the people take Einstein equation and then go through singularity in this chaotic regime. So also strange activity, yes.
I don't want to defend the quantum my friends, but if my understanding is better, it's just like a quantizing the classical system. The classical harmonic oscillator is quantizing, you have to start from classical level.
Very good, but there is also, as I told you, to harmonic oscillator quantum corrections which live nicely from your harmonic oscillator, as I told, because there are quantum fields, you don't need to quantize them in gravity, because quantizing other fields, yeah, you just get modification of your action because of the divergences. The appears as square terms at least with logarithmic divergences in front. And there are quantum effects, and this kind of quantum effects, they lead you to modification of the Einstein equation of the order of unity already at the energy scale below Planckian scale. You see? Therefore, to be on safe side, what I will be doing, I will be working in terms of so-called limiting curvature hypothesis, but I will be assuming that this limiting curvature is below the Planckian curvature. And I will be showing you, I will show you that you can regulate the level of quantum fluctuation to have classical solution, which will not be too much disturbed by quantum fluctuations. This is self-consistent scheme, because I'm not pretending that I can go to the Planckian scale. But if you will never be able to reach Planckian scale, then why we have to speak about Planckian scales at all? And in fact, actually, we come back to this problem after we wrote with Ali Shamsidin some paper about so-called mimetic dark energy, dark matter. It was, again, wrong motivation, because we were trying to kill one of the degrees of freedom in so-called massive gravity. We were not able to do it. But nevertheless, we invented something as modification of Einstein equation, which we're giving you as a solution of Einstein equation even in empty space, like solution in the universe filled by the cold dark matter. Okay? And of course, I could give you even some justification for this thing from non-commutative geometry, because we wrote paper with Alan Kohn and Ali Shamsidin. But let me skip this part, because if I will start with topology, and then from topology we'll get dark matter and dark energy, you perhaps would think, at least not explicitly, that I have to go to psychiatrists. Fortunately, there is a lot of people who need this psychiatric help before me, and I am not in a hurry. But the idea is very simple. What you do, you take Einstein equation and modify Einstein action in a very simple way. You introduce with the help of Lagrange multiplier some kind of scalar which is restricted by this condition, the gradient of this scalar square, what I'm going minus 1 is equal to 0. In this case, this scalar is not scalar field because satisfy first of the differential equation corresponds to half of the degree of freedom and only together with longitudinal degree of freedom of the gravitational field, it makes you 1 degree of freedom, which corresponds to the depth. At the beginning, everything was written in more complicated form based on some kind of symmetries, but then Golovnev have rewritten action in this kind of form. And then, by the way, also here we made experiment when we were publishing this paper with publication. I thought, Ali, let's not give single reference in our paper, and let's see what referee will say. Have you seen papers without references at all? But because neither me or Ali knows how to remove the bibliography in letter 5, we were stuck with it, and therefore we put one reference to Landau Lifshitz with a reference to synchronous coordinate system. You can check it. There was no complaint by the referee because, as you know, perhaps it's a paper with the minimal number of references which was published during the last 30 years at least. Now, as you know, the number of references exceeds 100 practically in every paper because you have to list all your friends. So now, there you understand that what can you do? This scalar field happens to be very good because, first of all, it doesn't give you high derivative. If you will take even box of this field, it's restricted to satisfy this constraint. It, in fact, actually doesn't give you the equation of the higher order. Moreover, if you go to synchronous coordinate system, when it looks like this one, this box of this field, which satisfies this restriction, is nothing more than just trace of the extrinsic curvature of T per surface T equal constant. In the other coordinate system is much more complicated thing, but this is the covariant way to build something invariant out of first derivative of the metric. Normally, you need second derivative. This is the reason why you involve high derivative terms. Okay, you have headache, but here you can work with the first derivative in the special coordinate system, which is called synchronous coordinate system. But there, if you go to the other coordinate system, of course, things becomes much more complicated. But nevertheless, in synchronous coordinate system, as I know, you have very simple expressions. Logarithm or derivative, time derivative of the logarithm of the determinant of the special component of the metric in this coordinate system. And then the question is the following: can you find some function which depends on this determinant in such a way that the resulting equation, if you add even the method, will be avoiding singularity? And in fact, actually, it happens to be very easy.
Laura, I have a short question.
Yes.
This formula we should have, because if you get linear expression for phi, isn't it just not trivial way to write dilaton?
No, dilaton is normally dynamical. Dilaton satisfies second order differential equation. It's first order differential equation. You can think about this phi as about just time coordinate and synchronous coordinate system.
Restricted to linear dilaton.
No, correct, but dilaton satisfies second order equation, as you know, it's exponent phi multiplied by r. And then when you go to the Einstein frame, it's just actually normal scalar field. For dilaton, it's theory. And the question was actually how to stabilize this dilaton. Because but here it is much more simple situation. Okay, so and then okay, so I'm always confusing things. The question is about this function f. What is the first idea which came in our mind? Why we would not restrict this kind of invariant, which is nothing more than just derivative of the logarithm of the determinant of the matrix using Born infinite type action. You see? So this thing what actually Born infinite used to restrict the value of this invariant b squared minus b squared. There are other terms, but the other terms are written just to simplify equations and to get exact solutions. The leading term or the major term here was like this one. You see? Then actually we did this thing. And then we found that the things are solved very easily. If you take Einstein equation, then irrespectively it's anisotropic or isotropic universe, you could rewrite Einstein equation, 0, Einstein equation, as this kind of Friedman-like equation, but instead of couple constant is determinant of the special component of the metric, and in the right hand side you put everything. I mean, this energy momentum tensor for the normal matter, this thing is so-called mimetic matter, which is extra degree of freedom, which appears there, as I told you, without extra particles, which could explain actually this dark matter. And this term comes from anisotropy. You see, and it behaves like 1 over gamma instead of 1 over square root of gamma. So it actually corresponds to the effective equation of state pressure is equal to plus energy density. But equation came precisely in the form which is similar to how Markov was writing it for isotropic case. You see, but here it's written for anisotropic case. And EM is a free parameter of the series, therefore you can take it below Planckian scale, but not too much below, because we still want to get explanation of cosmological data. But a couple of magnitudes below you can go, than the Planckian scale. Then, after that, take Friedman universe, I will speed up, don't worry, yeah. And then Friedman universe for an arbitrary matter, with equation of state P is equal W epsilon, you write equation for the scale factor, and it has exact solution, non-singular solution. Moreover, what happens? It happens that you have contracted Friedman universe, doesn't matter with which equation of state, and then there is a balance. Balance is precisely a limiting curvature which can be higher or below than the Planckian curvature. Moreover, this balance happens during very short time. If you would take, for instance, limiting curvature to be Planckian curvature, this balance happens during one Planckian time. Why? Because in this case, if you would rewrite equations as Einstein equations, taking everything else on the right hand side and interpreting it as an energy momentum tensor, then you would get strong violation of this energy dominance condition. You will get huge pressure, negative pressure, which would allow you to change contraction to the expansion. Yes.
Okay, so you said Planck time. So at Planck time, you are not going to trust this.
I'm not going to trust.
Yeah, suppose that you have much longer time and much smaller curvature.
Yes.
And then my question is, so then in this theory, there is some other scale which is not the Planck scale.
Yes.
And I'm wondering whether this solution is still self-consistent.
Yes. Because after that you can check the perturbations, okay, are small. Quantum fluctuations are small, really. Because you see, you have to check, of course, stability of the solution. And then in this case, it will be a stable solution. And moreover, it will be, as you will see in a minute, of the final answer to the question, because, okay, I have to speed up, but now let me go first to Kastner universe, yeah? And the Kastner universe, because the equation is more or less the same, you know, the Kastner universe is the solution, like this one, an empty space with this exponent. And the four-dimensional curvature square, not two dimension, not two index, not Ricci, not Ricci square. But Riemann square tensor is divergence like 1 divided by T4 multiplied by this exponent. Only one of the exponent when of this p is equal to 0, there is no singularity, but this case corresponds to the Minkowski space. You see, as you will see. But even in this case, what you will find, again, we are solving equations. Let me not concentrate too much on equations because you will not trace them anyway, and I have no time to stay more long on this page. But we are getting again non-singular solution, even exact solution. And you know what happens? You have Kastner contraction, then you have bounds without reaching any Planckian curvature, just getting to the limiting curvature, which is 3 parameters. And then during these bounds, Kastner change exponent, okay, like this one. For instance, if you have Kastner with exponent minus is special case, minus 1/3, 2/3, 2/3, then it turns to Kastner with exponent 1, 0, 0, which is nice and more than just Minkowski space up to topology. Now, let's take black hole now. What happens in black hole? You know that of course, most of the people, in spite of that, they say so, but they could not realize that now black hole is not black box. Inside horizon, you have evolving space. Moreover, in the region close to the horizon, if black hole is large enough, the metric is close to the Minkowski metric up to the curvature correction. Okay, it's like this one. At A minus AG inside horizon metric would be rewritten like this, similar to Kastner P equal 1, 0, 0. Then, when you start to approach singularity, which in the black hole happens at the given moment of time, okay, and then you consider the leading terms, the metric there becomes like this one. You see? Wait, this, okay. Like this one. And it's nothing more than just Kastner metric up to topology with exponent minus 1/3, 2/3, 2/3. Therefore, you could use this kind of approximation, then you will find in this case the following thing that inside black hole, when you went inside it, okay, instead of going to the singularity, you are jumping from Kastner exponent minus 1/3, 2/3, 2/3 to Kastner exponent 1, 0, 0. So instead of going to the singularity, you will find yourself on the opposite side inside the black hole near horizon region. But this black hole has a radius which is just initial gravitational radius in power 1/3. And then this picture is repeated many times. Then when you approach limiting curvature, we didn't know what to do because all this approximation will not work in there anymore. Then some people showed on the, of course we said that we resolved the problem way, but I was not very sure. Then we spent a lot of time to deal with these small black holes, but no success. Somebody on computer found that nevertheless, finally you go to singularity. So instead of diagram, conformal diagram, as we saw, is like this one, will become like this one. We got here after many cycles of contraction, expansion, contraction. So it's like black hole, which we got like Russian doll. Okay, within big doll, you have smaller doll, black hole, smaller, up to the Planckian scale. But then we didn't know what to do at Planckian scale. And then it was not quite clear how to proceed, but then after that I recall this idea about asymptotically free gravity at large curvatures. And then we switch to the other slides. We also got very good student, very rare phenomena, because at the beginning Harry was checking all his calculations. He was telling me first time in his life when he cannot find any mistake in the calculations. Once he came and I found minus instead of plus, but then he came in an amount of, unfortunately, this minus was irrelevant. You see, so, okay, Tobias Roots was doing these calculations, and we realized here this idea of, okay, so it's the same image gravity, synchronous coordinate system. I don't need to repeat this thing, but now what we did, we inserted in front of the curvature some function f, which is inversely proportional to the gravitational constant, and we assume that this gravitational constant vanishes at the limiting curvature. You see, and that is the change of the game in some sense, as it happened, because in this case, what we managed to get, wait a minute. What we managed to get, we took as example, again, it says example just. For the gravitational constant 1 over f, where f was 1 divided by this extrinsic curvature squared divided by limiting curvature. So you see when you start to approach this limiting curvature, gravitational constant goes to 0, yeah. And then for Friedman universe, we got this kind of modification of the equation. And of course, also here we got non-singular solution, but this non-singular solution looks a little bit different. Instead of having balance, when you approach singularity, you go smoothly to the Sitter contracting solution. So you are replacing singularity by the Sitter fix. Okay. For Kastner universe, it happens that the same story goes. Kastner anisotropic universe, when you approach this limiting curvature, becomes isotropic, and moreover, it produces you also the Sitter inside. You see, so it's a change of the game in some sense. It's not just balance like this one. It's the Sitter. We by the way had this idea to insert instead of singularity inside the Sitter, it's now a marker inside the hole, the Sitter, which was allowing us to go to the other universe. We wrote even papers on the black hole to the other universe, but it was long ago actually. It was 1988, yeah. So 1980, not 18, yeah. So good. So now, so in Kastner, the same story. But now what happens with black hole? Now, the question also about quantum fluctuation, by the way, is actually quite interesting remark. Because as you understand, if you will take quantum metric fluctuations normally, like gravitational wave, the amplitude is proportional to the gravitational constant. But because gravitational constant is vanishing, then in each given scale, the amplitude of quantum fluctuation decreases. So instead of having the picture of this very violent space with a lot of quantum fluctuation, in approaching limiting curvature, you are getting smooth picture where quantum fluctuations are suppressed, quantum gravitational fluctuations are suppressed, and then you don't need to make headache considering quantum fluctuations of the metric, for instance, with the scale smaller than the Planck scale, where they are larger than the background metric. But now, the last sentence, yeah, then we go to the black hole, and our student found some kind of Lagrangian, which looks ugly, but it says example, just to get exact solution. You see, because he also is lover of exact solutions. I know many people, some people in this room, not approximations. And okay, we have considered black hole you know, okay, this kind of thing, and you know also very well that black hole metric could be written down for black hole and for de Sitter in a similar form. Moreover, the best way to describe this black hole and this de Sitter is to go to so-called Lemaitre coordinate, where you mix radial and time coordinate. It's by the way presentation very good for the black hole in Landau Lifshitz. And then we found that Lemaitre found this coordinate in 38, and then you can solve them there. And then what we did actually, we have considered for black hole solution is like this one, for de Sitter is like this. So for de Sitter looks familiar, for black hole perhaps it's not so familiar. But then what we did, we have considered this kind of ugly Lagrangian with this function f. But the most important part in this Lagrangian is this kind of dependence, where kappa tilde is extrinsic curvature normalized on the limiting curvature. The rest I need only with one purpose to find after that exact solution of the equation. So then you understand that this horrible equation happens that they have exact solution which can be written down in this parameterized form, where A and B were this coefficient in the metric which describe both de Sitter and black hole. And then we found that as a large curvatures we have black hole solution, but when as a small curvature, but when we start to approach limiting curvature, this solution goes smoothly to the Sitter patch. And moreover, we found that because of limiting curvatures, there cannot exist black hole horizons with if mass exceeds some kind of limit in mass, which is determined by this free parameter of the theory, which is called limiting curvature. And you are getting this kind of conformal diagram, which describes you non-singular space-time. Moreover, you could ask me what happens with black hole when black hole during evaporation starts to approach this limiting curvature. If you check how metric looks like, in this case, then you will see that metric looks like for the extremal black hole. And extremal black hole has temperature going to zero, as you know very well. And in fact, if you calculate now the last slide, the temperature as a function of mass, then of course we are getting here Hawking curves, where temperature is inversely proportional to the mass with small corrections. We should be there, but when mass becomes 30% larger than the minimal possible mass, temperature stops to grow, and then temperature drops to zero when mass is equal to the critical. Therefore, you could think about this minimal black hole as about pieces of de Sitter space which are surrounded by black hole horizon and which are flying around us. Mass of these pieces is the free parameter of the theory, which is determined by the limiting curvature. So maybe one more candidate for that matter if you want, okay, or whatsoever, that I don't have on this speaking. But this is consistent theory where we don't need to make any assumption about intermediate layers, okay, which we were doing with Frolov and Markov, okay, with unusual properties here. Solution, exact solution of the classical equation with controllable quantum fluctuations, because you have seen that quantum fluctuations, this asymptotically free gravity, are vanishing when you approach this limiting curve. So thank you very much. So I think I did it nearly in time, plus minus 5 minutes. Okay, thank you.
Thanks for the very interesting talk. So my question is related to observations. Of course, theoretical motivation is basically there are many possibilities. One can have primordial black holes that recently were shown during disturbance in model during preheating. Some modes due to instability can collapse and form pH of 10 power of 12 grams. So, according to this limiting the range of possibilities, so there can be remnants, there will be remnants all over the sky.
No,
But there are stringent constraints from the range. You didn't find any gravitational waves or any kind of.
No, here black holes are small. Okay, what people do right now with primordial black hole, I do not know why this happening to this at all. This is a different reason because nobody knows the origin of these binary black holes, which LIGO, let me say accurately to be politically correct, claims that they have seen. I don't know what they have seen, but no one in astrophysics believes that this can be formed actually in the natural conditions. The people do not have actually this kind of masses. And therefore, what they started to do, they started to squeeze the spectra to form this black hole in the early universe. But you understand, you have to pay very, very high price. And from my point of view, it would be just more easy to draw you the curve which you need to explain so-called quote-unquote observation. Yeah. And then when you will draw me this curve, I can invent you 20 series on bed, and for a bottle of wine, 30 series within half an hour. You see, which will give you this spectrum. It's not big deal. But this has nothing to do with primary black hole because I do not want to violate normal inflationary expansion as the energies, okay, the
And
energy.
example, the standard inflation during preheating,
You can form nothing there. You can form nothing. Sorry. You see, during preheat, standard inflation, first of all, horizon scale is too small. You have to delay the things very much. Second, to generate, okay, this kind of amplitude, which you need to form black hole.
they are not big black holes that tiny. You can form tiny black holes.
Tiny, maybe you can form, but who cares about tiny if they are evaporating according to Hawking evaporation at least up to this space. You see, because people before, in the early time, when Hawking wrote his paper, I could still understand this activity when Bernard Carr wrote his paper also, because there were events, gamma ray bursts, which people, when they have seen them, started to interpret immediately as exploding black holes. Finally, they found that they had nothing to do with it. Primordial black holes. Then Bernard Carr wrote some kind of paper, 74. I remember when he was estimating the probability of the forming of such black holes. But you understand that, first of all, there was no right spectra. And second thing, everybody at this time believes that the spectra should be decaying in the range of large frequency. After that, after actually this stage of inflation came, okay, when became clear that the spectrum is red tilted, this kind of scenario became very unfavorable. You know, I wrote my diploma work, but it was actually student work, putting limits on blue tilted spectra, not to form too many primordial black holes. But right now, there is, of course, I know there is a whole industry, but this whole industry can be imitated very easily. I don't want to insult anybody, but okay, industry is industry.
So I have a short question. Your these Russian dog constructions and stuff like this, are they stable?
They are stable, but the problem is that the last stage of this Russian dog is not controllable. At least I don't know how to do it analytically. Some people who are doing numerical simulations claim that finally you will get singularity. But otherwise they are stable. You know the picture. Schwarzschild black hole is the only black hole which is stable internally. If you take Raster Nostra or Kerr black hole, nobody knows what is inside. Okay, because all the horizons there are unstable. People believe that structural singularity is a real singularity in any black hole, yeah? Time-like singularity, but not space-like singularity. No, space-like singularity should be there, but not time-like singularity, like for instance, Reisner-Morse. But as you know, people draw conformal diagram for Reisner-Morse, but they are completely unstable.
Thank you. Yes, we're running a little over time, so maybe one more question for short answer. Can some of these models be embedded on theories of quantum gravity?
Short question, short answer. I do not know any theory of quantum gravity because, of course, some people claim that okay, they can get something in loop quantum gravity, but sorry, I have never seen that you can get it. That's the second thing. Tell me a couple series of quantum gravity. Quantum gravity exists forever, yeah. There is all the special constraints and nothing more. Then there is the equation for mini superspace mode. But okay, there is not too much trust to these equations also, because as you know, quantum corrections are spoiling all of them, and second thing, these equations don't solve anything. And you know, Bourgeois, who are your claims that also they can get some values like, you know, I do not work with people who go, what I say, I cannot get back Minkowski space. I am sorry. Okay. There is one more lady issue. Yeah.
I have just a quick second question on Russian dome construction of the I think if I understood properly, I read it, here actually there is no potential, right, for the starter. If you add a potential, would that help?
No. When we edit potential, it creates a lot of new options. Okay, research report, we wrote in the whole paper. Where we could get everything. KS, what did you get there? I already forgot. Yeah, by the way, also, it got also bounce, you know, the solution without its square. But then I discovered that the measure of this solution was equal to 0. Here also, alien potential is not very natural thing. Yeah, but this thing actually is potential also was also investigated. By the way, actually there is a lot of activity in the literature because I think it's collected how many references actually would follow. 300, I think, both us, 260. 260, and we make it 400.
I was wondering that VO5 would somehow help.
VO5 is helping, but not too much. Actually, a more natural thing is to use, because I told you what was, is the invariant which made out of the first derivative of the metric. You see, normally in general relativity, you cannot make this kind of things because first derivative at each point can be banished in local inertial phase.
I think the potential you will translation environment. This is a big loss.
No, what you mean? When you add V of phi, yeah, you know, translation environment. Yeah.
It's a big.
Okay.
Okay, so I think we got to move on now. Thank you very much. So, guys, there is some announcement here on the way. We will have dinner at 6 p.m. tomorrow.
Okay.
There is a list here. You can find your family name. If you
Okay.
sort
So
the
we are-
family copy, you can
Yeah,
please put
this one.
some plus sign or something.
Okay.
If you don't
So
find
you
your family name, but
Yeah,
sure
this
that
one
you
also.
should come to the
Okay.
meeting,
Okay.
just write your family name. Okay? We just need to count some of
That is okay. That's
so you can pass the list one to
This
each other and.
You can put it in your box. This one.
Okay, so our next speaker,
Yes. I come from the Institute of Applied Physics, Beijing.
Okay.
Thank you.
And I see she's exploring the Himalayas.
Yes, yes. So today I'm very happy to have a chance here to talk about our experiment named ALI CMB polarization telescope. And our goal is to detect the premodulated waves in the Himalayas. So you can see this is a recent photo from our experiment on a small mountaintop in the Ali region. And our goal is to, open a new window for the primordial gravitational wave detection in the northern hemisphere. And here is the outline of my talk. So first, I will introduce the motivation, the background from the primordial gravitational wave detection, and then I will introduce our station in Ali, and then I will present the current status of our experiment under the telescope. So first, the main scientific goal of RCPT is to detect primordial gravitational waves. We know that the primordial gravitational wave is an important prediction of the inflation model. It is essentially the tensor perturbation, the quantum fluctuations of space and time during inflation. And with the primordial gravitational wave, it will lead to the CMB B mode on the last scattering of CMB photons and electrons at the last scattering surface. So observing the CMB B modes provides an efficient way for the detection of primordial gravitational wave. Once we detect primordial gravitational waves, we can test the inflation models, and it's a great predictions for the inflation paradigm. And CMB, I think everyone here is very familiar with CMB. It's it has been a precise probe for cosmological study for years since it was first discovered by Pontius and Wilson in 1964. And the measurement of CMB temperature and the polarization spectrum provides rich cosmological information of the early time, and it is very helpful for shedding light on lots of fundamental scientific questions. And I think everyone has a lot of background information here, so I will not go to detail. And I want to talk about the measurement of the CMB power spectrum. As I listed here, till now, in the past few decades, a lot of data sets has been accumulated in the measurement of temperature power spectrum, E power spectrum, with also the D modes, with 3 generations of the satellites from COBE to WMAP and Planck, as well as several ground telescopes. So now the temperature and the E spectrum has been measured precisely, which plays crucial important roles for the standard model of modern cosmology. But for the B modes, you can see that the best observation come from the ground observation. Till now, you can see that on the degree scale, the BASAP and Keck telescope provides the best measurement here, and the gravitational length B modes was first discovered by the SPT large dishes in the South Pole. So in the next few decades, I think a lot of efforts will be attracted on the ground observations before the next satellite come to the space, I think. And our RCPT is one of them, want to continue to improve the sensitivities for the B modes detection and try to find gravitational waves. As for the ground observations for the CMB, it is heavily rely on the atmospheric window, because we know that for the ground observation, atmosphere around the Earth will interfere with the CMB observations. So here, I show you the transmittance in microwave bands. You see the frequency bands I listed here will change with the water vapor lines. So with a different water vapor, you will see the transmittance will change a lot. So we usually the CMB observation will go to the high places, the mountain top for the thin atmosphere, and the place should be very dry because the water vapor will influence the transmittance. So now Ali region is one of the good site. I will talk more about the details in the next pages. And here I want to show you that around the Earth, there are about 5 windows that allow us to observe CMB photons. And we will do the observations with 1 or 2 more frequency bands within the windows. And RCPT will first start from these windows around 90 gigahertz and also 150 gigahertz here.
But that's the correspond to high frequency principle.
Yes, I think now in Chile and Atacama, high frequencies around 200 also preferred now.
But they also actually cannot go beyond 300.
Yes, transmittance is not very good, but it could do.
But it was killer by itself.
Yes, BICEP also have higher frequencies, I think around 200.
No, but because they haven't seen dust, you know, where there was dust. And this is the reason why they made fake announcements. BICEP.
BICEP.
2014, there was disaster when BICEP.
Yes.
They made actually, they discovered gravitational waves.
Yes.
But it was dust, what they have seen.
Yes.
And it was actually in the range.
Yes, at that time, they do not have the frequency bands here. I think the major conclusion from the channels of 90 gigahertz observation. Later on, they have adding 150 channels. Also, they put channels around 30 and 40 gigahertz.
But okay, on the right hand side, you cannot go. On the
Yes, these bands we cannot observe. Yes, we can. It should be go to sky. Yes, these 5 bands we can observe in the ground. Other than these windows, we cannot get.
and,
Yes.
and silence in each direction.
Yes, Simons also lies within these windows.
But they have 3 frequencies. No?
6 frequencies.
They
Yes,
also have 6 frequencies.
they also have 6
And you have
frequencies.
6 frequencies.
Now we have 2 frequencies, and the next year we will have the lower channels, and in the short near future we will have higher frequencies channel. Now we have 3 channels. Yes.
And how much is it right now? Already 100 million, 200 million? I mean dollars, not euros.
I'm sorry, I cannot get you.
How much does it cost now?
Okay. I think at least 100 millions.
100
RMB, yes.
dollars,
Yes.
not euros.
Yes, okay. Okay, I will continue. So this map show you the water vapor distributions around the Earth. This is a map, and the colors will show you the distributions of water vapor. The bluer the place, the drier it is. You can see that on Earth there are about 4 sites allow us to detect CMB. So the first. You can see in the South Pole, BICEP, SPT are there. And also in the Atacama deserts in Chile, there are some experiments like ACT, Polar Bear, and Simons observatories are there. And also, but in the North Hemisphere, there are 2 good sites. One is Greenland, and another is Tibet in our country. And Ali region here, you see the blue is very dry, and it's a good site. And since 2016, we have deployed we have launched a project to develop a small aperture telescope and observed at 2 frequencies. 90 and 150 gigahertz and try to, probe the CMB for the northern sky from the ground for the first time. Yes. And here is a map. I want to show you that ALI site could be a good complementary to the telescopes in the South Hemisphere. You see, ALI locates in the middle latitude of the Northern Hemisphere. So with the rotation of the Earth, ALI can cover a large sky patch, which include, the whole northern patch and a small part from the southern patch. So the in ALI site, there is the sky overlap with those from Atacama. So you can see that for the ALI station and the Atacama station, these two could cross-check to each other with the sky coverage. And also in the South Pole, they can cover about 30% of the southern sky. So with ALI, it could be easy to realize the whole sky coverage from Earth. And second advantage is that if you look at detail from the Planck high frequency observation 353 gigahertz, you will see that they are very blue patch in the northern hemisphere. That means there is clean patch for with low foreground emissions. So this patch could be a new window for the primordial gravitational wave detections in ALI with deep survey. So our first target is try to look at deeply for the clean patch in the northern hemisphere and try to find the primordial gravitational wave there.
But which part of the sky you are going to cover? It's small part which corresponds to the multiple between 80 and 120, or you want to go also to very low multiples?
Yes, we have our scan strategy. I will mention it later. But the conclusion is that we will have deep survey on the small patch, 10% of sky. And once this small patch cannot touch, we will have a large sky patch survey. So we have two scan modes for different scientific goals.
And you select those parts which is the cleanest according to that of the Planck?
Yes. From the Planck's high frequency map, we search the clean patch and focus on the clean patch. We will do the deep survey. Yes, for the R. And for the non-R cosmology, we will, try to have a large sky patch.
No, for the whole sky, you will never be able to cover something in reliable way, but okay, this small patch, like by set cover, if you go a little bit above, I do not know, then there is not so much dust. There is more clean regions compared to
yes.
You see. So you concentrate on these regions.
Yes, 10% of sky, and we can put 1,000 hours in the observation season. Yes, 1 year. Yes, for our telescope, we have our scan strategy. Okay.
And you are correlated with Atacama?
No, I don't think so. Yes. No. It has not the sky overlap with Sammons for the clean patch, but other patches, maybe galactic planes, we have some, sky, yes, coverage with Atacama. Okay, now I will introduce the details of the site. So here you see this is a map for the Tibet. And this yellow dot show you the detailed locations for the ALI site. You can see that it locates in the West Ganges mountain here and next to the Himalaya. The Himalaya mountain is very tall, so it resists the wet air to come across from the Indian Ocean. So which makes ALI region is very high. It's very dry in the winter. And the ALI region is convenient for the logistic. You can see this is a Google Earth map, and you zoom into it. You can see that the ALI station located here. It's in the middle of the Pinsha airport of ALI region and a small town named Shiquanhe town. The distance between the two is about 1 hour's driving. And from the town to the station, it costs about 30 minutes. So it's very convenient to perform the experiments here. So you can see this is a mountaintop, before 2017. And in this time, there is an observatory in the optics observation here. Some optical telescopes are carried out here in the small mountain named A1 point. And in the short distance in B1 mountain, about 1 kilometers distance, we pick the mountaintop here to perform the primordial gravitation wave detection. And after 7 years construction, now the B1 mountaintop becomes here, and you see we have performed the mount to do the typical constant elevation observation for the CMB experiment there with a Dume load. Once we take place the Dume to the real telescope, we can observe the northern sky. And this is the recent status of our lab. You can see that we are almost ready for the observation once the receiver arrived on the lab. And now the infrastructure is ready. You can see that we have roads to the mountaintop, and we have the windbreak, and the building for the lab is ready, and the trunk can go to the mountaintop directly. And our lab equipment for the experiments are ready, and we also have a lot of auxiliary equipments there. So our plan is that we will deploy our telescope in the winter of this year, and our receiver is now tested in the Stanford lab. This is the measurement for the water vapor. We have achieved 2 years data for the PWV measurements with a local radiometer in our lab building. And these are the results here in the winter. You can see that in winter, the Earth station is really very dry. You can see that from November to the March next year, each month, the water vapor is less than 1 millimeter. And we also compared our measurements with the other data analysis from different measurements, like the satellite meteorological satellite observations from MER2. And also we compared the results with the local weather station radiometer from the balloon. You can see that, these results are comparable with each other, and the local radiometers measurements are smaller than these measurements because these are, focused on a large regions around our area, and this machine focus on, the lab environments. And our lab is, on the mountaintop, it's dry enough, so you can see that the water vapor is really very low.
But could you send also the value of one of the more new videos of transparency?
Yes, the balloon is provided by the local weather station, so we cannot, set.
How high is the balloon?
Oh, the balloon will, several thousand meters high to above the Earth.
Because these days, like boomerangs, they are flying and the altitude 42 kilometers. You see high.
Yes.
But it opens new windows of transparency. It doesn't open new windows of transparency above 300 gigahertz.
I'm sorry, I cannot get the question.
You see, 300 gigahertz is actually the end of the windows of transparency. Now, if you go above atmosphere, do they hear high frequencies of transparency?
Yes. Yes, if you go to the high frequencies might be carried out for the observation. I think you can observe it. Go to the higher places, like higher than 6,000 meters. Now we have 5,200 meters above sea level. Yes, that's true. So our weather condition is similar to, those in the Atacama deserts. So in the Atacama deserts, their water vapor is around 1 millimeter. This is the conclusion. So now I will move to talk about our experiment at CPT. This is a collaboration. We collaborate with Stanford, NIST, and ASU for the development of receiver. And this is, the group in 2019, we visit the sites. Okay, so this table summarizes our basic pictures for the telescope. So at CPT-1 is a degree scale CMB parameter with an aperture of 72 centimeter. And at CPT-1 has two major channels around 90 gigahertz, 150 gigahertz. And we use, the popular CMB sensors of transition edge sensor, TES sensors, very sensitive. In our focal plane, we can host 19 modules. And for the two channels, 19 modules can host up to 32,000 detector arrays. And it is now the largest small aperture telescopes around the world, larger than BASF 3, and also the detector arrays is also larger than SO small aperture telescope. This cartoon show you the structures of CPT-1. It contains two major independent sections. You can see the top section is the optical section. It contains two lenses and several IR filters. And with the optic system, it will focus the photons into the focal plane. And in the lower sections, these are the camera sections. The camera sections will hold up, detector rays on the focal plane, and the detectors will be cooled down to the temperature around 280 millikelvin to let the TES sensors to work there. And the whole camera system will be cooled down by the PT 420s, two types of PT 420s to keep the lower temperature. And if you go to the modules, you will find, within one modules, there are detector rays here. You can see lots of layers here. These are the silicon antennas, and under the antennas, there are the wafers for the detectors. And also on the bottom of the modules, there are RF chains for the code readout system. And this is the real picture for the focal plane. And you can see that the focal plane can host 19 modules. And for each detector pixels, look at like this, we have two channels, on each corner. And you can see that in this corner, there are 90 gigahertz to sensors for observing the polarization signals at different directions, X and Y. And also this is for the 150 gigahertz two channels. And this is a bandpass for the two channels. And we compared with, the designed bandpass lines and the measured bandpass lines from the lab testing. And before we deploy the telescope in the past 6 years, we are focusing on developing the pipelines for the simulation and data analysis. And we want to, build up the pipelines to do more realistic simulation and try to make the sensitivity forecast. So now our pipelines can hold the CMB data in the 2D domain, the map domain, and the pulse spectrum domain. So we can realize the end-to-end simulation. So in our simulation, we realize, the sky signal simulation. The sky signals includes those components for the lens, the CMB, the galactic emission, also the diffuse foregrounds, compact sources, something else, all that can observe the components. We try to simulate them in the microwave sky.
So also we have considered, you know, the weather station information for the wood vapor emissions to mimic the atmospheric effects. And also we have adopted a real scan strategy for ICPT1, and also we simulate, you know, the real pointing and the detector response and the realistic time ordered stream. And then finally, we simulate on the data site for the whole observational season, namely the about 1,000 hours observation in the winter season. Taking these data sites, we do the science analysis and do the forecast. So here I will show you the noise model for the single detectors. So with the single detector noise model, we can set up, you know, the noise models for the whole focal plane. And we adopt the scan strategy. So this show you our scan strategy. You can see that this patch has a clean patch in the northern hemisphere with locations here. And this is about 10% of sky. So once this sky can be attached in other region, we will focus observing on this patch. This is clean patch. And once this patch, you know, fly away, we cannot touch it. We will do the wide scan survey, and we can survey about 50% large sky, including, you know, the galactic planes here. And this large sky patch can do rich cosmological studies like the foreground sciences, the point sources, and we also try to, you know, observe the transient events, because ICPT has very large field of view. And with this scan strategy in the noise model, by estimation with the whole observational season data sites, we estimate the noise level of our, you know, sky patch. So for the 10% sky patch, you can see that with the 4 modules observing for one observational season, we can get the median value of the noise level around 14 Milky Acme. And with 19 modules observed 1 year, we can get to 6 Milky Acme for the whole focal plane. And once we accumulate a longer, like 5-year, 19 modules, we can achieve around 3 Milky Acme, and which is, you know, this noise level is very close to the scientific goals of the CMBS-4 target. So you can see that, you know, ICPT could provide a good complementary in the northern hemisphere. And this map, we compare the sensitivity of ICPT 4 modules 1 year with the Planck's observation. You can see the color bar is same, and this is, you know, the noise level of ICPT1, 90 gigahertz, 150 gigahertz. This is the 2 weighted, you know, credited map. We can see that with 1 year's observation, we can achieve better signal to noise ratio than Planck. And we hope that, you know, with 3 to 4 years observation, we can get to comparable our sensitivity, and the curve behaves like here. And we hope that we can, with this sensitivity, we can test the existing inflation models. And in the first step, before we have accumulated longer data, we will focus on the E-mode, and we can do cosmologies with the E-mode sensitivity. So you can see that here we plot, you know, the signal to noise ratio of the E-modes for different data sites. So one module observed 1 year, we can get the curve from the same right line here. You can see that it's comparable with Planck's current E-mode sensitivity. But for the 10 modules 1 year, we will get better sensitivities in E-modes than Planck. And with larger data accumulates, we can get to the cosmic variance limited measurement of the E-modes. on these scales from multiple L's from 50 to around 500 scale. So we hope that with precision measurements of G modes, we could do some science of dark matter and early dark energy model testing and adiabaticity initial conditions testing. Okay. These are our current science roadmap. And here is a summary. So we hope that ICPT could open a new window in the Northern Hemisphere for the detection of primordial gravitational wave. And our timeline is that, we plan to deploy the receiver in the end of this winter. So we hope that, lots of scientists could have interest in our science, in our experiment, and we can do, good science with ICPT. So I will stop here. Thank you. Okay. Oh.
How do you
Thank you. Bicycle array will reach senior sensitivity of your symptomatic one in 3 or 4 years, while Iceberg by 2035 will have 10 times better. So how do you compare with these other experiments?
Yes, now I think BICEP the cap their 2 sigma upper limit is around R less than 0.036, right? And yes, our goal is that with 3 to 4 years, maybe we are well, at the first stage we cannot compare with BICEP and CAC. Yes, we hope that with years of observation, like 2 to 3 years, we can get similar sensitivity. Like the forecast results show that, here, our final goal is that, around 2030, we can get our sensitivity to R less than 0.01. Yes, because our focal plane is larger, we can host, 5 times detector arrays than a BICEP CAC, than BICEP 3. BICEP 3 now the focal plane can host up to 2,560 detector arrays. But our focal plane is can host up to 32,000 detector arrays. So we want to with a larger detector arrays to observe shorter times to get a similar sensitivity. That is our roadmap. Yes.
Okay, so but you know that actually the main problem is holographs, as you
Yes.
know very well.
Yes.
There is like an experiment with I forgot already 18 or 15 sliding frequency because there is very small two windows where you could see primordial behold from polarization from gravitational waves, right? Now, I do like he also told me something optimistic proposal, okay, maybe measurement from but other people say that okay, you can never reach these kind of things. Even it's not quite clear that like you will reach this thing.
Yes, Lightbird will happen, later than 2032.
32.
Yes.
Okay, so perhaps 35 or maybe even 40. Because it's postponed,
But the foreground we will have way, I think. You see, there's windows, the CMB channels lies around the 90 gigahertz, right? And for the polarization signals, the lower band is dominated by synchrotron. We have lower band. And for the higher band, it's dominated by thermal dust, but we can also have channels in the higher bands. Yes.
Even synchrotron. Okay, when you are using spectral length, 3.3 is not quite clear. Is it correct or not correct? Because spectral length for synchrotron can go quite flat. If you flatten, it means that for synchrotron you need many more frequencies to trace it to have
Yes, you are right. Yes, you know, this window, we can have, you know, thinner windows, separate windows.
Yes.
So I think that within one band pass, you can observe one synchrotron parameters. Once your your synchrotron models becomes complicated, maybe we can have more windows here, try to observe these parameters clearly. I think that is a philosophy, yes.
That's a good question. So in a realistic setup, do you expect to see the model of gravitational waves before LISA? So what are the time scales of observations?
No. We see the primordial gravitational waves, but this will detect, you know, the gravitational waves from black holes or yes, white binaries. It's different science scale, I think.
Black holes providing neutron stars,
Yes, well, when is their scientific plans, they try to find this kind of gravitational waves, when it will happen?
Well, this is my question. I mean, we claim that this would be 2037. You said 2032, right? So what are the realistic time frame for that? This is my question. When do you expect it?
Okay, we will deploy our telescope in the winter of this year. Yes, that is our plan, but I don't know Lisa's plan. Sorry.
Yeah. It may be better during circuit break.
Yes, we have to have a bit of a problem. So let's take the speaker again.
Just two important announcements, one from Anna about posters and one from.
So I have a brief announcement that today the experts actively working in gravity exploring in quantum field theory, namely Alisa Platania and Gary Schwarzenegger and Alice Liebman. We will decide about the best poster, which order will be invited to make a presentation on Friday, make an oral on Friday. Sorry. The decision will be announced during the last session today. During these poster sessions, I kindly advise to be near your poster to answer questions and provide some explanations. And we are looking forward to many nice discussions.
And those who didn't complete the list, please complete them because we can't put them for dinner tomorrow. Tomorrow at 6 p.m. we continue. And we recombine in 20 minutes, 10 before 11.
You're obviously. Yeah, yes. Nice to meet you. By the way, I wanted to. You are. It's my talk is today after the. Yeah. In the afternoon. Yeah. We can put a. Sure. Yeah. So. This is the laser pointer. This will make your slides forward. Okay. Let me show you. Okay, sure. So. Oh, because this is not.
Did you start screen share?
Exactly.
Where is Siam? It's his, he did this.
Yeah. No, the down one. The down one. Yeah, okay. Yeah, so let me upload your slide. No, there are unfortunately many folders, but I know, of course, where I should look. Should be close to the end. And it should start with my name. Just we have to take the correct. So let's copy, yes?
Yeah.
Which folder?
Yeah, so.
Okay, let's maybe. Let's check if it is the size should be correct. I don't want to change the name, but okay, I think it's still the area. Okay, yes, this is here. So okay, I can eject.
Yeah, sure.
Yeah, I don't know this way. How do I? Okay. Just. So you are a postdoc here with Alex, eh?
Yeah.
What are you working on? I spoke a bit with Oleg because we shared the same supervisor, not the same time, but Roberto was also my supervisor at season.
Yeah, I'm working in non-Gaussianities of non-local theory.
So more for the cosmology.
More
Yeah?
for philosophy.
Why did you take your PhD?
In India, so Indian Statistical Institute.
Okay, so you just came from India to China here.
Yeah.
Okay.
Alexei, can you come? Alexei, can you come? This Windows is giving me trouble.
No, ask Xian, please, okay, really.
Okay.
I don't know what do you want exactly, but give this job to Xian. Just call him and say, look, Xian, we need a trouble. Oh no, we need to solve the trouble. I want to find list for Dina. It's appeared.
Hello. Yeah.
I don't understand you. Tell me. WPS I should close, but it is not closing. You see, there are lots of, I don't understand. Yeah, it is not right clicking. I don't know why.
theory is traded for a negative norm state of the quantum theory. And in the quantum theory, all perturbative states have positive energy. Loss of unitarity is also not caused by a negative norm state. The theory still has what we can call S matrix unitarity, or in other words, the optical theorem is still satisfied. The unit operator in that S matrix unitarity relation, you have to be careful to say what it is. That unit operator is related to what appears in the completeness relation in the theory. Before getting to what the actual problem is, let me say something good about negative norm states. In this theory, the scattering amplitudes of gravitons at superquantum energies have bad high energy behavior, just because you can see at tree level, you have this, the amplitude is coming from interactions with four derivatives. But negative norm states cause cancellations to occur at the level of differential cross sections. And so sufficiently inclusive differential cross sections have good high energy behavior simply because of these negative norms. So that's the topic of another talk. So let me get to the problem here of what is the problem with a negative norm? Well, negative norms can cause negative probability by the Born rule. So you see in the Born rule there's the norm of the initial state and the norm of the final state. If one and only one of those two norms is negative, we get a negative probability. Okay, so let's call the sign of the norm of a state the ghost parity. So let's first of all consider theories that preserve ghost parity. So in those theories, ghost parity does not change from initial state to final state. So those two norms are either both positive or both negative, and we would have always positive probabilities. So here's an example where a probability interpretation exists even with negative norms. Well, we're actually more interested in the other type of theory that violates ghost parity, because that's what would happen in QQG. And in those theories, something more is needed, and that's the topic of this talk. And to approach this problem, let's go back to quantum mechanics, which can be viewed as a 0+1 dimensional quantum field theory. And because of the problem I've just been talking about, this problem has already brought focus on some extensions of quantum mechanics. There's so-called PT symmetric quantum mechanics discussed in this context of quantum gravity by Mannheim and Bender. And Alberto yesterday told us about direct Pauli quantization, also in the same context. Well, we're going to follow a similar path, follow canonical quantization geared to a ghost theory, and just see where it leads. And the path we follow will sometimes overlap with one or the other of these other approaches. Yeah, well, yeah, I'm going to be talking about interactions. So here's the basic picture, which is also true of those other approaches. And the main point is that unitary evolution is fundamental to quantum mechanics. And because of it, a lot of the things that we like in our theories follow from it, in particular the spectrum of the theory and the correlation functions that are of interest in quantum field theory all follow from unitary evolution. Now, the formulation of the Born rule is something to obtain probabilities from the theory. And that's a separate aspect of quantum mechanics. So in that case, then it suggests that we can modify the Born rule and not affect everything else we already know about the theory from unitary evolution. So that's the basic idea, basic picture.
And that leads to the question, okay, does that type of modification even exist? And if it does, is it unique? So for the rest of the talk, I'll set up the theory. Here, I would like to thank James Stokes, who worked with me at an early stage of this work. I'll identify two apparent problems, and then I'll show how the following two things could arise: a positive spectrum at both weak and strong coupling, and a positive inner product. And then some other topics: I'll obtain wave functions and a coordinate representation. I'll compare spectra with PT symmetric quantum mechanics. And lastly, I may not have much time to do that, is to consider the case where we do have complex conjugate energy eigenvalues. And maybe I'll just mention why that's of interest. So the setup, take a Hamiltonian, introduce a new parameter into it, sigma, which is 1 for a normal theory and -1 for a ghost. So that parameter just appears in front of the kinetic or quadratic terms in the Hamiltonian. And everything else on the slide is completely standard: the commutation relation, the relation to the annihilation and creation operators, and that commutation relation. So the difference between the two theories shows up when you construct the Hilbert space, in particular, construct the occupation number basis for the Hilbert space. In the normal theory, we know how that goes. In the ghost theory, you see that all that has changed is we've interchanged A and A dagger. So A dagger, I know it's a vacuum. So with that information, then you can work out the norms of these states, and you find that the sigma, which is plus or -1, shows up as a power to the end of the norms. And this is the problem: negative norms. Now the sigma.
Antonio theory is always Commission.
Yes.
But it's not coming from the.
I'll get to that. Well, I've already mentioned that it is bounded from below. I said all perturbative states are positive. And that's going to follow from this quantization that was laid out here. Okay, so sigma enters in two other ways: in the completeness relation. The norms are appearing here, so you get a factor of sigma at the end. And when you expand the general state in the occupation number basis, you have the expansion coefficients. When you solve for those expansion coefficients in terms of this matrix element, again, a factor of sigma at the end will appear. So this is the basic setup, and there are, I think, what look like different, but I also think equivalent ways to quantize ghosts. And for example, Alberto and Strumia, I think is equivalent, although they use quite a different notation. So I'll be trying to set up a matrix notation. So consider some infinite matrix, bold A, and some infinite column vector, bold psi. So the components of these things are the matrix elements of the operator A and these expansion coefficients that I just mentioned. And I'll also introduce a matrix, eta, which just has these powers of sigma on the diagonal. So in the ghost case, eta minus is just what you could call a ghost parity operator in the occupation number basis. For example, an operator product in matrix notation brings in this factor of this matrix, because you're inserting a complete set of states here. And any given operator you want to look at in matrix form will also end up depending on sigma. For example, the matrix form of the field phi depends on sigma. So I think you're starting to see how everything depends on sigma. From now on, I'm going to drop the sigma subscripts. And for the most part, we'll be talking about the ghost theory, sigma -1. So the first thing is the inner product. And in matrix form, again, the matrix eta appears in two ways. Often I'll be using the second way. So So with the inner product, then we know what a self-adjoint operator means, satisfies this, which in matrix notation, again, brings in the eta matrix. Now, when I say something is Hermitian, I'll just mean it in the usual sense, so A dagger equals A. Okay, so self-adjoint is not the same as Hermitian. If we have a self-adjoint matrix, then we can define a different matrix, eta twiddle, which is eta times A, that'll be Hermitian. On the other hand, if A is Hermitian, then eta twiddle will be self-adjoint. Now, as I just mentioned, the ghost Hamiltonian is Hermitian. So that means there's going to be another matrix, H twiddle, which is self-adjoint, and it'll play a central role. So for example, if we consider unitary evolution, we can translate the usual evolution of an arbitrary state into a matrix form, the evolution of this column vector. And it's the matrix H twiddle which appears in this matrix form of this evolution. We can consider a particular row vector, and it evolves also with H twiddle. So you can see by these two things I've chosen here, that just makes up the inner product, and the inner product then has the cancellation of these time dependence. And that's as required by unitary evolution.
One species right now.
We have one field, yes.
How long do you have both?
Yes. Well, first of all, let's consider interactions with one first. I also have looked at putting the two together in a way that I'll describe here. And you can ask me at the end of the talk about that. So if you look at the energy eigenstates, let the energies En and the states, the energy eigenstates labeled by n bar. Here's their eigenvalue equation. But in matrix notation again, we're representing these energy eigenstates by bold psi super n. Again, in the matrix form, we have this H twiddle appearing. Similar for this row vector. Now it's E star that appears. So what's going on here? Well, we have two types of energy eigenvectors, the right and the left eigenvectors. Simply again, because H twiddle is not necessarily Hermitian. And also we've seen that the energies need not be real, again, because the H twiddle is not necessarily Hermitian. But putting these two things together, we find that En must be real, except when the norm vanishes. So there's nothing preventing the norm from vanishing. So there is an issue here with possible complex energies. So let's consider the other issue, probability for some transition from state I to state F. And using the product I've just been talking about, gives us a Born rule. Automatically summing over F does give 1. That's just for completeness. This is also the analog of what I was calling S matrix unitarity. But it does not work for the other thing we need. For any particular I and F, it has to be between 0 and 1, but that does not necessarily occur here because of these possible negative norms. So this is another issue. So far then we have two apparent problems. The energy spectrum is not guaranteed to be real. And we have these negative norms. We can write down the norms now of these energy eigenstates. And we will find that, again, they just alternate in sign. So we have negative norm energy eigenstates. So with these two issues, let's go for the first one first. Let's see where and when and if complex energies actually occur. And then we'll try to deal with negative norms later. No, the unitary evolution is still preserved. That cancellation I mentioned between those factors of e to the I, P, H, twiddle, that still cancels.
How do you treat a classical limit in such a quantization? Like any correspondence to the classical evolution or?
Yes. Yeah, we're talking about a quantum theory of superplankton energies. And I'm saying that it may well be that this theory is a quantum theory, and that's it. There's no such thing as a classical limit of this theory. Only at lower energies, where you go below the Planck scale, then you go over the Einstein gravity, and that does have a classical limit. So that's the best we can hope for. So yeah, this is an intrinsically quantum theory, and that's it.
I assume that the cosmos is the order of time.
Yeah, I always will assume that.
So you said that there is no semi-classical approximation.
Or no classical limit. So there's no sense in which you can take H bar to 0.
We probably say, if you want to find a different product, and then it's classical in terms of that product.
Yes, I'm following those footsteps. So we are going to get to that. After I look for complex energies, I'll come back to what you're talking about and look.
You're doing is fine.
Yes.
The problem is the more we put
Yes.
two types together.
Yeah. So going back to the H twiddle, we can get that from the quantum Hamiltonian by making the replacements of the quantum fields by the matrices. And looking at the quadratic part first, even when there's a factor of sigma here, these fields are both non-Hermitian and also depend on sigma. And so what comes out is a standard positive energy free spectrum. And this is the reason why this quantization was chosen. So as I said, all the perturbative energies are positive here. But as we keep hearing that we need to consider the interactions, so let's consider K-even theories first. So even powers of the field in the interaction. As it turns out, this theory is Hermitian. And so this theory automatically has real spectrum. So we're not finding complex energies here. Also, because of even powers of phi, this theory also preserves ghost parity. Or in other words, H twiddle commutes with eta. And as I said at the beginning, in such a theory, all probabilities are automatically positive, and this gives an example where negative norms can coexist with the probability interpretation. Now, if we look at these K-even theories a little closer, it is true that the normal and ghost versions of these theories have different H twiddle, but they are isospectral. They have the same spectrum. Looking at the full propagators, I'll get to showing you what these propagators look like later. But in this case, these propagators just differ by a sign between the ghost and normal theories. Looking at any amplitudes with 2, 6, and 10 ghosts in them, the corresponding amplitude in the normal theory will just differ by a sign. So that's not much of a difference. With only these differences of signs appearing in amplitudes, it seems to me that the ghost theory with ghost parity is physically equivalent to the corresponding normal theory. So these ghost theories are just a fancy way to rewrite a normal theory. So let's move on to the K-odd theories. These are more interesting. And now the normal and ghost theories are distinctly different. And with the normal K-odd theory, for example, phi cubed, we know it has a problem. The spectrum is not bounded from below, at least for lambda sufficiently large. And then if we go over to the ghost version, in addition to that problem, we have the problem that we finally have a theory where the Hamiltonian is not Hermitian. Or, sorry, H twiddle. The original Hamiltonian is Hermitian. This H twiddle, which is appearing everywhere, is not Hermitian. And it therefore looks like complex energies are going to come out. But it turns out these looks are deceiving. The K-odd ghost theory turns out to enjoy a positive real spectrum for any coupling. So to tackle that, we have to look at a numerical study. Numerically then, to approach these theories, we truncate the Hilbert space by considering a finite size matrix. That we can easily diagonalize numerically, and then just study the behavior of these eigenvalues as we keep making the matrix larger and larger. And what we find is that there's always a lowest lying set of eigenvalues that are positive, and that set just keeps growing and growing as the matrix gets larger and larger. So for a matrix size of here 600 by 600, the first 40 eigenvalues are positive for both weak and strong coupling. And what's happening is there are these complex energies higher up, and as you just keep making the matrix larger and larger, those complex energies are being pushed to infinity in the infinite size limit. So that's why I would say that this theory just has a positive real spectrum. Numerically, we've got the whole theory, the full Hamiltonian. We just diagonalize it numerically for any coupling. So I can show you some values here. So this is for the K=3 ghost theory. And I'm showing you results for weak coupling and strong coupling for the first 10 energy levels. And I've said already that this string of real numbers will continue on to up to 40 energy levels before you start seeing some complex energies appearing. So for weak coupling, you see that the energy levels are close to the 3 values, but for strong coupling, the energies are increased and the energy splitting is increased. So this is showing you why we're not finding complex energies, because these energy levels are being pushed apart. And it's the other case where energy levels can merge. That's where you would expect something funny happening, like complex energies would appear if some energy levels came together. Now, what are these Z factors? These Z factors are how these states contribute to the full propagator. So here's the full propagator. It's the full ground state here. And so it has a vacuum term, and then a sum of terms involving these Zn factors times the Feynman propagator for 0 + 1 dimension, which is just this. It has a mass, but the mass here is being replaced by the energy of that corresponding state. These Zn factors are known. Again, as soon as you diagonalize the Hamiltonian, you know the eigenvectors, and you work out these matrix elements, and you know the eigenvalues, so you know Zn. And we see that Zn quickly dies away. So even a fairly small number of Zn's give you an accurate value, accurate result for the propagator. You also see here the dominant contribution, even at strong coupling, comes from the first excited state, which is giving you that negative contribution. And this is the negative propagator that I mentioned at the very beginning. This defines the ghost theory. Okay, so I had 2 apparent problems: complex energies. I've looked for complex energies. They show up in the truncated models, but they don't show up in the infinite size models. So that's one issue. So let's move on to the other issue, these negative norms. I'll get to the connection to PT theories. Okay, so negative norms. So how are we going to deal with that? As I mentioned, to deal with that, we have to try to modify the Born rule And to modify the Born rule means modifying the inner product. So let's just start off. Let's just say, let's consider a new inner product defined by some new matrix. And so in matrix notation, it's like this. It's a Hermitian matrix G. It's a G inner product G for ghost. I'll also write this inner product in a different way, again introducing a G twiddle matrix, eta times G. So in this way, you see that G twiddle is the new factor inserted into the old inner product, the old eta inner product that we had before, to convert that into the new inner product, the G inner product. So in this form, we see that if the G inner product is to be preserved in time, which we necessarily need, we see that for that to be true, all that has to happen is that H twiddle just has to be able to be commuted through this new factor in the inner product. In other words, G twiddle has to commute with H twiddle. This means that the energy eigenstates are also eigenstates of this new matrix G twiddle. So G twiddle acting on the energy eigenstates are just some eigenvalues. Well, now we can figure out what is this H twiddle? Well, what do we want it to be? What we want it to do is to change the signs of the norms. And we know that the norms have these signs. So if this new sign factor is introduced into the norm, we've canceled the negative signs. So that's what we would like G twiddle to do. How do you actually get a matrix to do that? Well, here's the answer. A sum of terms like this, where in the numerator that's a matrix because we have a column vector times a row vector. And this is a non-trivial matrix. It's in the original occupation number basis. All our matrices are numerically or explicitly in the occupation number basis. So by non-trivial, I mean typically all the elements of this matrix are non-zero. So if we square that G twiddle, then you can easily see that you'll end up with this sum of terms, and that's nothing but an expression of the completeness relation. So G twiddle squared is 1. Now, anyone familiar with PT symmetric studies will start to realize some of the things I'm saying are familiar to you. And this is one of these things. G twiddle turns out to be self-adjoint with respect to both inner products. H twiddle is also self-adjoint with respect to both inner products. So that's that statement for the G inner product. Now, the most important thing about this new norm is that G is a positive definite Hermitian matrix. And that is what is going to give us a more sensible Born rule. We can even make things look simpler still by looking at the G inner product for the energy eigenstates. The whole point here was to eliminate the minus sign, so it's just proportional delta Mn. So if we want to write a general state in terms of the energy eigenstates, define new expansion parameters, psi twiddle, define new column vectors. Now the G inner product is just the standard Dirac inner product. So we've reduced it back to what we're familiar with. But the rule here is not the same as usual. We need an additional step to write down that form of the Born rule. We have to first of all determine the energy eigenstates of the full Hamiltonian. And in that basis, obtain these expansion coefficients, and then using those, we get the standard form of the Born rule. So we have modified the Born rule because we have to go through all these steps to get there. Or if you wanted to work directly in the occupation number basis, and these are the expansion parameters in that basis, we would just have to use the G matrix explicitly to get the same result. Okay, so I think I've addressed those two issues that we had with this theory, at least as far as I can tell. So let's move on to a different topic. I'm heading towards a coordinate representation and to find what the wave functions look like as a function of the coupling. Well, how do we find an observable in general? Well, going back to an eigenvalue equation translated into matrix notation, a twiddle appears. So that means an observable is going to require this a twiddle to be a Hermitian to get real eigenvalues. Or in other words, the original operator has to be self-adjoint. So that's what we're learning here. Self-adjoint, any self-adjoint operator could be an observable. Well, this is nice, but the story with the Hamiltonian is not like that. The Hamiltonian itself is Hermitian, it's not self-adjoint. And as we saw, H twiddle is not Hermitian. So in this case, why or how we ended up with real eigenvalues seems to be an exception to the rule. And it only occurred in the infinite size limit. Okay, so let's find a coordinate representation. So we can just start off with the commutation relation between Q and P. Assuming we don't know ahead of time what those things are, we can go over to a matrix notation, bringing in the factor beta, going over a twiddle matrix notation, and then we just look for matrix solutions to that equation. And there are two sets. Q twiddle and P twiddle can be the original fields phi and pi, or these I phi twiddle and I pi twiddle. In both cases, these are all Hermitian matrices, so we are going to get real eigenvalues. And it turns out that the second set is the Dirac-Pauli choice, but there is another choice here. Going back to the original Q and P, this means that Q is eta times phi. So there's that choice as well as Q being I times phi, which is the Dirac-Pauli choice. Let's go with the Dirac-Pauli choice. If I can remember later, I'll mention what happens with the other choice. So we just use that matrix and look for eigenvalues just like we've been doing. So this is the matrix eigenvalue equation. The eigenvalues will be the real positions, and the eigenvectors are labeled by a superscript x. So those coordinate eigenvectors can be used to construct the wave functions for the energy eigenstates by just taking this inner product here. So involving the coordinate eigenvectors and the energy eigenvectors. So that's a wave function. You can consider that to be a wave function. And we can do the same thing for the momentum-based wave function. And so let's look at these things at zero coupling. So as I mentioned, we're looking at the full energy eigenstates. So we expect dependence on the coupling. So if we just look, first of all, at zero coupling, I'm showing results for the ground state and the second excited state. And at zero coupling, we just get the same results for the in momentum space. So the blue is the ground state and the orange is the second excited state. And so you might be wondering, well, how am I getting these curves? Well, I'm going back to that 600 by 600 matrix. So I'm getting the energy eigenvectors. They're 600 components long. And that's giving me enough points to make something that looks like a smooth curve here. If we turn on the interactions, then these wave functions are modified and they're more localized. Now, if we go over to momentum space, we would then expect those wave functions to be more spread out. And we do find that, but something else also happens. We do find wave functions that are more spread out, but they also break the parity. So a parity would just flip these things around p equals to 0. And so these wave functions are not parity invariant. And I'm saying that this is the case because the parity is being explicitly broken by interactions. Now, as it turns out, the action of this eta matrix does cause a parity flip on the on these wave functions. And we've already seen that eta does not commute with these k-odd ghost theories. So maybe this is not a surprise. What's the effect of the G inner product on these wave functions? Well, it keeps them the same. At least the absolute values stay the same. The eta inner product in the coordinate basis, so if you consider the x prime x inner product, this is something that Alberto is very familiar with. It's a matrix which is not diagonal. It's delta minus x prime. That's a matrix with negative eigenvalues, just like we've been finding negative norms in the other representations. But for the G inner product, consider the same thing. That matrix has no negative eigenvalues. It's still a non-trivial matrix though, and it's only when the coupling vanishes does it go over to the standard result. Okay, so I don't know how much time I have left. I'm almost finished.
11:30. Starting from.
Yes, okay.
Any questions?
Follow question. So if you take clearly proof of renormalizability of the theories you started with, it was not using negative norm and all the rules which you introduced. So I wonder if these rules are introduced, is his still valid?
His quantization is the one I'm using.
Yeah.
He has negative norms, and that's what I'm dealing with here.
Okay, so you say that there is none of these rules violate his rule.
I don't know what he would say about this modified Born rule, but nothing else I'm doing is altering what he's doing.
John Donahue, of course, talks similarly to these theories. Talking maybe on decay. The question of whether it actually constitute initial and final states. Can you illuminate us on the relation in your discussion?
Yeah, the third topic that I never even got to is related to that question. And so the third topic was to look at the finite Hamiltonian case where we do have these complex energy organized. And that's related to a new paper on this debate on what happens to the ghost propagator when it's corrected by one loop correction, which is what John's talking about. And he says that causes a decay backward in time. Now that debate is still going on. There's a paper by Kugel and Kugel recently. Now they disagree with Donahue, and they argue that there is in fact an asymptotic state, which is a ghost, caused by this correction to the ghost propagator. And I would argue that that's fine, but I would say if you add a G inner product on top of that, then that asymptotic state would turn into a positive norm state. So in either case, it doesn't decay, it's a state that's in the spectrum. So I'm just saying there's an ongoing debate on what's going on with what seems to be an simple question. You've got a propagator, you put a one loop correction in it, and no one can agree on what happens. So I think this just gave a simple model, a simple finite matrix model, where you could study more closely these states that have complex energies. Just going back to your other question, so I gave you numerically the result of an interacting single ghost theory. I've also considered ghost theories of the type you're talking about, where you have a ghost and a normal particle. And I can numerically study that. And I also find positive energies, even with that interaction. Now, these are all maybe results that sound a little strange and hard to believe. But that's this key connection. People have been talking about such strange things for a long time. And there is a connection between what I'm talking about. If you transform it into the corresponding PT theory, then you can start to see the relation between what I'm saying and what they're saying.
Yeah, and again, that paper by Bender and Lampard is really only at the linear.
I agree, yes. Well,
Happy to agree with you, you can do what's fine.
I mean, independent of that theory, I mean, Bender and collaborators have studied many theories, not just perturbative theories, with interactions, everything. And a major theme in their work is to find this new inner product, which is positive, right? For interacting theories. And sometimes it's not easy to do, but that's what they do. So they just haven't brought that machinery into this story, of what you are referring to, where they seem to ignore interactions altogether.
There's a work by Alessandro Strumia. It was published later compared to the one that you mentioned, single author paper, where he computed the spectrum of the Pi-Suddenberg oscillator, which includes also an interaction, and found some eigenvalues. So I think this model is more representative of the quadratic cavity case, because it's a 4-derivative model. Well, as far as understood, in your model, you just put the 2-derivative model with the minus sign plus an interaction, which is different from quadratic cavity case.
Well, it's a piece of it, yes.
Well, for example, it doesn't have the two,
yes,
at least 2 degrees of freedom. One that has the plus sign chaotic term, and the other one has the minus sign.
But ahead of time, there was a possibility that as you turn on the interaction with such a theory, it would destroy itself. But it doesn't. And I'm saying that also carries over into the case where you have both.
Yeah, I just wanted to mention this word because he computed the spectrum, so it's along the line of the computation of the Pi-Suddenberg form.
Okay.
So our last speaker of the our next speaker is Gaussian. He will talk about multiplying gravity without density with equation. Let's welcome.
Exactly. Okay.
First of all, let me thank Alfie and you for the invitation, and it's a great honor to be here and share with you our recent attempt to construct the modified gravity without actual degrees of freedom. So, first of all, I would like to mention a brief motivation to modify gravity. So, I just listed two motivations. One is from the phenomenological side. So, there are two novel concepts. One is the detection of the accelerating expansion of our universe. The other is famous the detection of the gravitational waves. And in order to explain the accelerating expansion of our universe, so one motivation is that the gravity may be modified on the cosmological scales. But we are theorists, so for us, the most important motivation is to check the conditions that the GI is based on, so that we can understand why, if and why GI is the unique theory for the gravitation chosen by nature. So we can modify or just tune the various conditions GI is based on. So maybe we can find there's something wrong, so we can understand GI is the unique theory. This is the most important to to us. So then how to modify gravity? So in the past more than 1 or 2 decades, the most important tool to modify gravity is to play with degrees of freedom, DOF, degrees of freedom. So the key question is how to keep the correct degrees of freedom. Because recall that one of the most important motivation to modify gravity is to explain the accelerating expansion of our universe. This means GR by itself cannot be explained. So we must introduce something more than GR. So, but something more, but not more. I mean, we cannot introduce something dangerous or something we don't want. So this means the correct means something more than GR, but not too much. So to be very precise, we must introduce the wanted degrees of freedom, but to eliminate the unwanted or boost-like degrees of freedom. So this is the main tool to modify gravity. So with this in mind, so we can classify the various theories of modified gravity into 2 classes or 2 phases. One is to introduce something more. So the motivation is just to explain the accelerating expansion of our universe, or to explain the dynamics of the primary inflation. So this means we must introduce some extra mode without ghost, something more than GR, but not too much without ghost. So this means gravity is more than GR, and there are some typical theories. Maybe many of you know the theories like Monastic theory, the degenerate higher order skeleton theory, for general gravity, the effective field theory of inflation, geometric gravity, and so on. There are many such kind of theories. Just to introduce something more than GR, but I just in this slide I just show a simple example. The typical or the most well studied or most well known modified gravity theory that is the skeleton theory. This is the timeline of the development of the skeleton theory from the general relativity and from to the relativity and KSS and the Monastic theory. Those. So the right hand side is Lagrangian. You can see that during the time evolution, the Lagrangian of the theory becomes more and more complicated. And of course, this is the after the degenerate higher order skeleton theory. So we can say that it is the most general skeleton theory where the second order derivative Lagrangian, but still have just one scalar plus 2 tensor degrees of freedom, which means there's no extra mode, degrees of freedom. But since the Lagrangian becomes more and more complicated, so there is a difficulty to further extend or further generalize the theory. And this is a simple example on the left-hand side. On the right-hand side, say after the detection of the gravitational waves, so the main interest of the community of modified gravity suddenly changes from introduce something more than GR to introduce nothing more than GR. Nothing means we think that the gravity just the we call the TTDF, that is the full tensor degrees of freedom of the general relativity, because everyone knows that the general relativity only propagates the gravitational wave, tensor real degrees of freedom. So nothing more than GR means we just think gravity is just a gravitational wave. So there is no extra mode at all. Nothing more than GR. So the interest of the modified gravity community just wish to construct a non-GR theory for the TTQS for 2 tensor degrees of freedom TTQS. So this means we think the gravity is just the TTQS, just the gravitational waves, nothing more, no scalar mode at all. But the TTQS more simply just the gravitational waves. They may behave differently from the GR, from that GR. So there are at this moment there are only few examples, not so many, only few examples like I will mention it later. Pascal minimally modified gravity, the four-dimensional Einstein postulates, and the theory I call the TPDR theory, and in my talk. So then the question is how to build such kind of non-GR theory. Non-GR means we are going to modify GR, but everyone knows GR is very solid, it's very unique. There is a famous log theory, which claims that the Einstein equation is a unique equation of motion from if you want to write a Lagrangian build of the second derivative of the metric in 4 dimensions, and also you require space-time covariance. So this means if you want to modify GR, you must break at least one of these conditions. You recall that this is just our motivation to modify gravity. So this condition includes you introduce some extra variables, some extra degree of freedom, or you require some extra dimension, or higher derivative Lagrangian, or you just abandon the remaining geometry to use some like torsion or non-triviality and so on, or you just give up your code. So this is one of the approach to modifying gravity. And from the other point of view, so GR is a unique theory for the TPUF, or simply just Gaussian wave, tensor Gaussian waves. If you require Lorentz invariance and locality, this means if you just you know nothing about general covariance, but you just want to build a Lagrangian with the Lorentz invariance and the local Lagrangian, but you require the theory only propagates TPUF, and you will get GR unique. So why? Because the metric has 10 components, and in order to require a theory to propagate only 2 degrees of freedom, you have to impose that 4 of the components are gate modes. And these gate modes are nothing but the general covariance. And there are some associated 4 constraints. So 10 minus 4 and minus 4, you will get 2. This 2 is nothing but the 2 polarization of the message routing. So, and this explains the name. The TPDF means 2 tensorial degrees of freedom, also means transverse and faceless degrees of freedom. And from the theoretical point of view, so we can also understand this more in more details. If we just want to write a Lagrangian in impulsive background, like we just write a Lagrangian for the metric perturbation in a impulsive background. So first of all, we have 4 arbitrary coefficients. So this is the most general quadratic Lagrangian we can write down in impulsive background. And we just require this Lagrangian only propagates 2 degrees of freedom, not 10, just 2. Then we must require, so we know, first of all, we know nothing about gauge transformation or the general covariance. Just a condition, we must eliminate 8 components. Then the coefficient C1, C2 to C4 are uniquely determined. Then occasionally we find that this Lagrangian with this coefficient occasionally has this gauge transformation and this gauge symmetry. So, and I think everyone of you know that this is nothing but the linear expansion of the GR itself. And we can do this order by order. And formally, we can resum this expansion order by order, and we can we get nothing but just the GR itself. So from this point of view, we can understand the GR is the unique theory for Messer's graph, which is I mean, if you just write a Lorentz invariant local Lagrangian for 2 Messer's graph, you get nothing but GR. So, and then the question is, how about for Messer's graph? We just abandon the Messer's condition. And someone has tried to build the random DRGT Messer's graph to follow the same approach. Just to build the Lagrangian order by order and resum, that will get some messed up. But GI is not the potential, it's not a mass term, it's not a potential term, it's a kinetic term. So the question is, question is, can we write down a non-GR kinetic term for the method gravity? But everyone, including myself, has tried this. But at this moment, with the conclusion is that very likely GR is not only the unit kinetic term for the merciless gravity, but also the unit kinetic term for the method gravity. So just to relax the merciless condition is not enough to modify GR. So yeah, yes, in four dimension. Yeah, in four dimension. Of course, in high dimension you have some like log terms here. Then we have another options and choices. So our choice is to abandon the Lorentz invariance, because to abandon the merciless condition is not enough. So we just choose our choice to abandon the Lorentz invariance, but keep only the special covariance. So the basic picture is quite simple. So suppose this is the space-time, the four-dimensional space-time. And we just put some correlation of space-like hypersurfaces in the space-time. So on each hypersurfaces, we have only special covariance, the three-dimensional special covariance, but not the four-dimensional space-time general covariance. So then we just try to build the gravity theory only on each hypersurface, three-dimensional hypersurface. So the theory will only respect the special covariance, not the general covariance. But you might worry that people dislike Lorentz breaking theories, but don't worry, because for each, so there's a one-to-one correspondence or some like duality, theoretical duality between a generally covariant skeletal theory and a specially covariant gravity theory. So for the generally covariant skeletal theory, the Lagrangian is built a skeletal, the metric, and the Riemann-Curvature covariant derivatives, and all the quantities are generally covariant. So it's very good. On the right hand side, we have no scalar field. We have only metric. All the variables are metric variables, but we just abandon the general covariance. Our symmetry is a three-dimensional spectral covariance. So we just write a Lagrangian like this. The variables are the standard NDM variables, the 3+1 composition variables, like the Lagrange function, the special curvature, the special metric, the special curvature, and the extrinsic curvature special derivative. So all the ingredients are just a three-dimensional special quantities. So the resulting Lagrangian respect only the special quantities, of course. But there's a one-to-one correspondence. So if we start from the generally covariant skeletal theory, as long as the scalar field has non-Bayesian vacuum expectation value, and as long as its gradient is common-like, we can just fix the so-called universal gauge, which is a true prime coordinate of the scalar field. Then the resulting Lagrangian just looks like a specially covariant drawing theory. Conversely, if you just build me a specially covariant Lagrangian, we can always push the time coordinate to a dynamic structure, and the resulting theory looks like a generally covariant skeletal theory. So there's a one-to-one correspondence between these two apparently different theories, but they are equivalent physically. Oh, okay, so we are set to go further along this line, just to build a truly metric theory, but respecting only special covariance. Along this line, actually, there are some old theories, like the ghost organization, or the effective field theory of inflation, or the Hojava gravity. And if you know some of them, you can immediately realize that there are special cases or special examples of special covariant gravity. I mean, metric theory respecting only special covariance. Okay, I won't show the details, but just show this. So this is the most general, I don't say the most, but quite general Lagrangian for the special covariant gravity. So it's a purely measured theory respecting only special coordinates. And we have proved that in a series of papers, we have proved that this Lagrangian, if without other extra conditions, this Lagrangian will propagate two tensor plus one scalar degrees of freedom. Okay, so
here there are some new operators that are being included in the EFT equation.
new operators, which one?
This is most general one, especially covariance, right?
I think the actually has been included as a special case. Yeah.
So this one is more general contents.
Yeah.
New operators.
Yes, no, of course, yeah. This is the most general, yeah. You can't imagine, you can write anything else. So let's report our approach. So first of all, so our choice is to build a metric theory respecting only special covariance in order to modify gravity. This is our choice. But this is not good. This is not okay. This is not anything, because we have one sample. Because our final purpose is to build non-GR theory for the only two tensorial degrees of freedom. We don't want this scale mode. Okay, we have a framework of a special coordinate gravity. That's good. But as I said, without any condition, we have one scale mode, but we don't want it. We want to kill it. We want to eliminate it. So how? So then the question is how to eliminate this scale mode. In fact, in our previous calculation on counting the number of degrees of freedom, we have proved that as long as the last function appears linearly in the Lagrangian, this Lagrangian propagates no scale mode at all. In fact, we have already found this condition. So this means there is a possibility to build non-GR theories of gravity propagating only two tensor without any scale mode within the framework of special coordinate gravity. So then the question is how? And how to find the general conditions and how to write down the concrete Lagrangian of unknowns. In fact, there is an old example called Castanon. So this theory of this as an example, I will mention it as an example. So this theory has been proposed a long time ago, actually. Even before the invention of the theory of Galilean theory, long time ago. So the Lagrangian is not so complicated. The Lagrangian is just a special case of K-sense. But it's a bit weird because the kinetic term has a square root, the square root of the standard kinetic term. But the interesting point is this Lagrangian propagates no scale mode on a cosmological background. This Lagrangian, although it looks like a scalar tensor theory, looks like a K-sense, it has a scalar field, but it does not propagate any. It does not propagate any scale mode on a cosmological background. So it propagates only the two tensorial graphene waves. So why? Here I just show a naive understanding of this issue. So this model has a scalar field, of course, and it has a scalar perturbation. If we denote the scalar perturbation delta as psi for simplicity, so normally if the scalar mode propagates, it will based on the wave-like equation of motion like this. So this says is the scalar sum. This is the kinetic term and the gradient term of the scalar. This is the scalar sum. But interestingly, for this particular type of kinetic term, square root, you need to check out this scalar sum is infinitely large. It's infinitely large. Infinitely large means this gradient term becomes dominant, but the kinetic term becomes negligible. So this means a wave equation becomes a Poisson equation. Poisson equation just like the static electric potential. It obeys a Poisson equation, means the configuration of the field in the bulk is completely immediately determined by the special boundary condition. So there is no freedom to propagate at all. So this naive picture just explains why this theory contains or if it's built, it is written originally in terms of a skeletal theory, but it indeed does not propagate any skeleton at all. So this is my picture.
This happens only in this particular background.
There is a background design. If you consider something homogeneous background, which has this propagation. Minkowski. Yeah. Okay, so then let's take a look at the special covenant blood correspondence of this model. If you choose the unit page, just choose the special the time coordinates, you got a button like this. Okay, then you found it. Oh, it's very interesting that yes, indeed, the Lax function appears linear in the Lagrangian. So this also explains why this theory only propagates 2 degrees of freedom without the scaling mode, because this is a special case of a special covenant gravity in which the Lax function appears linear. But this condition, I mean linear in the Lax function, is just a special case. So our purpose is to find the most general condition as most as possible for the special covenant gravity to propagate no scaling mode. Of course, so after custom 10 years later, some other people just introduced the so-called minimally modified gravity. So from this name, you can understand what they want to do. So minimally modified, minimally means we just modify GR, but introduce nothing, no extra degrees of freedom beyond GR. So this is called minimal gravity. So you can see that the Lax function is linear Lagrangian. But in this form, there must be some additional conditions on this function. So I will mention the details. So there are some further extensions, the extended Aristotle, and just recently, so we just study the most general conditions in the framework of special covenant gravity in order to propagate only 2 controller degrees of freedom. So this is our result. I don't want to show the calculation, but just to show the result. So our starting point is this, let's say this is the most general metric theory respecting only special covariance. And our result is as long as this Lagrangian L obey these 2 conditions, of course these conditions are so complicated. As long as this L obey satisfy these 2 conditions, then this Lagrangian progress no scaling mode. It progress only 2 tensorial degrees of freedom. So these are the most general sufficient and necessary condition for the special covenant gravity to progress no scaling mode. And as an application, we just show quite a simple example. So this one. So this Lagrangian is dedicated clearly it's not GR. Clearly it's not GR. Of course, you can recognize some familiar building blocks like extrinsic curvature, like the special rigid scalar. Very similar to GR, but it's not GR. And it cannot be transformed to GR. It's not equivalent to GR. And any field transformation. So it's non-GR field. But it satisfies our condition. So this means this theory indeed propagates no scaling mode. It propagates only 2 tensorial degrees of freedom. And GR is a special case. And the previous proposed the Pascal theory is also another special case. So this means in our framework, although our conditions are very complicated, of course, at this moment, unfortunately, we haven't found the most general complete Lagrangian. We only find some simple examples, but they are new. They are new non-GR theories for the TTDF.
That all functions rho and that all functions or constant.
That constant. Yes, in this one, we can use it now. That constant.
Even n.
Which one?
N.
Yeah. This is beta on the rule of constant. Okay. So then recently, just because these conditions are so complicated and it seems impossible to use this condition to find complete Lagrangian. So we just choose some alternative approach to just to build the PTDOF with some auxiliary constraint. The idea is, so why it's so difficult to build a Lagrangian? Just because these conditions are derived by the Hamiltonian analysis, constraint analysis in the Hamiltonian approach. That's they are conditions on the Lagrangian. You see, we use Hamiltonian analysis to derive the conditions on the Lagrangian. So this is why it's so complicated. It's so complicated. So the idea is why we just start from the Hamiltonian itself. We just use Hamiltonian analysis to derive conditions on the Hamiltonian itself, not Lagrangian. So then a simple idea is like this. We just start from the Hamiltonian directly. We write a general Hamiltonian, very general Hamiltonian. So build up the left function, the special metric, and its conjugate momentum. And of course, the special derivative. And the idea is that in order to eliminate the extra scalar mode, we just introduce some extra constraint by hand. Because no matter in which approach, in which method you derive from these conditions, finally it just appears plus a constraint in the Hamiltonian. So we just put an extra auxiliary constraint by hand. We call it auxiliary constraint by hand. We just put it by hand. And of course, since the last function has no is an auxiliary variable, it has no conjugate momentum. So we have to put this Lagrangian multiplier plus the momentum, the conjugate momentum of the last function pi. And of course, we have to add this term. This term is nothing but the constraint associated with the spatial covariance. Because don't forget, our theory will respect the three-dimensional spatial covariance. So we must put the associated constraint of the spatial covariance. Then we have a constraint. If we don't require any extra conditions on the auxiliary constraint all the time, so we can count that. Since we have a special covariance, so the pi and I and hi are first class, but the pi and phi is the so-called second constraint associated with the pi. Okay, forget the names. So we have 8 constraints, and 6 are first class, 2 are second class. So that means if we don't require any further conditions, how many degrees of freedom? 3. This is a standard formula to count the number of degrees of freedom. We have 3. 3 just prove our previous plan that without any condition, if we write down a metric theory respecting only spatial covariance, we have 3 degrees of freedom. 2 tensorial plus 1 scalar equals degree of freedom. So, but this is nothing what we want. We want to kill the scalar mode. Kill means we have to put some extra conditions, extra requirement on the auxiliary constraint. So we have 2 choices. One choice is that the pi itself is still first class. Then we have to require this condition. You can see these conditions are so simple. It's much simpler than the conditions in the Lagrangian side, in the Lagrangian approach. Quite simple. So simple means we have the general solution. The general and concrete solution for the Hamiltonian, just like this. This is the most general Hamiltonian we can write down to satisfy this condition. Then I just pick this down. And after some counting, we can show that this Hamiltonian indeed has no scalar mode. It progress only to conform. And the other choice is the pi is itself in second class. Then also put some other different conditions requirements. Of course, they are quite simple, much simpler than the conditions in the Lagrangian side. And the finding also show that we have just 2 conservative freedom with this come to the Hamiltonian. You can see that this is the advance in the Hamiltonian approach. In the Lagrangian approach, that we have very complicated conditions. And it's difficult to write out any concrete Lagrangian. We just show some simple examples. But here, we can write down even the most general Hamiltonian to propagate only 2 conservative freedom. This is the basic idea and basic result. And finally, I recently we just generalized this idea to the case with multiple auxiliary constraint, multiple. Previously, we just consider a single auxiliary constraint, but of course we can consider some multiple, many auxiliary constraint. So here, like we have a general arbitrary Hamiltonian, and these are the constraints associated with special covariance, and we just put as many constraints as we wish, and all the types of constraint, the scalar type constraint, vector type constraint, tensor type constraint, we just put as many constraints as we like. And we just count how many constraints we wish in order to eliminate the scalar. There is a single counting like this, just keep it. The conclusion is quite simple. So just this. This means we don't need any vector or tensor constraint. And we can introduce no more than 4 scalar constraints. This is the conclusion. So because if without any constraint, we have 4 degrees of freedom, two tensor mode plus 2 scalar mode. And our purpose is to introduce some extra auxiliary constraint to remove this 2 scalar mode. So we cannot introduce any vector constraint. Otherwise, we will have maybe just one polarization mode for the Gaussian variable. Of course, this is not feasible. Or we have negative number of degrees of freedom. This is not feasible. So we have no vector constraint, but we can only introduce scalar constraint, but no more than 4. Then we can still this. We can just have this table, this list. We just exhaust all the possibilities of the number of constraints and types of constraints. We can have a multiple auxiliary constraint, scalar constraint. But if the number is less than 4, like 2 or 1, the auxiliary constraint may induce some secondary constraint. So, and finally we have a lot of constraint. And this constraint must satisfy some further conditions. Like this Poisson bracket is just a simple notation means we require that this Poisson bracket must be vanished. These are the conditions. But in any case, just the summary is just the conclusion is that we exhaust all the possibilities. All the possibilities means if you wish to write down a Hamiltonian, a general Hamiltonian, respecting only special covariance, and progress only 2 tensor mode without scalar mode, then the Hamiltonian must be one of the cases in this table. You can find a GI here, and the custom is here. The covariant extended custom is here, and the 4-dimensional Einstein cosmodynamic Lagrangian, of course, is another famous theory is here, and the linear auxiliary function is here, and some other kind of theory, Flash theory is here. So you can find that all the previously proposed theories propagating only 2 tensor modes are special cases in this table. But we also found some unknown theories. Unknown means we just prove that this theory must exist. But of course, at this moment, we haven't shown its concrete Lagrangians or the concrete conditions. But we have proven that there are indeed such kind of theories. Okay, so let me summarize this. So in this talk, the main information is possible. There are non-GR theories propagating PDI. So these theories indeed exist. There are, but of course, you have to abandon the general covariance. You have only such covariance. But as long as you accept such kind of condition, you can build many various kind of such kind of non-GR theories. And we have built or we have constructed such kind of theories in 2 approaches: Lagrangian approach and Hamiltonian approach. In the Lagrangian approach, the theory conditions are very complicated. Hamiltonian approach, the conditions are very simple, and we can write a very general Lagrangian, concrete Hamiltonian. Of course, there are some open questions. So in the Hamiltonian approach, we can write down the concrete Hamiltonian, but the Lagrangian approach, because people like Lagrangian, because it's easier to apply. So how to write down temporal function? And another question is, are all these non-GR theories, are they indeed non-GR? And are they equivalent to GR? Can we just transform the theories to GR by some theory transformation or some kind of information? And of course, they must be tested by observations. Okay, I just stop here. So thank you.
If I understand correctly, your theory in general does not satisfy Lorentz invariance.
Yes.
So if you can come back to that table,
Yes.
yeah, suppose we also impose Lorentz invariance, does that just give the exactly the Lorentz theories? And all Lorentz theories with Lorentz invariance? Can you impose this actually?
You mean if you impose the Lorentz invariance, you will get some pure sort of the theoreticity.
I'm just wondering because GR is
Yes.
class.
Yes.
They all have Lorentz symmetry.
Yes.
I just wondering about the unknown theory, they actually create the Lorentz symmetry.
I think this case is quite, there are two cases are quite great. One is this one. So this is the form is too small. There are only two first class function, no second class function. And this case, two first class function, no second class function. Because you know that first class function corresponds to training values. So in these two cases, the symmetry can enhance. The symmetry can enhance from the special symmetry to the general covariance or some other kind of symmetry. So for this one, this is just the general covariance. But for this one, we don't know. But there is some other kind of symmetry different from general covariance. But it has the same effect. Same effect means it is a very symmetry. So you can also eliminate the external. But for other kind of you can see that have non-dimension. They are second class function. Second class function just a function. No symmetry associated with it. So this means how to say, the conclusion is that in this case, the symmetry can enhance from the special covariance to general covariance. So you can see that in this case you have long event. But for this class, no. But the symmetry itself is on.
We have a concrete example on second line that break on symmetry. So we have the example breaks on symmetry. But just one point that was confidence that maybe it's ruled by fairness if it breaks on symmetry.
Yes, I think you can do this, but we have to calculate any application of like the regression or such kind of theory. So at this moment we have no such kind of calculation on the how to say the effect of the lower breaking of the kind of theory.
Okay, just a small comment, very good talk. Just a small comment, actually, in Ivan Vivo, we measured the polarization mode, not exactly the degree of freedom, because you can have multiplication of gravity that at the linear level they have only two polarization mode, but they have a set degree of freedom. But my question is the following, there is a big discussion whether theories with the same number of degrees of freedom are more or less through some transformations equivalent. So my motivation is the following: what is the motivation behind it? Your theories, in the end of the day, can answer problems that the GR cannot answer. So why you are giving theories with the same number of degrees of freedom but no GR?
Yes, that's true. The motivation of studying such kind of non-GR theories, I think that is mainly from the protection of Graphical waves. Because Graphical waves is protected and maybe we just have tensor path. Which means in the space only tensor is not.
So GR, up to the moment of observational rotation, GR is correct. So what is the motivation to be beyond GR theories to explain gravitational waves, since GR is enough to explain.
How to say? So maybe in the future we may detect some features of the fractional waves. Maybe it cannot be explained by G. So, but I mean, we didn't handle the ancestor part. I mean, fractional waves. So we must explain it. We have done any information about where is the star move on the star. Why no star move is occurring we must do it done. So this is one of the motivation. Another motivation is maybe in the future, make some features. It cannot be explained by G. And another amusing point of sectional theory is after we publish our paper and after we propose our computer Lagrange of the GDR, some people just use our Lagrange to study cosmology. But since in our model there's no scalar model, but they want to study scalar perturbation, so they have to introduce another scalar field again. So this is sometimes is unusual because
I wonder what is the quantum cutoff for the theory which you have the square root of regime rule?
oh yeah. Sorry, we have to watch this. Yeah.
I mean, that would answer to the question, what is the applicability domain?
Right.
You expect this is you not it's comparing back to routing scattering process. Would that be?
That's a good question. Because I know some people study, but I think all of them require one. The people just like describe. They study the scattering field of largest.
In that case, many different theories will give you the same result. Yes.
I think the result is the GR, this scattering field of GR is being. But the condition is requirement is but here we don't really want to. This is why we have some.
Yeah, maybe the result here.
Yeah.
Thank you, Brother. I want to ask some questions. I don't understand the motivation to create a space, create series, only describe the spatial covariance. As we know, GR describe the general covariance and it past values, experiments and observations, but specialists they only describe the spatial covariance. So they maybe make different prediction different from the general relativities. So I want to ask whether that series made the prediction or also coincide with the no experiment. Oh yeah, yes. I want to ask because we know the general relativities coincide inside is many no experiment and observation. Yeah, and but in that series the general covariance was broken, and we only describe the spatial covariance. So they make different prediction from the general relativities. So I want to ask, for the knowing experiments, does that series also coincide with that experiment?
I didn't quite get your point, sorry. So,
I'm not my point.
Just to give a general comment on the basic picture of this panel theory. So, of course, we just consider true merging theory with respect to special covariance. But such panel theory, in my mind, I always understand very fixed version of the spectrum theory. But the only requirement is the square field has relevance. It has a non-ranging expectation value. So let me take my mind. I never just think about Lorentz gradients driving theories. I always think of skeleton theory, general calling skeleton theory. That's just because of the skeleton has a background, and you just cannot find any skeletal version propagating on this background. So I'm not sure if I.
So his wording is this theory is consistent with all the tests we have about space.
Yeah.
Okay, yeah, okay.
Questions, otherwise we go.
If you break the logistic variance in the classical model, then almost surely you will produce a violation of the logistic variance of 1% if you try to quantize the theory, which means that any classical model breaking logistic variance has a little or no hope of being embedded in quantum theory. The problem.
Yeah, as I said, my explanation is I never treat sectional theory, just a metric theory, like in Lorentz written. So I just understand this generally covariant skeleton theory. But the Lagrangian is in tune such that there is no, you cannot see any skeleton okay on the like a cosmological background. So this means we must understand this as a general covariant theory, not Lorentz written. But just with some given background.
So imagine your fundamental Lagrangians are in fact could be in fact at some gauge fixed version of some.
Yeah, sure.
How about we stop discussion here and we finish all the talks in the morning session and let's send all speakers again.
Hello, hello. Hello, hello, hello. Yeah. Hello, hello. No. Consider the point. So yeah, I thought let's let it start because it's 36. So very important. So don't do anything. Okay, sure. Just yeah, so don't do it. It got shifted, but it we just play. Why is this happening?
Just active from the desktop. Don't worry.
Do you still need the email?
Yeah, maybe. Maybe I will. So you are going back? Good. We'll go back.
But I can stay here for a while. Okay. Yeah, it's news and they don't work there. So I see. What happened? I haven't seen such errors before.
Don't worry. So we just have to restart. Just play this thing.
So what if I put another PowerPoint? What happens if I want?
No, don't worry. That is the last stop. A lot of work takes time.
This is the last. Oh, actually, it's fine because you can use use this WPS for.
It's okay. It's okay. You have to press this display button. You'll change.
Okay.
Just open it.
Why this does not hide? Oh,
It will hide. It will hide automatically.
okay.
This one.
So this one's not working.
Not working. So you have to restart and
Why is this? I don't know.
don't see.
No, then we have a Zoom meeting. Yeah, so we have to test this.
So yeah. So this will put your phone.
No, the opposite of what my intuition. The opposite. Otherwise, if I use the laptop, how can I change? Just this. No,
Maybe
this. Because I'm sure I will get confused, but anyway.
So you can put this lights.
Do you think I need?
So maybe you can skip the local mic, but this is for streaming.
Ah,
So for Zoom and those
okay.
kinds of things.
Okay. I sent them my talk.
Yeah.
Do you already have it or you need that to?
I have it.
Okay.
Yeah. So,
But even this?
yeah. It's also clear. And if you don't need this mic, it's for the local speakers.
Yeah. I think quite loud. This water.
No, this is not. I think I don't know. You need water?
There is one.
Okay, fine, outside. We will show you have a very clock. Okay, so shall we begin our presentation? So the photo will be given by Leonardo Modesto, and he talked about nanograph and optics. So please.
Okay. Thank you for the invitation, especially to Alexei, which maybe they told me. So I will review something that I studied extensively, I would say, in the last 10 years or more. But this time I will mix together to I will present more or less at the same time local and non-local theory, which share many common properties. And about both, I will present several proposals. Well, actually, the proposal for unitarity one proposal for unitarity, mainly developed by Anselmi and Piva for local theories, and something that is common to the two classes of theories, which is supernormalizability or actual finiteness, depending on which action you start from. So, will be mainly a review, but there are also views spread along the presentation. Okay, so local theories. There are this couple of slides that I show here presents a large class of theories, where the first one is very famous and I would say unique. Then you can introduce higher derivative theories first throughout the action principles introduced by stability, or even more higher derivative. If you want to achieve urbanizability, then these two theories are not enough. You need to consider the theory or quadratic gravity theory, which unfortunately or fortunately depends, because there are news now on these years. Shows one dot. So here there are proposals about how to make or how to make unit, how to prove unitarity of this theory, and I will shortly review later. Not specifically for the quadratic gravity, but for some toy models. Of course, we can go beyond. If you have more derivatives still in local theories, you have you use also more degrees of freedom, in particular more cost-like freedom. But what you achieve is more about finiteness, and more about the finiteness of the loop amplitude. And this will also be probably or hopefully clear shortly, later shortly. There is also a possibility to keep only for the question, but the theory is non-normalized. Okay, this is a large, I mean, this more or less are all possible local theories you can write down, consistently with the diffeomorphism invariance, Lorentz invariance, etc. What about non-local theories? So, non-local, they must about gravity, yeah, of course. I'm talking mainly about gravity, besides some toy models when I want to tell you about unitarity or eventually removability. So, this is a simple theory for gravity, which is non-local, does not show up at least around Minkowski space-time and around any Richardson space-time other degrees of freedom beside the spin-tuned gravito. What are the ingredients present in this Lagrange? First of all, the main ingredient is the fourth factor, the exponential of Campbell H. And it's peculiar to select this class of functions which are asymptotically polynomial. I mean, if you expand for large box the exponential of H, the theory turns out to be a local theory, exactly like the one I presented a couple of slides before. This is crucial if you want to have under control the power counting organizability of it. Moreover, the corrections you get are all exponentially suppressed. Think about zeta like space square, which is to square flat space time. Therefore, if you want to study the power counting normalizability of the theory, is sufficient to look at the high energy behavior or the local behavior. It's not that trivial to prove this statement, but was done actually initially by Kudmin, and we and even recently we generalized in a paper with Gianluca Tiberio, Breno, and others. Okay, so the two main properties that we would like the theory to have are unitarity and normalizability. Okay? In analogy with what we know about the standard model of particle theories. Of course, I will only speak about perturbative quantum gravity.
not non-perturbative aspect properties in this seminar. And so let's start with unitarity in the non-local theories. Well, here it's quite simple to see that there is 3-level unitary because the propagator is exactly the same. Besides this exponential that of course does not introduce any other degree of freedom. There is an essential singularity, but no other degrees of freedom. It's not that trivial, even this, but almost trivial. But you can prove that the imaginary part of the amplitude at the level, where you know is the energy momentum tensor, is 4. Okay, this is not true if so this is 3-level unitary, but we have to go beyond. And in order to go beyond, we have to prove that at any loop order, the S matrix is unique. So you compute the bubble diagram, 2 loops, and so on. And you have to show that at any perturbative order, the amplitude is the usual S dagger S equal identity relation is satisfied. So the idea is to derive the final rules from the back integral, Laurentian, and then in any loop amplitudes, you take internal and external momenta to be Euclidean. Okay, you never take internal momenta to be Laurentian. You make your integral, and afterwards you make the analytic continuation in the external energy. Okay, that's the procedure. Okay, of course, this is not equivalent to integrate along the real axis because you have an essential singularity field. Okay, this is the way you define it, but it's consistent with S dagger S, so fine. Let's provide an example here, which is the scalar theory within 5-4, 5 interaction. The poles, as you can see, are the same of the local theory. The poles are the denominator of these two propagators. The exponentials do not introduce any pole. I find instance in the complex plane. You integrate along the imaginary axis, but when the external energy becomes real, these two poles that comes from the denominator move towards the right, and especially K4 pinches the imaginary axis. Okay, so in order to have to define the analytic continuation, you have to integrate this funny part, whose result is the integral along the imaginary axis plus the residual. And this residual gives roughly one of these two delta here, on shell delta. The other comes, this one, the other comes from the limit epsilon to 0, which is the final description, usual final description, and you get the usual discontinuity relation consistent with Katkowski rules in local theories. Okay. Let's go beyond this formal analysis and compute the real part and the imaginary part of some amplitude. For example, the previous bubble diagram with the exponential form factor. It doesn't work for gravity, but this is the model. So this behavior is the usual one when you send lambda to infinity and you recover the local theory. Why there is this kind of modification, which is crucial, you will see later is crucial in modification. But this is the result. So this is the logarithmic behavior you have in the local theory. This one is the modification. The imaginary part, as we have seen according to the Katkowski rules, is the same of the local theory. Okay. Another core factor would be this box square. For example, here is the result. Actually, in this plot, we show the two different behavior. What does matter really here is that well, this case is negative, this is positive, but goes exponentially to large values for large energy, external energy. We will see this later. We'll use this later to infer about scattering amplitudes. So in general, you can prove this relation is true at any loop order. And also anomalous thresholds are under control, unitarity, so perturbatively is fine. Okay, yeah, please.
On the problem
Not exactly, because there is this exponential, you see, which makes the integrals more convergent, right? In the simple case, it's just exponential of k squared minus k squared. Okay, so let's now come back to local theories. And the local theories are, as I told in the beginning, there are always, if you consider highly derivative local theories, ghosts, one or more. So what is the main problem with ghosts to me? I don't know if everybody here agree, everybody, even in the other presentation, have an answer to this problem different from what I have. But to me, this problem is very hard to solve. We put the only energy conservation and interactions, because the vacuum is unstable, but it's not unstable with a lifetime which is finite, 10 to minus 100 seconds. Is stable, is unstable with lifetime which is identical to zero. Thus, which means that in a scalar theory, phi equals 0 and psi equals 0 vacuum does not exist at all. And all perturbative theory does not make any sense, does not exist. Okay. So you have to solve this problem somehow, or to define the theory in order to avoid this problem, which is actually the proposal by me, especially by So, moreover, something that I hear in many seminars, this is regardless of the mass scale. So if you have a theory, you cannot say that there is a mass scale which is 10 to 100 Planck mass, and your theory is fine as an effective theory. This is wrong, completely wrong, because this instability does not fill this energy scale or the mass scale of the box. If there is a ghost, 10 to 120 GeV, right, your vacuum does not exist. That's easy to prove. It's written here. Yeah, please.
This is not the end of the story. One thing mechanics, we particle. It's a very consistent model, as you know what.
Indeed, here you need interaction.
Yeah, it's a contrast. You have no vacuum of the theory is consistent. So it means that vacuum, I mean, one energy, it's important. But the system of vacuum, quantum theory.
The vacuum for me is what is the vacuum in the scalar theory like this one? Can be any 5 zero solution of vacuum. In particular, 0 in this case. Okay, so you should have. This should be, right? Okay.
Not in quantum mechanics. Free particle. It's not normalizing what we call the vacuum.
Okay. Let's discuss later. To mathematics. Anyway, okay, so this is the problem. Let's see how we can eventually make a proposal for solving this problem. Well, this is the 6th derivative theory that, as far as maybe you will speak about later, this is a proposal for gravity. It's a subclass of the theory that is presented in the first slide. That eventually, let's have, as far as I know, we'll study more extensively in 1 hour from now. But look at that as box, okay? Because there is a box operator here, which is a local theory, which is a local operator. Therefore, the propagator has at least two extra poles. But the nice property of this kind of theory that I introduced with Ilya several years ago is that since the poles are complex conjugates, these do not give contribution to the imaginary part of the atom. Okay, they cancel each other at 3 level at least, and at 3 level the theory is unique. Okay, let's consider a toy model for such theory in which you have complex conjugate poles because this box here, okay, and then you have the propagator. Again, the main reason in the beginning at least was, and till now to say, to have more convergence. Okay, and therefore this theory is K to the 6 and not K squared. So it's more convergent than the normal scalar field theory. And when you think about gravity, this eventually make even gravity, renormalized, or supernormalized, or even so that's the main reason. What about perturbative unitarity? I said that since the poles in this class, special coupled fields are complex conjugates, then at 3 level they do not contribute to the imaginary part. What about loops? Because you have to do like perturbative loop. What we did here with the speed of mind, mainly the computation, you use exactly the same technique used for the case of non-local theories that actually you can use also for any local two-dimensional theory. And you start from the theory defined Euclidean and continue the amplitude at one loop, like in this case, from complex external energy to real external energy. What it happens is that you get this kind of path in which at any loop order, this is just one loop, the imaginary part of the complex conjugate poles do not contribute. Like a field. And this happens at any perturbative order in the loop expansion. Of course, the amplitude is not analytic, it's not an analytical continuation, and but is integrable, and the result shows one extra peak at the threshold of which is not the threshold of the ghost. The imaginary part is the same of the local theory. So let's go behind this. And this was really extensively studied by Anselmi and Viva in many papers. And they made a proposal, new proposal, beside the one we are aware about, which is the final proposal for any part. Could be a gauss, could be a normal part, but it's another prescription. And there are at least 3 versions of this, as far as I know. The one really, to me, at least simple to present is this one. First of all, the problem of instability you solve in all these theories, even the previous one, because you do not ever compute scattering amplitudes with external ghosts. And you say, well, that's easy, right? Yes, seems trivial, but what is non-trivial is the consistency of this statement and this proposal. What does it mean, consistency? It means that at any loop order, the Katkowski rules never see such propagation of ghosts in the loop. So they are not recreated, they are not contributed to they are not generated any loop order. Okay? They do not contribute to the threshold. So the proposal is short. Take your integral, like usually, with the Feynman prescription, like you are sure aware about, and you integrate the energy first. Then you apply the usual decomposition in principal value and delta of each of these 2 ratios, and you trash away in this way to see the proposal, all the delta which contain the ghost state, the ghost energy. Okay, so in the end, actually, you have these 2 contributions. You have 2 ghosts, one for each leg, internal leg, and the result is that the amplitude now has an absolute E-squared value, which, if you remember the Feynman result. Here the signature is minus plus. You have a minus with energy squared, so you have an imaginary contribution for the final amplitude. But according to this new prescription, you get absolute value square, or actually it is this kind of average of final amplitudes, which means there is no imaginary part. So this has been studied extensively in different ways, more rigorously. But that's the result in short. Okay, so you have to appreciate, maybe you do not lie, fine, the consistency. Okay, that's the main and the key point, which is not that different from what happens with the RST ghost, because if you compute an amplitude in which the RST ghost is non-zero at the beginning of the end, the amplitude is non-zero. So first, even there, you have to remove by hand the BRST ghost from the spectrum of the asymptotic state. Then why in Young's theory they do not propagate as internal state in loops? Because they cancel exactly with the longitudinal states of the Young's fields. Or if you wish, because there is gauge imbalance. Here there is no gauge imbalance, but the mechanism is very, technically happens the same. Okay, so recently we went beyond this and we consider also multiple complex conjugate poles and even higher order complex conjugate poles. Well, this is, could say, an academic exercise, maybe not really, and we'll come back on this point later, hopefully. Okay, again, the result is consistent with unitarity because these complex conjugate ghosts are cancel each other at any order. But the prescription is more general, as I said. Yeah, it works for any part. For X boson can work if you don't want to be observable. So if you have many complex conjugate poles, this is the kind of picture you should observe. You should see in an experiment. And these represent, all these people represent the presence of these ghosts. They are really ghosts. They never interact with us, but they never show up. They can interact with us. They're like portals, okay, if you wish. They can affect our life without to ever show up. Supernormalizability. So here I want to make this story short because maybe I presented it so many times. So the main idea is that in this, now I'm back again to the non-local theory in this case, but the result is applicable to also local theories because in the non-local theories I focus on this asymptotic box to some power local contribution. That's matter for the power counting. And regardless of the locality or non-local, local or non-local theory we are studying. So, easy and roughly, the power counting works like this. You have one P to some power 2 gamma plus D is notation higher power momentum, if your higher derivative has enough derivatives for any internal line. And you have the same power, unfortunately, for covariant theories for each vertices. I said unfortunately because if you use many derivatives, you can easily solve the problem of divergences from 2 loops and above, but not for n equal 1. If you take gamma or the number of derivatives large enough, this quantity can be negative and there are no divergences, but only if n is bigger than or equal to 2. For n equal to 1, you have all the same divergences you have in Einstein's theory of Stille gravity. And in 4 dimensions, you have this, in general, these contour terms. It's easy in higher derivative pure local theories to remove all these divergences beside this. This is not easy, but we did. How? We went, let's skip, beyond the theory that I just showed. And one simple way to do not have such divergences is to go in all dimensions. Because in all dimensions, there are no divergences for, there are no divergences at 1. You take the general formula and you see that n and k in our theories are integer, b over 2 is semi-integer, gamma is not. So no divergence, the theory is finite. So this theory is the whole theory at classical and quantum level, plus quantum corrections, which are finite and RMS, of course. What about 4 dimensions? In 4 dimensions, if you want to achieve finiteness, you have to have 2 extra operators, which are quartic in the curvature, or cubic, but this is what we did. This is the simplest way to achieve finiteness, because these 2 operators contribute, but only linearly in distinct coefficients, S1 and S2. So you can always find the solution of this system of the 2 beta functions for R square R mu square. By the way, this result is 1 loop exact. There are no corrections at 2 loops. So this define the theory, this computation define the theory. You will have here two coefficients, 1 over 98 pi pi, 118 pi, whatever, and that's it. The theory is fine. Okay. So what is nice to me about finiteness is conformal invariance. Why? Because it's easy to implement conformal invariance because you can always introduce the diagonal in your theory. But in this case, in this family of theories, since you have finite, the conformal invariance or wide invariance is preserved at quantum level. Okay, and if it's preserved at quantum level, I can believe in such symmetry to be, for example, broken only spontaneously, and eventually, probably not have time, solve some issues like the singularity problem in black holes, cosmology, galactic rotation curves, and other applications. Okay, the way, however, to me, till now, the best way to till now to break conformal invariance is spontaneous. Okay, scattering amplitudes. The classical scattering amplitude we debated a couple of years ago. If you consider this kind of theory without Riemann square, you don't need to use the Riemann square to have a superlinearizability of finiteness. So for this kind of theory, which is R plus operators quadratic in Ricci square, the amplitude scattering is exactly the same of the Einstein limit. There are several ways to see this. This is a stupid way, because we did the computation in the beginning, but afterwards we figure out that there is a theorem again by Anselmi, which allow you to understand this result in terms of a figure definition. We will see the slide later, you can read it. Another way is the following. Since the theory is quadratic in the Ricci square, in the Ricci tensor, all the perturbative solutions of the equations of motion are the same of Einstein-Hilbert as long as the background solves is a Ricci flat solution. And using the solution, the perturbative solution, so you can understand the scattering amplitude, which of course will be the same of Einstein-Hilbert because the solution are the same of the Einstein-Hilbert theory. Okay, something new. Usually the scattering amplitude, this is the best side of the theory. I mean, yeah, it's good because we know we don't have to do the computation. If you wish, you have the scattering amplitude the same of Einstein-Hilbert. However, you can have the problem of the unitarity bound. This is still under investigation, of course, but there are some progresses in toy models in which we show that actually it's very soft the amplitude in the ultraviolet after resolution. Okay, and okay, information is a serious business, but as long as you sum the bubbles, this is the behavior we found. So it is very soft, so gravity seems to disappear, or any theory with this kind of modification seems to have a trivial behavior in the ultraviolet. Causality, well, again, three-level causality is the same as the theory is causal because you can use this argument that you can find in a paper by Carbone and collaborators based on the three-level scattering amplitude. The three-level scattering amplitude, we know what they are the same of Einstein-Hilbert, so causality is the same of Einstein-Hilbert, so the theory is causal. Another way is to look at the Shapiro's time delay. Once again, Shapiro's time delay results is based on the three-level scattering amplitude. This three-level scattering amplitude is the same Einstein-Hilbert theory, so you have again the same time delay. So causality. The same you don't get, for example, in a theory with a Gauss-Bonnet operator in D bigger than 4. Okay. How we can make contact between gravity and standard model particle physics. So the proposal is this kind of theory that actually later, so the proposal is this action, which is not so ugly or complicated as it seems, and later will be used actually in the next talk by extensively its properties by Gianluca Calcagno. So, and an application, a very interesting application is called mode. So, what is the action? The action is the local action, I mean, LL is the Einstein, is the action of the standard model including gravity. LM is standard model particle action, Lagrangian, and this is the Einstein inverse, okay? What is E are the equations of motion you get from this action. And F is again a form factor. Before I was into the box, and before E was just R mu nu or G mu nu, the Einstein test, so it's consistent with what I presented previously. Again, quadratic in the equations of motion. So you could ask why this kind of theory? Well, because this theory preserves most of the properties of the standard model and of Einstein's theory, exactly like the non-local theory that I presented in the beginning. Again, because it's quadratic in the equations of motion or quadratic in the Einstein tensor. So, in particular, the properties are that all the solutions of Einstein equations of motion coupled to standard model are still solutions of this theory. All the three-level scattering amplitudes of the standard model including gravity are again the same in this theory. All the stability properties, that's crucial, of Einstein's theory and the standard model are the same in this theory, exactly because of this structure. So the equations for perturbations at classical level in this theory are the same that in Einstein gravity plus standard model. So, for example, Minkowski is stable at any perturbative order. It's not that trivial statement actually proved. Schwarzschild, if you are not so fundamentalist like some mathematicians, and you believe in the Regge-Wheeler result, Schwarzschild is stable also in this theory, and so on and so forth. Supernormalizability and finiteness are achieved also by this theory, and the causality is the same because of the points 1, 2. Especially for the finiteness requirement, there is actually a paper where you can find really all the details, and the key ingredient in the paper is the modification of, you remember, before the argument was box in the exponential. Now it's delta, delta is the echelon of the theory. But you have to also add here, without having more derivatives than the leading contribution in box, if you wish. Other operators, similar to R to the fourth or that I presented for the purely gravitational theory, and you are able to achieve finiteness. So again, conformal invariance, which you will use 10 minutes from now, more or less, by Gianluca in cosmology. Implications. Well, in the beginning, I told you why I present theories. So that's, I mean, maybe, well, I can even stop here if you wish, but I want to tell you something else. So there are questions here till now. Okay. Then some implications of this framework, of this class of theories, local or non-local. One new proposal, which is not yet published actually, is the confinement as a fundamental mechanism. How? Well, in the beginning I told you, when I discussed the case of the local higher derivative theories with more complex conjugate poles, etc. It's just an academic exercise, or we can also apply to something, to explain something. Well, one possibility is where this limit epsilon to 0 is tricky, but this theory should be used, and at the same time can provide a potential in the infrared, which grows with the distance. Okay. We can even in general, we can even do something more technical involved and mix together ghosts and locality and achieve again in this in the same way the confined potential. I mean, this is not very elegant, I would say, but if we are able to prove unitarity, then deserve to be considered as a proposal. Because if you have at the same time unitarity and infrared modifications, which is very difficult to achieve, infrared modifications, I mean, with confined potential, then it deserves to be studied. Okay, there are several other implications of this class of theories, like bound state in the ultraviolet regime, because in some of these theories the potential does not diverge in R equals 0, but is actually vanishes. And then you can have primordial gravitational bounds, if you wish, or non-local black holes. Here there is a lot of there are many people involved in this business. Which why? I mean, actually this was one of the initial motivation, because we would like to solve the singularity issue using no locale, and somehow it works. But what is not that good is that these solutions are all approximate solutions. Part of the result is made by hand. Okay. Why conformal invariance is so important to me, or finiteness, if you wish. So, well, this opens a new chapter. Maybe I can leave you some time for asking questions. Because I will not. Yeah. Well, how many minutes do we have? Well, so the message is the following: the theory is finite at 1 to 11, and then is while anomaly free. I can use conformal invariance to solve the singularity issue. As I said, all the solutions, all the classical solutions of Einstein theory are still solutions, especially, for example, the Schwarzschild solution, or others, if you think there are some tricky point in the definition of the source for the Schwarzschild case. Therefore, you can use, as I said, conformal invariance to take to enlarge the class of solutions and solve it. And this way you can solve the problem of the singularity, because you select or you break spontaneously your symmetry to solutions that are not singular. In other words, you can always find, the general statement is that you can always find a where is, well, I don't know. You can, I can't find anymore. Anyway, let me give you an example. You agree that if your conformal invariance is not closer at 1 to 11, you can always make a rescaling and you get another solution. Then the idea is to select a rescaling which make your space-time now singularity free. How? In which sense it's singularity free? Because it's genetically good. That's the main the key point. Although in this case, even the curvature invariants are all regular. You can ask, well, but why this kind of rescaling and you do not keep your initial singular space-time, which is still in the same gauge orbit? Well, first, because in the conformal invariant phase, you can show that singular space-time, singularity free space-time are gauge equivalent. So the statement of the singularity in a conformal invariant theory does not make sense. So there is no singularity. Okay, that's, I think we agree. Now, which kind of rescaling factor or conformal factor I take when I get out the conformal phase, or when I break spontaneously the symmetry? Well, I take one which analytically interpolates between something which is singularity free in the ultraviolet and something which is singularity free also in the infrared, right? And by analyticity, that's the right thing you have to consistently select. Okay. This is you can be generalized. I don't know where is the slide, but anyway. Okay. I mean, I can stop here, or I just want to skip to the last slide and introduce the seminar that will be next, which will be an application of actually this framework. Okay.
Okay, so is there any questions? Yeah, thank you for the talk. I was puzzled about one thing. So you make this comparison of the scattering amplitude, the non-local theory and GR, and you get the same result. Now GR is not renormalizable, and
That theory doesn't apply here, I don't know what you.
and kind of the non-local theory seems to be renormalizable, but then the amplitude still divergent. So how does it come together with unitarity and everything?
Well, first of all, I could reverse the question and say why a theory which is scattering amplitude grow with the energy shouldn't be renormalized. That's an odd paper where there is this statement. There are some some examples, but it's not applicable to this case or to this kind of this theory. Why? Because we proved. Okay, so we actually disproved with this large or infinity class of theory that that paper is really true in some. We assume something. Okay, there are some assumptions there that we are like even like locality.
But then you don't really have solved the actual problem of non-local right? Because the actual problem is the scattering amplitude that you don't really have unitarity because
you mean unitarity bound. You mean we don't solve the unitarity bound issue?
Yeah.
So first of all, renormalizability is there, no doubts, or finiteness. Your question is now what happens at the Planck energy? Okay. As I show at the Planck energy, what you have to do is to resum this amplitude. For example, what we are doing, what we did already is to resum the bubble diagrams, and then you see that the amplitude at the quantum level is not S, but is S times e to the minus e, so it's extremely soft, okay, even more than in string theory if you want to compare. So that's one possibility. Or the other possibility is not to go so far with finiteness and just take the theory as with one divergences, but super normalizable, and you achieve kind of asymptotic freedom. So, in other words, there is nothing beyond the class. Okay. Everything is free, even the causality evaluation, which is, I mean, what I show here is causality evaluation. There is no causality evaluation or micro causality evaluation. Micro should be there, is there, easy to see, at the scale of locality. But when you achieve such scale, your particles do not interact anymore. So how you can test a causality evaluation if you cannot detect anything? Okay. That's the reason how. Thank you for the question.
Leonardo, thanks for the nice talk. So, well, mostly about similarity. I mean, if we have full quantum theory, consistent quantum gravity, then we don't have to care about classical singularity. Then why do you insist on conformal symmetry? The theory is finite, quantum gravity, good theory, then quantum theory takes care of singularity, so you don't have to worry about classical.
Because, at least in my opinion, this is a good theory, this is finite, this is for me quantum gravity, but there are singularity. So classically, and from well, then we should prove that all the quantum corrections somehow conspire, like this kind of behavior of scattering quantum, conspire in making everything smooth, but there's not element that control it at the moment. So what I'm very conservative. I said in the worst case, I conform my bias if you wish, right?
You want to see every now and then.
So I mean, I can claim about what I learned to compute, right? And the quantum interaction is very hard.
Okay, so the second speaker. Okay, so now let's look at our next talk. So the next talk speaker is Gianluca Cartesian, and he will give a talk on the type of non-local quantum gravity in the Florey universe. With question weights.
Can I put this here or it must be near to the
Yeah.
Yeah, okay. Okay, first of all, I would like to thank organizers for the invitation here. This is basically a natural continuation of Leonardo's talk, but more oriented to phenomenology. So here, the purpose is not to build a model to do phenomenology, but to extract the phenomenology from something we already had for different purposes. And I will concentrate mainly on primordial gravitational waves. Nowadays, it's clear that multi-messenger astronomy, and in particular gravitational waves, can say a lot, not only about the nature of astrophysical objects, but also about the fundamentals of gravity. So far, Einstein's gravity has been tested to tremendous precision, and it will be even more so in the future. For instance, in a third generation observatory like LISA, we expect to constrain the stochastic gravitational wave background to a high precision. These are results which should appear next week from in the LISA collaboration about a single power law or a broken power law shape of a stochastic background that could be observed at within the LISA sensitivity window. The nature of this type of signal, however, is far from clear, and in fact there is a lot of speculation on what could produce something observable in LISA and in other experiments. But if you look at how many models embedded in quantum gravity, or even slightly motivated, slightly inspired by quantum gravity or string theory, could be able to predict a tensor signal of such amplitude, then there are not many choices. In fact, there is one is the pre-event cosmology that can reach the LISA and the Einstein telescope sensitivity window, and actually also PTA, but this would be trumped completely by the observed signal. While many other models, no matter how much robust they are, they anyway cannot reach, cannot go beyond the decimal range. So since it's a long time in the future to go for decimal, has not been approved yet. One may think that it's really difficult to try to test quantum gravity with gravitational wave astronomy. However, here in this talk, I will give an example of a model which is actually this black curve, which, like many others, yes, cannot do better than going beyond the cycle, but the key point will be that it predicts a large tensor to scalar ratio. And this is not just about the predictiveness of a theory, but about the falsifiability, because this prediction can be falsified in a time span of a few years. Now, there are many proposals on quantum gravity. Some are perturbative, some are non-perturbative, but they have in common the fact that it's difficult to extract observable predictions, and it's even more difficult that these predictions can be falsified. Non-local quantum gravity, as Leonardo presented in the previous talk, is able to generate a falsifiable prediction when matter is coupled non-minimally to gravity. So one possible motivation for non-local quantum gravity, maybe I'll go faster because Leonardo already said a lot about it, originally was for some to cure the unitarity problem in local quadratic gravity. It can be done in different ways. You are not forced to introduce a locality, but anyway, it's one possibility. And so the first versions of non-local quantum gravity did precisely that. So they just added as an extra ingredient these non-local quantum factors in essentially a quadratic action. And there are several versions to do that with or without the Riemann term, which is important also for classical solutions. With or without killer operators, with those local operators Leonardo talked about that can make all the data functions vanish. And with or without an extra mass scale, which would allow actually to embed Starobinsky inflation in this type of this class of theory. Okay, this is just a brief summary. What we know about this class of theories, there is evidence in favor of the well-definedness of a theory as a perturbative candidate to quantize gravity. We have a path integral. At a classical level, we can have a well-defined problem of initial conditions. The number of physical degrees of freedom is finite. The theory is power counting super renormalizable, and I want to add this is sufficient to claim renormalizability because the theory is also BPHZ renormalizable. So this means that you don't lose subdivergences on the way, and the power counting argument really gives an upper bound of the type of divergences you can find in the theory. This is, I think, this is a detail that is important to mention. Leonardo already talked about the unitarity and the singularity problem. Well, in the case of the Big Bang, that has been studied already a long time ago, also in string-like models with no locality, and we will go back to this later. And about the Black hole singularities, well, it depends on whether you have or you don't have a Riemann operator. But here, so we take it here basically is that in some versions of the theory, no locality is the ingredient which smears the singularity, but in other versions of the theory, this ingredient must be conformal invariance, and no locality is not sufficient. However, okay, so apart from these explorations, which are not complete, one problem could be that here matter is introduced by hand, so you don't really unify the forces, and also it is difficult to extract falsifiable predictions because the argument goes like if you do new physics at the Planck scale, you will get effects at the Planck scale. And this is unfortunately is not completely true. So let's consider the non-minimal version, which you already saw, which is basically made by the addition, apart from the Einstein reduction, of the terms which are quadratic in the extremals. So these EI are basically EI equal to 0 would be the local equations of motion, and then with some form factor here, which we take in this talk to be an asymptotically polynomial operator. Okay. So in the case in the gravitational sector, extremals would be basically the left hand side of well, would be the Einstein equations, but the full non-local equations of motion are of course much more complicated. In fact, the theory not only has the solutions of Einstein gravity, but also other non-local solutions. So the space of solutions of the theory is larger than that of Einstein gravity. But we also have the usual solution. Any theory can be made classically conformal invariant by theory definition. The point here is that that would be a trivial operation. But since at the quantum level you preserve conformal symmetry, then
this operation is non-trivial. In fact, we will heavily use conformal invariance to build the cosmology of this model. So this nominal version has the same characteristic as the other versions of this class of theories. Plus, it gives a testable cosmology. Yes.
Finding the conformal transformation are not the same.
Now, here by conformal, I mean you can call it the scaling transformation or Weil transformation. Yeah. In that sense, that is what I mean by conformal invariance. Equal to Weil, equal to scale. Okay. Yeah, I know there is some ambiguity in the terminology. Yes. Okay. So basically, we can identify two phases. In one phase, conformal or Weil invariance is manifest, is preserved, and this happens at energies comparable with Planck energy, while at slightly lower energies, there is spontaneous breaking of the symmetry. And one can actually identify a regime which is still close to the Planck scale, but one order of magnitude smaller, where the intermediate term of this polynomial dominates over the UV and the constant, if you have any. And here the theory gets a local limit of a quadratic type. So in the Transplanar conformal phase, basically you don't even have gravity because all correlation functions of non-conformal fields are identically zero. So this is it's very simple to show. You can find it in this book by Di Francesco. Here if you want to do cosmology compute, for instance, your spectra, you will find zero exact scaling values. You do have quantum corrections, of course, but they do not affect the propagators in this phase because they are always a higher order, either in the graviton or in the combination of the graviton and the dilaton. At slightly smaller energies, where here lambda star is the scale fundamental energy scale appearing in your form factors, but above a certain scale, which we call lambda higher derivative HD, which is proportional to lambda star, where B is remember is the coefficient of this intermediate term. Here you have the breaking of a symmetry. The dilaton takes an expectation value, but we know it to be the Newton's constant or the Planck mass, and you break spontaneously the symmetry. How to do that? There are several ways. One is just to add cosmological constant in the local action, and remember that by local action I mean the leading term here in the action, and that will also have repercussions on how you would define the externals E. So if you have the cosmological constant there, and you make your field redefinition by dilatory scaling, then you naturally add a particle potential with global minima. A more elegant way was actually proposed by Lars Turok and collaborators a few years ago, which is to introduce a Higgs dilaton potential, which still preserves Weil invariance, and basically the expectation value of the Higgs would determine the expectation value of the dilaton and vice versa. So this doesn't break explicitly the symmetry, but allows for a spontaneous breaking mechanism. So in this post-Planckian phase, the action, the non-local action, reduces to quadratic one plus quantum correction. So the quadratic part is basically the square of extremals, which is a sort of overconstrained version of stellar gravity, because
the coefficients of R mono squared and R squared terms is not arbitrary, is fixed, and actually in 4 dimensions you have only the R mono term. And then you have quantum corrections where these coefficients beta are not beta functions, they're just numbers, which are finite numbers which can be calculated. So in this case, quantum correction in this phase, quantum corrections do affect the 2-point correlation function, and in fact they are responsible for the deviation from scaling variance of phase modulus. So we have so let us explore the consequences of having these 2 phases in the early universe. The first consequence is that you are able to address the classic problems of the hot Big Bang model without the need of introducing a phase of accelerated expansion. The second consequence is that you can also produce primordial perturbations, but not since you don't have inflation in this case, you need to use you basically need to produce scalar perturbations as thermal fluctuations. And the third consequence is that these spectra are so rigid in their shape that the prediction ensuing from them, which is a larger tensor to scalar ratio, cannot really be modified as much as you like, and will be observable by bicep array within 4 years. It can be tested, and by Lightbird in the further future. So let's see why all of this is possible. It is thanks to conformal invariance. It is not a new idea to use this symmetry as an alternative to inflation. In fact, there are several papers where this was proposed first, but it was always in terms as a generic mechanism, not clearly embedded in a top-down setting. Here, we believe we provide a complete setting with all its limitations and drawbacks, but at least it's an attempt, with the bonus of having a prediction which is actually characteristic and differentiates from both of these phenomenological models. So at the end of a conformal phase, conformal invariance, it is not difficult to show that conformal invariance basically forces your background to be either Minkowski or flat Friedmann-Robinson-Walker. One can show this in 3 logical steps that gradually reduce the infinite possibilities of a metric. One can start with a widely inhomogeneous and isotropic metric, of course, but in the conformal phase, this will be eventually be homogenized, isotropized, and made flat just by pure symmetry arguments. So the bottom line is that at the beginning of a Higgs phase, the universe should be very close to flat FRW. Or Minkowski, the mathematical error that is still a possibility. What happened for the Big Bang problem? Well, the singularity is not that it is solved, but it ceases to make sense. And I like to, in terms of, instead of finding a specific solution which are non singular, I prefer to think about the problem in general terms by appealing to the Bordeaux-Vilenkin theorem, which to date is the strongest result, strongest and most general result we have about the Big Bang singularity, which says that if the universe expanded in average in the past, then it must be geodesically incomplete. Okay, so this is independently of the theory you have. Here, you violate the hypothesis of the theorem because this statement of the theorem is not a conformal invariant statement. So in the conformal phase,
if you have a contracting background, you can always make a conformal transformation, making it expanding and vice versa. Or if you have a singular background, you can make it regular still by the same mechanism. So you can see that in the example of a FRW background. This is much more generic, and it works because the dilaton decouples from the geodesic equation of massive particles. So it is easy to see geodesic completeness in this case. Well, the horizon problem is dispensed with by noting that since you have a conformal phase, you cannot really talk about physical distances because the short is large and the large is short. You do not even have a meaning of horizon. So basically, you have everything is in causal contact. And when you break conformal symmetry, this is not a trivial finding, but we found that at the breaking of conformal symmetry, when you smoothly connect with FRW, the horizon appears but at distances larger than the horizon in Einstein's theory, which means basically that even scales much larger than the GR horizon at those epochs were still thermalized with respect to those inside the horizon. So again, this is actually like the previous point is actually independent of the underlying theory. It's just based on symmetry arguments. So you don't need the details of action, but here the point is that we try to guarantee the mechanism by having finiteness at the quantum levels. In fact, the first referee who reviewed this paper said, "Yeah, I don't believe that it's finite." So it took 1 year for us to publish the GHED paper showing that in fact it is. And then everybody was happy. So the flatness problem is solved because in the conformal theory, the FRW metrics are with different extrinsic curvature are physically equivalent. They're not just conformally equivalent, but also physically equivalent. And in particular, selecting the k equal to 0 metric is something similar to having no longitudinal polarization for the photon because of gauge symmetry. Anyway, let's go now to perturbations, which is the most interesting part, in my opinion. To calculate the spectrum, we make 2 assumptions, which are necessary to have self-consistent calculations. We do not want to deviate from perturbation theory. We are not working in a non-perturbative framework, so we wanted to make sure that quantum corrections do not dominate with respect to the classical part. And this happens only in a narrow range of energies, which are lower than the fundamental scale, which I haven't specified yet, but eventually you can put lambda star equal to be the Planck mass. And they are larger, slightly larger than this emergent scale. So basically we are working in the regime where the action can be approximated by R squared plus quantum corrections. And in particular, it's not even a range, it's very close to 1/10 of lambda star. So basically this fixes the energy scale at which we are working. So under these assumptions, basically one can neglect the curvature of the background and calculate the 2-point correlation function of a graviton. So we start with the tensor spectrum, which is generated just by the quantum fluctuations of a graviton, and the final result is the following. So the tensor spectrum is with using a conventional normalization notations. Is a power law where the tensor spectral tilt is depends on the a constant beta appearing in front of R squared of the sorry, the R squared term. Depends also on the coefficient b inside the polynomial in the form factor. Gamma is the Euler-Mascheroni constant, so it's a non thing. And then on the ratio of lambda star over the Planck mass. This thing is positive. So the first prediction is that the tensor tilt, the tensor index is a blue tilted. You have a spectrum which grows with the frequency. Okay. So it depends on several free parameters. Let's keep this in mind and move on. The scalar perturbations are generated by from thermal fluctuations, which are induced by the gravitational fluctuation. So this is a mechanism which has been used in several models, string gas cosmology, the periodic universe, and many others. Anyway, we did the same here, and we found the scalar spectrum, which again depends on the parameters of a theory, and it is red tilted. Okay, this is a good news because we know that the spectrum observed at CMB scales is red tilted, and now let's see how much. But the interesting thing is that if you take the ratio of the two spectra and you calculate the tensor to scalar ratio, then you see that well, you can write it down in terms of just the spectral index, and the inverse, and L star is just the inverse of lambda star. Is 1 over lambda star is we just re-expressed the fundamental scale, energy scale as a length scale. Doesn't matter, but it depends on that in this way. And you see the disappearance of the coefficients beta and b, which means that you can only, if you know what the spectral index, scalar index is, then this number is only determined by the fundamental scale of the theory. And the other result is that the tensor spectral indices are actually related by this mysterious relation. I say mysterious because it's not the first time it appears in the literature. It happens whenever you have production of scalar perturbations by thermal fluctuations. We tried to understand why, if there is a general way to understand this. Personally, I couldn't. So, but it's something that it's also in complete independent scenarios. It's the same. They find the same frequency relation. So whenever you have a red tilted tensor spectral scalar index, sorry, you will have a blue tilted tensor. Okay. I say something brief about the parameter space because. Although the tensor to scalar ratio does not feature the parameter beta Ricci, it appears as in another observer, which is the scalar amplitude, to mention one. And since we know what this is at CMB scales, at the pivot scale of the Planck or W map, then we understand that to get the number we see, then we need a very large beta, and there are ways to explain this large value. One is to add many fields and actually to make this theory something closer to a supersymmetric one, because when we have many fields, you naturally produce a large beta coefficient in front of the logarithmic quantum corrections. Another way is to use conformal invariance to rescale basically the spectra, which is something that of course would not change the tensor to scalar ratio, but would produce order 1 beta. So we are out of the need of any fine tuning. This is something. This is really an open issue how to because we have not computed the beta in the theory. We know it's a number, it's there, but we have not computed it, so it's some open thing to understand what is its value and how to make it compatible with observation. But well, if you just plug the values of the observable, which we know, then we can determine uniquely the times autoscaleration, and in particular, we find that it must be between 0.009 and 0.011 within the specified range of energies which we needed to make all calculations self-consistent. In particular, in the worst case scenario where the fundamental scale is the Planck scale, then the test autoscaleration gets this number, which is 3 times larger than the test autoscaleration predicted by Starobinsky inflation. And it is, as you can see, there is a lower bound here. It's not just it's not a range of values. It's really very narrow, and you have a lower bound. And so the consequence is that it's within reach by bicep array, which is the merger of bicep 3 and the cake array, which they finished installing, and by 2027 we reach an uncertainty of 0.003, which means that any signal with test autoscalar ratio above 0.006 will be detected. So if they don't find anything, it means that they will exclude this model. You cannot change, if you try to change the assumptions of this model to the calculations leading to the cosmological spectra, you find out that you cannot do that easily, and in fact it would spoil all the construction. So it's really a way to falsify the theory. If a bicep doesn't observe, bicep array doesn't observe anything, then you cannot trust this model any longer as an empirical model. Lightbird will do much better, but we'll have to wait another decade to see it. So this is still an interesting possibility, but the focus should be actually on bicep array, which is really in a very reasonable time span. Since the tensor spectrum is blue tilted, it also generates a gravitational wave background larger than the standard inflation, which will reach the SIGO, and that's the importance of this is that if something were detected by bicep array, then this would be a cross test able to discriminate between this model and other inflationary models with a high tensor autoscaleration. So nowadays, it's not realistic to test the theories or just gravitational wave astronomy with one set of observations. You always need to cross-correlate with different observatories. That's a across different frequencies. That's absolutely. I think it is the standard. It is the standard of experimental community, but should also be the standard of theoreticians, because otherwise you have a lot of degeneracy in your space of model. So to conclude, we get unique predictions for in the tensor sector at the CMB scales, and we have very few free parameters. One could actually argue that in fact it boils down to one. So we can say that this would be a genuine evidence of a perturbative proposal of quantum gravity, because it's not just a prediction, but it's a falsifiable prediction. And fortunately for us, it is imminent. We don't have to wait generations to see the result. So if it fails, the theory would need an inflationary phase, for instance, and in my opinion, it would be much less appealing because you would have to introduce ingredients. The theory was not born to embed inflation, but of course we would like to have it explained as much as possible. A third test, independent test, would be about non-Gaussianity, because there is
there are reasons to believe that the Lagrange Gaussianity of a theory would be larger than the inflationary one, but still within the observational uncertainty. And this is by all the results using conformal symmetry as an alternative to inflation, but we have not calculated the 3-point function of the graviton. So it's a difficult problem, but it's something that we would certainly like to do in the future. And I already mentioned the open point about investigating the parameter beta, and I haven't said anything about cosmological tension, so because so far we have not explored. Thank you very much.
Okay, the question, so come on.
I think, as you said, in the initial motivation for numerical gravity, stellar gravity, which can automatically come to disturbance in inflation with the spectrum. So it is much more natural to have inflation in this period. Of course, you showed other possibility, and agree with that. We related to the last comment you made, inflation will be less appealing, but in this period, disturbance inflation is actually more appealing.
I think it is not just because it doesn't produce a relative gravitational wave background, which is the case, but if you want Stravinsky inflation, you have to add an extra master term, which would change your form factors, which should be tailored to be to preserve to give a stable theory in your cosmological background. But then the question is, then you can choose different backgrounds, and then you have to modify your form factors. So I'm not in terms of largeness or parameter space and the problem of unitarity. I'm not sure how appealing really is having inflation in this model, but of course, yeah, that's the first thing has been explored because it was the most natural thing to think about. Anyway, let's see. It's just a matter of waiting 3 years. You may not like the model, but the observation will be there for everybody.
Okay, is there any question? Okay, so there's no the same speaker again. Thank you. Okay, so let's go to the third part of the session. The third speaker will be Professor Redwall, and he will talk about the power of UV planet into the 6th derivative project series. Okay, please.
Hello, good afternoon. First, I want to thank the organizers for nice invitation to participate in this conference and also for the support. Delegation all the way from Brazil. So you see here people gather, and not only from Europe, not only from Asia, but also from South America. I think maybe I'm the only representative of this part of the conference. So it shows very nice thing because it's a global meeting and it's very nice to meet with people and discuss interesting topics about quantum gravitational theories, non-locality, unitarity, and all these things. It's all very nice. And so I want to show you today the work I have been doing with Leonardo, who's here, and with Gianluca, and 2 other Russian collaborators. They are from Brazil. Unfortunately, Ilya couldn't come, but you see his picture, and there's also Alexander Pichu, he's also in different university in Brasilia. Ilya is in the same university that I am in Juiz de Fora. So today I will tell you something about UV finite and also something about 6th derivative gravitational field, because we will see that in very similar to what Leonardo was presenting, the situation in the general case is nice, but it's also good to have some first example very direct, and you see that in this first example of 6 derivatives, the things are not so easy, but still we can compute and we can tell the final answer to this kind of question. So here you have the references, and most important, they are taught. So you see, they are real people. It's not that we are using computers, but they are real people who make articles and do something in business. So let me just remind you what is the calculation, and this was also yesterday many times repeated in the talk by Alberto. Today you also saw in the morning by Slava, and of course Leonardo and Gianluca. This topic is very repetitive in a sense. It was started already something like 7 years ago when there was the first paper by Utiama and DeWitt. And of course here people tell that, yeah, okay, quantum gravity is a very ambitious thing, so maybe let's start with something less ambitious and be more directed by the phenomenology. So we know that there is standard matter theory, which is a quantum one. This is an undeniable fact. And then we know that there is also cosmology, which is used with classical equations based on Einstein gravity. And the first thing is we can try to put the things together. And the content of the paper and also all the others which were followed up by Utiama and DeWitt was this situation, and what you discover is that inevitably if you put this theory of quantum fields in a curved spacetime, you generate R squared and C squared divergences, which are the 4 derivatives, and this is a speciality of 4 dimensions, and there's 4 derivatives of the background method. So this is also the same thing that we had yesterday. So higher derivatives are inevitable if you want to speak about quantum gravity. So the formulas you have already seen yesterday and today. So I don't have to tell much about the first proposal of Kellogg from 77. Let me just put maybe a word on a proposal which was put 30 years ago, so already a lot of time, by Azori, Lopez, and Shapiro. And this is the theory which slightly generalized in the sense you add more higher derivatives, not just 4. Try to do something with 6 or arbitrary number. Actually, here is this. Sorry, it's this capital N, which tells you what's the summation index. And you see you have the structure which repeats a bit the one that was here in front of, instead of R squared, we have now insertion of box to the arbitrary power, and you take arbitrary coefficient, you sum up to capital N, and the same you do with Wright tensor. So here I use a very schematic notation with Ricci scalars, and with Wright tensor, I don't want to write in this because it's automatic. So these are the terms which are quadratic, and then I can show you that of course we don't have anything else to the level of quadratic in curvature, but what is important is that there are also higher terms in curvature, and this Lagrangian, or this actual action, you can view as an expansion in curvature. So here you will think, most of the time for this talk, you will think about expansion in the number of powers of curvature. So this is the leading thing if you want to speak something about quantum gravity, not expansion in derivatives, not expansion in coupling, but expansion in the number of curvatures that we have. So one of the particular examples that I will show you today will be either take n to infinity, and that's what was introduced by Leonardo and Gianluca, or we can take on the other extreme, not n equals 0 because it's a stellar theory, but n equal 1. And then we'll see what happens in C derivatives. And I will tell you slightly a bit more complicated situation, but still interesting. And actually, if you remember the result of the stellar theory about the one nuclear divergent part of the action, I will show you that first you can try to cook up some explanation why the result is as it is. But second, the results in 6 derivative gravity will be simpler. So you can find something that as a theoretical laboratory looks easier, and then maybe thanks to this, you can understand something about the beta functions in stellar theory. So let me go there. And first case n equal infinity. So we start with the extreme one. So what we get instead of sums, now we get from factors. So this is the one between the Ricci scalars and the other between Wright tensors. And these are the functions of the covariant GR covariant box operator. Already Leonardo and Gianluca they introduced a lot of properties. So let me just repeat that we can have to this level of quadratic order in curvatures, This is the most general theory, describes gravity propagation around flat spacetime. All the other terms which are neglected here, they are cube, they do not influence propagators around flat spacetime. This is weakly non-local, and then Leonardo talked a lot about unitarity. We know that also the propagators improve, because now if there is a very specific behavior in the asymptotic limit of these two form factors, then we know that the propagation of gravitational modes is suppressed, and then we expect that this would help to solve the problem with divergence. The spectrum, we know also from the consideration that Leonardo showed us, I can say this also applies to a very small modification to what happens on maximal symmetric background. You just have to shift the Ricci scalar to background value. All the other tensors basically, if you use a specific basis that I will show you, they will not have any additional contributions. And then what will be the most important theme of my talk today is what is the control of the UV divergences that we could have in this sphere. So let me remind you that the words that were said by the very famous physicist Wolfgang Pauli, when people came to him and said, look, we have a very good, nice theory of quantum electrodynamics, it's a quantum theory, there is only one problem. You know, it gives divergent prediction. So Pauli said, how can it? How can it? Because of course, everything what you measure about quantum theory is finite. All the observables have finite values. So how you can deal with this thing which is infinite? So of course, thanks to the development of quantum theory, we know what is normalization. But generally, this is the problem. How possible that you can have infinities while all the experimental results are finite? And here I want to study this problem and try to find solution. What to do with divergence, specifically with the UV divergence. So we will go, and already this was said, so I will not have to be very detailed. I will say something about normalizable, supernormalizable, how finally get UV fine. The key point here is to take the very specific form of the propagator in asymptotic limit. So limit for when the polynomial, when the argument of the polynomial goes to infinity, and let's assume that there is here some exponent gamma, and you can follow what was done by Leonardo in his talk about the normalizability. Here are some details about the power counting. So we know how is the scaling of the propagator. We know also how is the scaling of the vertex in and the inverse of the propagator in this theory. And gravity is very special. It's more simple than Yang-Mills. In Yang-Mills, you have to play with the number of dimension of the vector field, which is dimension of energy. You can choose some choice. You can make some choice in which the graviton field is dimensionless. That's why these two things, they are equal to each other. And then the result for the superficial degree of divergence is very simple. And L denotes here the number of loops. So what you get after this very simple algebra is the following inequality for the bound on delta that applies for arbitrary value of gamma and arbitrary value number of loops that you are trying to do your quantum theory are computing loop integrals. And this is the exponent delta, which stays on a arbitrary internal momenta. So when you have to integrate over this momenta. And you know, when delta is positive or zero, we have a problem because we have divergences. When delta is negative, divergences are gone. So what we can do with this formula? We can choose some particular value of gamma, and then, as Leonardo said, only one loop will be problematic. Higher loops, they will give delta negative, means no divergences, they are finite contributions, but not divergent. Let's choose gamma equal or bigger than 3. Then we are sure that the problem is only at one loop, and we can choose particular example just to be definite, so we can see how the things go on. So we can choose form factor, let's say the same between Ricci scalars and y, and it has this form to reproduce correctly the infrared behavior with Einstein-Hilbert. But what is important is some special function which is here that if you follow Leonardo's talk, it was the anti-function, and if you use the mathematical thing with the gamma incomplete functions, you can show that this is a very particular one. Why?
because it's entire function on a complex plane, but it has more special behavior than the near real line that you have on a complex plane. Near real line, it behaves like a polynomial, but everywhere else is not a polynomial. So it's important what happens in the real line, because when we do integral, we want the, for example, variable of the integral to be originally real. Later with the form like Leonardo showed different contours, but originally for the definition, the variable of the integration is real. So we want to know how's the behavior of the real line. Also, it was mentioned that unfortunately this kind of functions they develop also essential singularity, so we have to see what happens at the complex infinity. But around the real line, which is important for the integration, the function behaves like a polynomial, and here it's with this particular construction, you have a particular way how to see how to build the function, and these arbitrary polynomial that we see in this asymptotic. So this is a particular example, but of course, for example, I remember Gianluca showed the general formula that you integrate the general function H. This is more specific here, but let's just stick to this one example. Shows you that the idea is to have some function which is analytic and then on a complex plane, but around the real line, it boils down to something which is more simple than just analytic function in the expansion. It's a polynomial. Polynomial that you can have finite degree and d. So this is the example just to keep something in mind. Shouldn't be very complicated. And now let's try to address this problem. How we can constrain the divergence, because this is the biggest problem. Like Pauli said, how possible that you can have something infinite? It was so beautiful here. We put quantum mechanics and relativity together, but the result is infinite. So try to put more control over the divergence. We start with more, and we will see what's here. So first, you know that from the bound to the delta, the divergence only appears one loop. And then we have this theorem due to Weinberg, and Weinberg says that here all the divergences, if you have a gauge symmetry in your field, they have to be written in a gauge covariant form. So let's write everything what we can, but also this formula that was on the previous slide showed us that the most likely situation, what will happen is that this delta can be equal 4. The 4 as an exponent then means that we could have in a worst situation 4 powers of momenta in a term that should be covariant, and according to Weinberg theorem should take into account all the divergent contributions. So let's try to write some terms. We know that generally covariant terms has infinite of them, but now we want to write only those that have 4 derivatives. So there are only few, and as Leonardo showed us, they are just this 4, and they use particular, maybe different way of writing them. But you will see using the trace-free tensors, it will be easier. So that's why I started using here the y tensor is for the Gauss-Bonnet, and this one is a bracket because it's just for derivative. So let's go and say how we can achieve something more here. We have this property of supernormalizability, meaning it's not that just theory is normalizable. The only last moment in which we have divergences is at 1, at 2, everything is finite, and if you go to higher, also there are no divergent contributions. This is everything because we have chosen particular value of gamma. Doesn't have to be very high, just that you can, for this model has to be bigger than 3. At the end, I will show you also something about 6 derivatives. So then it will be completely small value of gamma. So let's go and let's try to say something about additional steps that we have to get full control, and for this we have various options. For example, Kuzmi in the paper 89 chooses a very specific combination and also very particular value of the exponent gamma. We don't have to follow this. We can try to look for the fixed point using the, for example, functional normalization group approach, but I will show you something else today. And this was the idea that also Leonardo showed. We can add additional operators that are quadratic in number of curvatures. This is the expansion. We expand the number of curvatures, and they are written here in this basis that I said we use the base 3 objects. So Ricci scalar we cannot make case 3, but Ricci tensor we do, and this is the F tensor. And if we try this operation with Riemann tensor, what we get is a Y. So let's use this R squared, H squared, and C squared. That is not anything with heat strength, it's just place Ricci tensor. And then
Yeah, the previous slide, the Kuzmin relation.
the previous one.
The Kuzmin relation which mentioned. Can it cancel by 2 or there is a mistake? Yes.
I think I took from this the
4, 2, and 4, yes?
yes, I took
And there is
this.
difficulty to cancel by 2 here, or what?
Okay, I just thought what I think people, there was this paper which was translated to the Soviet.
Okay, but.
I didn't have access to the Russian version,
Yeah.
sorry.
But anyway, it's not going to. Okay, great.
Yes. So let's come back here and use R squared, C squared, and F squared. And if we put this additional, if we use this additional 4 operators that are built very much the same with R squared, C squared, and F squared, we have now certainty that the matrix which appear for the structure of the function is non-degenerate and diagonal. This is because of the trace-free property, and of course, if something is trace-free, you do whatever traces at one loop, you cannot generate a trace because it's trace. So, for example, C squared only will contribute to C squared, and F squared will only contribute to F squared, and at the end, R squared is a scalar, so the R has to preserve. So these are the conditions that you have to satisfy, and if you want beta equals 0 for all the couplings that you have here, so you have 4 couplings, you have to solve for the 4 unknown coefficients, but these are not running because there is no anything proportional to them in the divergent part of the effective action. So the solution of this algebraic system, when the matrix is non-degenerate, always exists. So let's do further and see the second part of my talk, when I will tell you something about example when we don't use higher value of gamma, like 3 or 4, when we have naturally supernormalizability at 1 loop. We will say something about the situation with the 6th derivative theory. So here the situation doesn't stop at 1 loop, we have also higher, but this model we can use as a theoretical laboratory because you will see the expressions, they will be simpler than what we can get in a stellar theory, for example, for the results about the divergence. And in this way, you can also try to say something about original stellar result. So we will get here the final results for the beta functions. And from the point of view that was also discussed before, this is a particular model that we can study more about unitarity. And there was a paper, of course, by Leonardo and Ilya about the possibility of having Libby pair, or we can use the uncertainty prescription there. And this is the topic of the previous talk, so I will not repeat these things about unitarity. It's a higher derivative model, so of course we have to be careful. It's not like that. It's not the same like it was in non-local gravity. Now we have higher derivative, so its problem is there, but then maybe there's a lot of solutions on the market, so you have to choose. Let me just tell you about another property that we have here, and you can prove it exactly mathematically, that you have the expressions for the unidivergences that doesn't depend on your choice of the gauge fixing parameter, doesn't depend on the choice of your scheme. For example, how you do this doesn't depend on a gauge, and this is something that is very nice and is related to this fact of the supernormalizability of this theory. And one of the things that I will show at the end is to show that if you take operators which are cubic in curvature, naturally you can also have unifiedness, although conditions for that are more complicated.
Sorry, Lester. How many derivatives do you need to reproduce the unit of gravity
if you want the supernormalizability, yes, but here you can try to do something with 6, but it's the situation will be complicated, but still there is a solution. Okay, we will see actually what are the accessible parameter range. Yeah? So let me start with some actions that we speak about here about 6 derivative here. So in general, we could have this Y tensor with box in the middle, Ricci scalar with box in the middle. There will be also other operators cubic that I will write later, but for the moment, the minimum here we can forget if you just work with the order quadratic, and then Y squared R squared delta n, which is a part derivative, so so the action doesn't contribute to anything perturbatively, and then Einstein then went cosmological constant. And already here, let me define a thing which will be very crucial, and there will be the discussion about the possible parameter range, the ratio of the field. It's important for perspective, for example, all the things about the ghosts and the presence of additional modes. You know, if you know what's the ratio between this coupling omega C, so the one which is the most dominant of 6 derivative over omega. So this is the dimensionless ratio. That's why I call it this calligraphic X. And we can repeat the same thing about supernormalizability. Now we know gamma is equal to the exponent here is equal to 3. So we have scaling like that, and the formula for the bound on delta we have here. And you see, generally the situation is a bit worse because you think that you should have analyzed the situation up to loop level 4, but you will see that because you also look at what's here, there is this 4. This brings us some kind of hierarchy of the beta function, also hierarchy of the contribution to the beta function. So let me show you this slide about the structure of divergences. So this is the same repetition, that because we are in 4 dimensions, there's only 5 possible structures with y squared, which is squared, Gauss-Bonnet, which is scalar, or cosmological constant. And we know that divergences which have already 4 derivatives in their expansion, they got only contribution to 1. Those that they have 2 derivatives in their expansion, they receive also contribution 2, but we will not compute 2 here. And lambda, so the cosmological constant goes up to level 3. Level 4, as I showed on the slide, so on the slide here, level 4, nothing contributes to nothing, because this is already excluded by this bound. Delta becomes negative, you don't have variance. So this is the hierarchy of the contributions to the beta functions. Not everyone contributes to everything. We know that the most contributions we have to cosmological constant, but the higher number of derivatives, the less contributions we have to. And this is what we will concentrate here, level of loops 1, and the counter terms of the type C squared, R squared, and Gauss-Bonnet. We know that also this argument about the dimensionality, because the couplings that I wrote in the field, they come with a particular dimension. And here, if you want to see how is the contribution to C squared, R squared, and Gauss-Bonnet, the dimension must cancel. And the things which were on the slide here, they are, these are the leading ones, but they have different dimensions, that's why they cannot contribute. So this is already what we know from the dimensional arguments, because this is very simple thing. So the final thing, I will just show the diagrams when the output terms were neglected, but at the end I will restore them and I will show what to do if you have a list of them and what are the possibilities, how to find the full finite of this model when you have all the terms in a game. And the most important part will be to see the beta functions in front of C squared, R squared, and Gauss-Bonnet. So let's go. And again, for the computation, we have to say how is the most minimal model, so we will not have to worry about terms which were there just, let's say, for decoration, but they do not contribute anything to the divergences that we are interested. So the minimal working model, it will just have these 2 terms with 6 derivatives in their quadratic in a curvature. And still applies the Weinberg theorem. So we have that the expected form is only of this type of counter terms. 3 types. I neglect the box of R because perturbatively it's total derivative. Doesn't have to make except perturbative. So we have expected dependencies that these coefficients that appear in a divergent part of the one rotative action, they have to be dimensionless in 4 dimensions, but they can only be function of the calligraphic ratio, the fundamental ratio x that I find over here. And you can think which kind of function it is. It will be very complicated, maybe some analytics. You will see at the end, it's more simple than instead of here. That's what you will see. So there is this property that I was showing before, that you can have various independencies here. And this is basically mathematically proven by the parameterization independence theorem. It was proven by these 3 people. And the idea is if you take minimal model, you see the equations of motion are with 6 derivatives precisely. The minimal model is only 6 derivatives units, while what you have on this side is precisely with 4 derivatives. So how you can make equality between some differential operator with 6 derivatives equal another operator with 4 derivatives? The coefficient has to be 0. So it means we cannot have anything on the left-hand side of this equality, and this equality is basically the difference when you look at the divergent part of the effective action in one way of computing and the other. So it doesn't depend which way you choose. So these are the things that are independent of. And let me now go to the computation. So we use the method from Barwiński and Wilkowski. This is a bit technical, so I don't want to spoil you with a lot of formulas, with a lot of different different details. Just that we have to take the Hessian of the theory and compute its trace of log. This is what we do typically at 1. And this will be enough here, but we don't have only gravitons. Because of gauge symmetry, you also have to use Fourier-Popov gauss. That's a normal thing, but also because you have higher derivatives, you also have to use Fermi-gauss. So this is the full expressions that you have for the contribution to the effective fraction, and you have to compute these traces. As I said, I will not show you the explicit intermediate results. First, because they are boring, and second, they will not fit it here. You need the 1 megabyte text file, something similar to what we have seen yesterday in the GAN scope. So they are not presentable on a one slide like that, but I can present the final answer. This would be interesting. So and this is not using final diagrams. That was just my tip. So what are the results? Here we see them. So this is the divergent part of the effective action, and in this 6 derivative theorem, as I promised, there is something in front of C squared, in front of R squared, and in front of the Gauss bonnet. And you can compare the situation, the same object, just in stellar theory, we have something in front of C squared, R squared, and equal. In for stellar theory, I define corresponding fundamental ratio, and you see the function here is quadratic, and you can look for solutions, and then you can find some fixed point in this case for the R squared term. But here you see the function is only linear, and all the other things they are constant. So that's why I said this is simpler structure, because we don't have something quadratic, it's only linear in this fundamental ratio which defines, for example, the spectrum of your theorem. And moreover, you see there is a change because here this function is, this linear function is in front of the C squared, while in stellar theory it was just constant coefficient, and the basically C squared and R squared term, they swap the roles. So in stellar theory, we have this polynomial in front of R squared, while in the 6 derivative, this is a number. So this is something that shows us that maybe stellar theory was very special case, and actually there is a reason for that, because we can compare what's the expression for the divergences in Y theory, so the one which is C squared in 4 dimensions, and this basically is the way, is the agent why this thing has to be as it is, and why this thing is different from what we know with 6 derivatives. So these are the results, and let's go what we can do with them. So we can write the system of the beta functions, and because of the argument that I told you that there is no contribution to Hilbert, and moreover we know that the expressions are universal, we know that these 3 they are the final results for the beta functions in 6 derivative theory. The others I just wrote with 1 root, and then in principle they could have contributions. So first line running of the beta function of K Newton is from our paper with Ilya and Leonardo, and the other one is from the paper of Azore and also Ilya. Of course, at that time it was 30 years ago, so I couldn't be announced, unfortunately. But this is the result. Of course, these 2 lines they receive also contribution of Hilbert. As I said, this is plus something a 2 that I don't think anyone compute, and this is a 2 and 3 that also is probably a 9. But let's see what we can do. We can solve these equations because these are very simple equations for the running, and we can integrate, and these are the solutions. And in the case of the last 2 couplings, I said we are a bit agnostic about the value, but still we know what the dependency in terms of the logarithmic RG time. So this is the the t, but the values we don't know because they have contributions from not only one loop but two loop, and in the case of the lambda also three. So then we have the solution. Let's look at what is a special, and this means that we also look for some specific values that may be defined asymptotic freedom or asymptotic safety. So the case about asymptotic freedom is that we have to came with a very specific initial condition. Basically, the sign how we start must be the same as the sign of the beta function. So we can choose, for example, and this I will show on next slide. Just here you see that if there is a specific value that is 0 of this linear function, then basically coupling theta c stays at the non-trivial fixed point. So let's speak a bit more about this asymptotic freedom. So for example, in a C-squared sector, you can have when the value is smaller than the fundamental ratio, and you choose a condition that initial value is negative, then you find a condition that you don't meet the Randolph. Also, it means that your coupling with the fraction sign argument goes to 0, and this is asymptotic freedom. And the same happens if you flip the sign. So it's here that you have different conditions, then you can choose different initial condition. While if you stay at this particular value, what happens? Nothing happens because there's no arc flow, and you are sure that at 2 loop this will not be destabilized, because at 2 loop we don't have any contribution. So this is something partial, but now we can ask, okay, can we have all the 3 beta functions set to 0? So this is possible, but we know that if you just take this minimal model with C box C plus R box R, it doesn't work, because there was no reason why it has to work. But let's try now to add the terms which have cubic of curvature, and generally, okay, I will skip this part about conformal because maybe we have no time, but already Leonardo made a lot of motivations for that and a lot of explanation. So let's go back and try to say something about the terms which are cubic in curvature. So this is the list of them, and we know that in 6 dimensions, sorry, in 4 dimensions there are only 6 of them. And they are written here. I will also write them in a better way, but generally they come with 6 coefficients. So we add and we modify now our action that is not only R box R and C box C, we also add these terms which are cubic in curvature. They are not minimal, but as we will see, they will contribute to the beta functions of terms which are quadratic in curvature, but the contribution is quadratic. So you don't find, like in the previous case here, the contribution of this term that we can call killer is quadratic, because this is the what we know, for example, from Barninsky formally, like Roberto was showing yesterday. We could have the term, let's call it U squared, although maybe you use different letters and find out that also Russians use different letters, but there is something square. We don't go to cube. And the fact that this is square means that here we can have some expression which is generally quadratic, yeah, because we speak about 2 things, so they have 2 different indices. So generally you can have a quadratic dependence of this result for the trace, and this we will see in a beta functions. So we can try to see this kind of system, and actually it's a difficult algebraic problem, although we have only 6 couplings, but you add also particular value of x. You can choose without arbitrary parameters. So basically you play with 7 algebraic variables, and you have equations that they are quadratic, because that's what you see, and you want to solve for 3 beta functions that we want to solve to 0. So there are some numerical solutions that we found by the method of shooting. You can simplify something saying that, for example, omega is equal to omega c. The first 2 you can set to 0. The other one you try to be integer, not so bad, but then the others you have to get by solving some quadratic equations. So that's why, or maybe even cubic. So we have to use Cardano formulas, and these are the results. What you care about here, the solutions should be real, because we cannot allow for the coefficients in the action to be complex explicitly. And this gives a problem from the point of view of algebra, because, of course, if we have this kind of system of equations, we could always, thanks to the basic principle theorem of algebra, we could always find a solution. But here we want solution to be real. So let's go and let me present here this Killer Lagrange in a slightly better form, and now I use this trace-free object, and then we use the trace-free Ricci and completely trace-free. So the Leibniz. So these are the 6 terms that we can write, and when you use also the same basis for the divergent, we have three types of beta functions of R squared, F squared, and C squared. And luckily, we don't have dependencies on the whole 7 parameters when we find this diagram. Due to this fact that the trace-free things cannot produce a trace, we have only dependence with 4 terms, but these are different combinations. So we have this kind of system of algebraic equations. And how many minutes do I have? No. 1 minute. Yeah. So let me just show you that basically it's a geometrical problem, the intersection of 3 elliptical cylinders that they are going in 3 different directions in space. And then, as you know, even it was a problem of international mathematics Olympiad, how to find this kind of volume of the intersection is not so easy. But here we try, and one of the results we get is that there is only possible, there's excluded range for the value of the fundamental parameter of the field. For example, if you are in this range, which is actually defined by the solution of the equations which are up to the 8th order polynomials. So when you solve these equations, you see that between 21 and 1200, you cannot have a UV finite. So you have to find you have to use any value, but not in this range. So it's a very specific result that we have using algebraic geometry, but this is because we require solutions to be real. Otherwise, this would not be, we will not get 3 inequalities for the discriminants, and everything would be easier than mine. Instead, solutions real means that we have to work. So these are basically the conclusions. I told you about the one way how to get UV finiteness using quality killers, but also in 6 derivatives. I presented a way that it's a bit more complicated because now the dependence is quadratic, but still you can find some algebraic possibility for the range of couplings that makes the theory which is completely UV finite. There are also other parallel developments that you can do, and I think Leonardo and Gianluca they spoke more about this in the previous talk. So let me thank you for your attention. These were the papers that I also cited, and I can say sit there. Thank you.
Okay, is there any question or comments?
Only what does here is here, right? It's for not constant.
No, this we get if you take minimum theory just with 6 derivatives. Of course, Einstein, Hilbert, thermocosmological constant, they are no derivatives because from the dimensionalism you cannot construct the enough dimension for them. If you take all the couplings like omega C, y both sides, omega R both R, and then all the other terms which are cubic in curvature, you don't have the reason how, for example, dimensionalization construct the coefficient that is not of the cosmological constant that is the divergent factor. The same for the Einstein term. So when it will be in this whole sector, yes, it will be unified as in this whole sector. Of course, if you have some leading terms, like for example 4 derivatives, you generate, and this is where the partial formula that we derive, and you have to subsequently solve them. But this is the hierarchy that you have to solve. First, beta functions of the 4 derivative terms. You are done with that. You can go to 2 derivative terms if you are done with that, but for this, you not also 2 loops. If you are done with that, you can finally do the solution for the couplings in the cosmological constant if you want this beta function. But this would be the last.
Thank you for that question. So when you talk about asymptotic freedom, you mean that the running of the coefficient, of action goes to zero. But since you have lower order number of derivative terms in the actions, the theory is not asymptotically free. The theory is interacting theory. You still have axiom term and other terms. Even if these higher derivative terms goes to zero,
It ought to be meant, so it's a kind of abuse of language.
You can say this, but let me say, so first, on the one, I said, I don't want one, which was one. And then you can say maybe here we disagree with the definition of the asymptotic or not. But I said that we also use this definition which is in the paper of Leonardo, that you can scale, like exactly this in the paper from 82. And then this scale uses the kinetic term of the things which have the highest number of derivatives. So when you are right that, for example, some leading terms they are there, but if you scale with the terms of 6 derivatives, they will be separate because you divide by them. So they will be separate.
Okay, so let's say the speaker and all the speakers of the section. Okay, back 4 years.
哦，我们这个电脑它刚才这个下面好像死了，就死了，我可能重新弄回死。
Can we do a sound check? Can you see my screen?
How much you go still the only aspect is.
Hey Robert, can you hear me?
Yes,
Yes, I can hear you. Can you see my screen?
Yes.
Okay, so I will go full screen.
Now we are in the
Make
coffee
this
break.
full screen.
Yeah, so please wait another 10 minutes.
Yeah.
Sure, no problem. No problem.
But we are sorry.
So far?
Yeah, fine. See if he can hear you.
This
Hear
design.
something. It's off, it's off, it's off.
So,
Not
it would
the
say if
lower button.
it would be a bit.
Hello, Robert.
I would say.
Hello,
Very intelligent. It starts solving.
thanks for
Nice to
giving
see
me the chance to speak.
It's rather better start
Alexei.
with your and then you first try.
Yes, I recognize your voice.
Maybe it's video. No, we don't use this one. We have a camera over there.
So this theta is theta is constant. So then you can choose whatever theta I0 you want. And then with this constant value, which doesn't.
Why? You don't want to see him.
No,
wait.
and you look for this, but now you look.
Means, do you want to see him? The video?
Depending on this. So basically, it's at the end you are.
Does he want to open his camera?
The anything is zero, so all the data functions.
Robert, are you going to start your video so that your image is also in the corner of the screen?
Okay.
No, I mean not video, I mean this camera sign.
Yes, I have to open, so
Yes,
let me go.
that's it.
So also the parameter have to be sure where we
Yeah, but this is okay. I was
You see,
trying to
it's
say,
all dark
like,
outside because it's
I mean, I'm trying
4
to
o'clock
find
in the morning, my time.
very specific videos, and they are already theoretical.
I ask you to be silent for a second. I just want to see what it sounds. You are really loud.
I was there too.
I am
Robert, can
very
you say
loud.
something? Sian, please make your laptop loud.
Okay.
Make more sound. Increase volume.
Yeah, he will do it.
I'll do that, yeah. Yeah, of course.
Is the volume good now on my side?
No. Your side is okay. These guys should check out something.
Yeah.
Yeah, now it's the loudest.
We need more. It's very low. By the way, Robert, can you increase a little bit your microphone? Increase sensitivity of the microphone.
Okay. So I increased it. Is it better now?
Well, let's say better, yeah.
So it's almost maximum on my side.
Yeah, I understand. Are you sure it's maximum what you're doing? Yeah. No, I'm not asking you, Robert. I'm asking student here.
Yeah, this is the maximum.
You sure?
Yes.
Can you produce any other sound, by the way?
Okay, I will sound check again.
Maximum.
I think play around because this is the output for these speakers, so it can go at most this.
Wait, is it here? We can try?
Yeah, maybe you can rotate this.
Sorry, can you say something else, Robert?
Yes. So I'm sorry not to be able to be in Shanghai in person. Sound check.
But why do you need to? No, man, he was asking for something.
Was that better on your side?
Well,
It's almost same.
Actually, nothing is changing on this side.
I think there's a maximum we can do. So it's strange. You want?
Oh, no.
Right. Give it up.
You see? Can you make the same from here? Please, somehow. Or ask the guys how to do it. Because something is, it's very low sound.
Yeah.
Very low.
So I hear you loud and clear.
Well, the mic is.
Yeah, this is the mic.
No, if
Yes.
Yes.
So what does it mean?
Means
That he transmission loss now?
no, means that this is the maximum that the Zoom. I'll see how to do that.
I think I understand. And so, Robert, you're saying that from your side is the maximum volume of microphone?
Yes, let me just check again. Yes, on my side, it's the maximum.
I see. Okay.
I will just step out for a minute to get some coffee. I'll be right back.
Yeah, okay. See you in 5 minutes.
Yeah.
I think he should have. I think he should have made it louder.
No, io cioè, 2 anni sto capire che
Excuse me, Professor Robert. Can
Yes,
you say something to test the volume? Thanks.
okay. Sound check. Can you hear me?
Yeah, I can. Okay, now I'll call Alexei to see if the volume is correct. Okay.
Where's the mic? Where he can hear me? Okay. Robert, I'm Gianluca. We will start in a couple of minutes.
Okay, thanks. Nice to see you. It's been a long time.
Yeah, how are you doing?
It's 4 o'clock in the morning, my time.
Oh. Thank you for the effort.
So is this volume sound okay to you?
Yeah, yeah, yeah. So you have 40 minutes in total, okay?
Yes. So can you hear me loud
Yes,
and
yes.
clear now?
Yeah,
Good.
yes, perfect.
I'll put it somewhere so that I can be like this. Okay.
Okay, I think we can. Okay, I think we can start then. So it's a pleasure to have online Robert Vandenberger from McGill University. Today he will talk about emergent metric spacetime and early universe cosmology from a non-perturbative definition of superstring theory. Thank you, Robert.
Good. First of all, I'd like to thank the organizers for putting together this event and for inviting me to speak, even though I'm not able to be in Shanghai in person. So I'd like to apologize for not being able to travel this time. So I want to tell you about a research program that I'm very excited about, and it is related to the question of singularity resolution, which Slava Mukhanov addressed early this morning. But it's a very different approach to the question of singularity resolution. So quantum gravity is supposed to not only give you a quantum theory of the metric, but it's supposed to give you a quantum theory of space and time. And I will tell you an approach where space and time emerges from a well-defined quantum mechanical matrix model. So this is the outline of the talk. I will first give you a short motivation. As you will see, the metric space-time that emerges also gives rise to a cosmology which is of the form of an emergent cosmology. And I will give you an example of an emergent cosmology, a toy model, namely string gas cosmology. And then I will turn to the actual model of an emergent metric space-time from the BFSS matrix model, Banks, Fisher, Schenker, Susskind. It is a proposed non-perturbative definition of superstring theory. Okay, so as you all know, current early universe models are based on effective point particle quantum field theories, and there are singularities. And from my point of view, the singularities imply that there's a breakdown of effective field theory. So, question that I'll be addressing is, can quantum gravity resolve the cosmological singularity? And I will take the point of view that superstring theory is the best candidate for a unified quantum theory of all forces. But I have to also mention that I am not a string theorist. So I'm just using string theory. So I will then ask the question, can superstring theory resolve the cosmological singularity? And will a new early universe scenario emerge from superstring theory? So the key point, from my point of view, is that we require a non-perturbative approach. We cannot just do effective point-particle field theory with some ingredients which are motivated by string theory. We need a fully non-perturbative approach. This is obviously very difficult. Now, in the late 1990s, there was a proposal, the Banks-Fisher-Shenker-Susskind matrix model, and this was a proposed non-perturbative definition of superstring theory. And we've picked up on this proposal, and we have a construction of an emergent metric space-time based on this matrix model, and it also yields an emergent early universe cosmology. So what do I mean by an emergent early universe cosmology? And here is a toy model for an emergent early universe cosmology. It's a model which Kumon Vatfa and myself proposed long time ago in prehistoric times before the invention of the archive. So our idea was to just take a space-time and instead of having matter being a gas of point particles, just take matter to be a gas of fundamental strings. Now, compared to point particles, strings have new degrees of freedom and new symmetries. And the question we were asking is, do these new degrees of freedom and new symmetries lead to interesting conclusions for the early universe? So the new degrees of freedom that strings have compared to point particles are oscillatory modes and winding modes. So strings can oscillate, point particles do not have these modes. And if space is toroidal, then strings can wind the torus. Point particles cannot wind the torus, they can only whiz around the torus. Now, it is well known that because of the power of string oscillatory modes, there's a maximal temperature for a gas of closed strings in thermal equilibrium, the Hagedorn temperature. A gas of point particles does not have a maximal temperature. Now, the string winding modes lead to a new symmetry, and the symmetry is that physics at large size of a spatial torus is equivalent to physics at small size of a torus. This is a manifestation of the T-duality symmetry. So more specifically, here is this T-duality symmetry. So if you take space to be a torus with radius r, then the center of mass modes, the momentum modes, their energies are quantized in units of 1 over r. The winding mode energies are quantized in units of r. And so there's a duality if r is replaced by 1 over r in string units. And if you replace the integers, if you exchange the integers n and m, then you have a symmetry of the mass spectrum of string states. This is a symmetry of string vertex operators, and it is supposed to be a symmetry of string theory at the non-perturbative level. So what happens if you look at the consequences of the maximal temperature and of this T-duality for string thermodynamics? So if you take a gas of strings with radius r, and you look at the temperature, and you start with r very large, and you gradually shrink r, the temperature will initially rise, But when the temperature approaches the maximal temperature, then you can start to create the oscillatory modes. And once the temperature shrinks to below 1 in string units, the energy can flow into the winding modes and the temperature decreases. Okay, now this T of R curve, hopefully you can see my cursor. This point here looks like it might be a very long-lived metastable configuration. And so based on this thermodynamic curve, we postulated that the scale factor as a function of time would have this form. You start out at early times in this phase where the temperature is close to the maximal temperature. You live there for a long time, and eventually a phase transition takes place to the radiation phase of standard Big Bang cosmology. And this phase transition, at the time which I call T sub R, is given by string winding modes annihilating into string oscillatory modes. Now, this process of string winding modes annihilating into oscillatory modes only is allowed in 3 large spatial dimensions. Because in more than 3 large spatial dimensions, the string world sheets will never meet. This is provided that there are no long-range forces between these long strings. So there's the SO9 to SO6 plus SO3 symmetry breaking, spontaneous symmetry breaking, which gives you an explanation for why we have 3 large spatial dimensions, even though the underlying theory, superstring theory, has 9 spatial dimensions. And you will see this symmetry breaking, it will appear again in the matrix model. Okay, so this is the space-time diagram that emerges from string gas cosmology. The vertical axis is time. The horizontal axis is physical distance. The early times, T smaller than T sub R, that's the Hagedorn phase, gas of strings near the Hagedorn temperature. The phase transition at T sub R, the standard Big Bang phase of radiation domination. The blue curve is the Hubble radius, which is infinite in the quasi-static phase, and then it drops down to microscopic value and increases like in standard Big Bang cosmology. And the red curves indicate fixed co-moving scales. And as you see from this plot, fixed co-moving scales, scales that we observe today in cosmological experiments, like the ones which Li Heng described this morning, they emerge from inside of the Hubble radius at early times. And therefore, we have the possibility of having a structure formation scenario. Now, since the early phase is a hot gas of strings, the fluctuations that we have here are thermal fluctuations, not vacuum fluctuations. So the way that we compute observables from string gas cosmology is the following. It's a 3-step procedure, which I illustrate here. We first calculate the matter correlation functions, energy density and pressure correlation functions in the Hagedorn phase. And then mode by mode, we convert the matter fluctuations to metric fluctuations when the scale exits the Hubble radius. And then we evolve the metric fluctuations using the usual theory of cosmological perturbations to the present time. The key point, which will appear again in the matrix model, is that the matter correlation functions are given by partial derivatives of the finite temperature string gas partition function. So if you have the finite temperature partition function, we can compute observables in our early universe model. And these are the equations which we actually use. So here you see the metric, including cosmological perturbations, this red phi, and gravitational waves, the small hij, and the cosmological perturbations, scalar metric perturbations, are given by the energy density fluctuations, and the gravitational waves are given by the off-diagonal pressure perturbations. So in order to connect the early universe, the thermal Hagedorn phase, to observations today, we have to compute in the Hagedorn phase these correlation functions. So the energy density fluctuations in thermal equilibrium are given by the specific heat capacity, by this top equation. And in a gas of closed strings, the specific heat capacity has this holographic scaling with radius of the spatial box. And so if you mix these equations together, then you can compute the power spectrum of cosmological perturbations. And you see that at first sight, it appears to be completely scale independent. So, but if you look more closely, this T here is the temperature when the scale K exits the Hubble radius. And let me go back a couple of slides. So if you look at this diagram, you see that smaller length scales exit the Hubble radius slightly later when the temperature is slightly lower. We go back forwards to this equation. And so you see that you get an induced red tilt of the spectrum of cosmological perturbations. Now, if you compute the spectrum of gravitational waves, then this factor 1 minus T over T H appears in the numerator, not in the denominator. And hence, the power spectrum of gravitational waves is predicted to be scale invariant at 0th order, but having a slight blue tilt, unlike for inflation. So here, in terms of this toy model, I've indicated that we can connect a quantum gravity model of the early universe to cosmological observations, and we can make specific predictions. This is the bottom line. Now, the problem with string gas cosmology is that we put in the background by hand. I argued for the quasi-static Hagedorn phase by thermodynamics, but there were no equations. There were no dynamical equations. In my view, this is the Achilles heel of our old toy model. And this is where we are improving in our new approach. So let me now turn to our new approach, which is obtaining an emergent metric spacetime from a well-defined quantum mechanical matrix model. Okay, so we take this Banks-Fisher-Shenker-Susskind matrix model, which was proposed as a non-perturbative definition of superstring theory. And what we do is we consider this matrix model in a high temperature state. So in the matrix model, there's no space. If we consider the matrix model at high temperature, there's no more evolution. So we have a well-defined quantum mechanical model, but there's no space and no evolution. So our challenge is to start with this matrix model and to obtain an emergent time, an emergent space, an emergent metric, and an emergent early universe cosmology. Okay, so let me just emphasize one more point. So this Banks-Fisher-Shenker-Susskind matrix model is suggested to be a non-perturbative definition of M theory, provided that we take 9 spatial matrices and 1 temporal matrix. Okay, so here's the Lagrangian of this matrix model. So here I wrote, here in this slide, I considered small d spatial matrices xi, and there's something that looks like a covariant derivative. This capital D sub t is partial derivative with respect to time plus commutator with respect to a 10th matrix, a temporal matrix. Okay, now it is in the limit where the size of a matrix goes to infinity with g squared, the coupling constant, times n held fixed, it is in this limit that one is supposed to get super M theory. Now, if you start from string theory, then obviously we know that small d should be 9, because it's in 9 spatial dimensions that we have anomaly cancellation for string theory. But there's an interesting old paper which I stumbled on recently, which shows that from the point of view of matrix theory, there's something distinguished with small d being 9, because it is precisely for small d equals to 9 that, first of all, a supersymmetric extension of this bosonic matrix model is possible. L sub f, this is the fermionic term, and that this supersymmetric extension contains a normalizable zero energy state. So also from the matrix model point of view, there's something special about taking small d equals to 9. This is what we're going to do. Okay, so we consider a high temperature state, and then we can expand all the spatial matrices, all the matrices, in fact, we can expand them in Matsubar modes. So we expand them in our compactified Euclidean temporal direction. And when I say we choose a high temperature state, we choose a temperature so high that it is the zero Matsubar modes that dominate the action, as I indicated in the third point here. Now it turns out that the contribution of the small n equals 0 Matsubar modes gives exactly the action of the IKKT matrix model, which was proposed as a non-perturbative definition of type 2b string theory. So we rescale the Matsubar zero modes according to the bottom formula, and the action for these zero modes is this action, and here I write out explicitly the fermionic terms. So this is a pure matrix action, no space, no time. There's an action, there's a partition function. Okay. Now our task is to obtain an emergent time, an emergent space, an emergent metric, and an emergent universe cosmology from this ansatz. So the matrices are Hermitian, so we can always choose a basis in which one of them is diagonal. And we choose a basis in which A0, the temporal matrix, is diagonal. And the eigenvalues of A0, we interpret them as emergent time. This is standard in the matrix theory literature. Now, numerical studies indicate that the expectation value of the trace of A0 square scales as capital N square, and hence the maximal eigenvalue scales as square root of n, and hence the difference between eigenvalues scales as 1 over square root of n. And so in the limit when n goes to infinity, you obtain infinite continuous time. So this is time. Now we focus on the spatial matrices. So the spatial matrices have these following 3 properties, the last 3 lines. So if we first of all look at the off-diagonal elements of the spatial matrix A sub I and the expectation value of the square of it, then you find that these decay when you go sufficiently far away from the diagonal. And sufficiently far means bigger than a value small n sub c, where small n sub c scales as square root of capital N. Again, in the limit where capital N goes to infinity, n sub c goes to infinity. Now these 2 properties, so bullet point 3 and bullet point 4, you can see them using the Riemann-Lebesgue lemma from the partition function. Now, numerical studies also indicate that the diagonal elements so close to the diagonal are approximately constant. We don't yet have an analytical argument for this last line. Okay, so we continue to work in this basis, and we want to construct space. We want to construct space at a particular time t. And the prescription for doing this is as follows. So we work in a basis where the temporal matrix is diagonal, and we want to define space at a particular value of time, which I indicate with my cursor. So what we do is we take the spatial matrices, we go down the corresponding distance t, and we look at small n by small n blocks, which I call A tilde of n and t. These are these blocks which I indicate here. And then what we can do is, for these subblocks, we can compute the expectation value of the trace of these subblocks. And it's been observed numerically that in a thermal state, there's a symmetry break in phase transition. The SO9 symmetry of the matrix model is broken to SO6 cross SO3 in the sense that it is precisely 3 of these extent of space parameters which become large. The other 6 remain finite forever. This sounds very much like what happens in string gas cosmology, and I believe that it is the same mechanism that we explored in string gas cosmology, which is responsible for this symmetry breaking. It is the impossibility of string winding modes to annihilate in more than 3 large spatial dimensions. Okay, so now our prescription for space is the following. We will pick small n by small n subblocks of the spatial matrices, as I indicated before. The small n will be the spatial co-moving coordinate, and the extent of space parameter, which I described before, that's giving us the physical length. So this is our prescription for how the emergent space will emerge from this matrix model. So we have length, we have co-moving coordinates, so therefore we can also produce a metric. I should also mention that this construction works for small n, smaller than n sub c, and n sub c goes to infinity as capital N goes to infinity. So the range of co-moving coordinates which emerges is infinite, and you will see that this implies that the emergent space also has infinite size. Good. So the metric is obtained by the length in the standard way. And we can use the properties of the off-diagonal matrix elements, and the result is that the II components of the emergent metric are independent of n. They only depend on time. And if you now use the remaining SO3 symmetry, then you find that the spatial part of the emergent metric is spatially flat. So we have a prescription for emergent time, a prescription for emergent space. A metric emerges, and this metric is spatially flat. Lorentz invariance is built in the action for the BFSS matrix model because there's an eta mu nu symbol. Okay, so this is our model for emergent space-time from this quantum mechanical matrix theory. And what does this imply for cosmology? So if we consider the large three-dimensional space, then at late times, the evolution should be given by solutions of the classical matrix equations of motion. So these were studied, and you find that the equivalent of the scale factor grows as a power law of time. There is no sign of a cosmological constant, and there's no reason for a cosmological constant to appear because we are never quantizing a harmonic oscillator. Okay, now the SO9 to SO3 cross SO6 phase transition, it has been observed in the IKKT model, but we assume that it also holds in the BFSS matrix model. And we've been able to show using a Gaussian expansion approximation method that there is symmetry breaking in the supersymmetric BFSS matrix model, but we haven't yet been able to show that the preferred state is SO3 cross SO6 symmetric. But I have no doubt that this is the case. So now you see we have an emergent universe. We have a thermal state, and therefore we have thermal correlation functions of the matrices in this emergent space. And so we can therefore compute curvature fluctuations and gravitational waves in the same way as we did for string gas cosmology. So we start with the partition function of this matrix model. And in calculating the correlation functions, the 1 over temperature corrections in the BFSS action are crucial. So we can compute the energy density and the pressure correlation functions. For mode by mode, we can convert the matter fluctuations to metric fluctuations like we did in string gas cosmology. And we can evolve to the present time using the usual theory of cosmological perturbations. So the key point is that the matter correlation functions, which determine curvature perturbations and gravitational waves, are given by partial derivatives of the finite temperature partition function. And we have the finite temperature partition function, and hence we can compute these matter correlation functions. So to review the equations, we want to obtain the metric with cosmological fluctuations and gravitational waves. The cosmological fluctuations are given by the energy density fluctuations. The gravitational waves are given by the off-diagonal pressure perturbations. These correlation functions are given by partial derivatives of the finite temperature partition function, which we have. So these are a couple of equations. The specific heat capacity is obtained by partial derivative of the energy function. The energy function is given by partial derivative of the finite temperature partition function. So since we have the finite temperature partition function, we can compute the specific heat capacity and hence the power spectrum of cosmological fluctuations, and the same for gravitational waves. So you see, the setup is exactly the same as in string gas cosmology, and hence the result is the same. The thermal fluctuations in the emergent phase give us a scale invariant spectrum of curvature perturbations, and there's actually a Poisson contribution on ultraviolet scales, and we get a scale invariant spectrum of gravitational waves without a Poisson contribution on ultraviolet scales. So at this point, I've argued that the BFSS matrix model, which is a non-perturbative proposal for superstring theory, it yields an emergent time which runs from -infinity to +infinity. It yields an emergent space which has infinite extent in 3 dimensions. There's a metric which is spatially flat, and there's an emergent early universe phase with thermal fluctuations, which lead to scale invariant curvature perturbations and gravitational waves, and there is no cosmological constant. Okay, so this is an ambitious research program, and now obviously it could crash at any point. There could be fatal mistakes at some point, but my thesis advisor told me that if you want to do something new, you have to risk being wrong. And so I'm pursuing this research program. But there are lots of open problems. In our computation of correlation functions, we haven't included the effects of the fermionic sector. And that's going to be important to study the late time evolution of the matrix model, the late time evolution of the 3 large spatial dimensions. We need to understand the phase transition from the SO9 symmetric phase to the SO3 cross SO6 phase. Understanding the dynamics of this phase transition will allow us to compute spectral indices for cosmological fluctuations and gravitational waves. I think they will turn out like they were in string gas cosmology. Then we also need to understand how general relativity emerges in the infrared as a description of the dynamics of local point-like excitations like the sun and the moon. So obviously we first of all have to construct our point-like excitations. And at the end of the research program, we also have to address dark energy. And I think this is going to be a very interesting question. The dark energy that emerges is not going to be a cosmological constant, and it's not going to be quintessence. It's going to be something much more interesting. So there are some open problems. And let me just conclude, because I think I've used exactly half an hour. I want to leave time for questions. So the proposal which we are making, and by we, I should give credit to an excellent postdoc, Shudo Brahma, and an excellent PhD student, Samuel Laliberté, without whom this research would have been impossible. They were the driving force in this research program. So we've taken a proposed non-perturbative definition of superstring theory, the BFSS matrix model. We've considered this matrix model in a high temperature state, and we gave a prescription for how time, space, and metric emerges. We get an emergent early universe cosmology. We've computed thermal fluctuations in these emergent cosmology, and we've shown that this leads to scale invariant spectra of cosmological perturbations and gravitational waves. So thank you for listening, and I'll take questions.
Thank you, Robert. Questions? You have to use this microphone. Yeah.
So Robert, can you hear me?
Yes, I can hear you.
Okay, amazing for me. So I have questions. How to detect the gravitational waves predicted by the BFSS model? Can you talk about that?
Yes. Right. So let me go back to how it is done for string gas cosmology. I think I went too far. So the bottom equation on this slide is the key equation. So gravitational waves are determined by the two-point function of the off-diagonal pressure perturbations. So you know that black holes, rotating black holes, give rise to gravitational waves. It's quadratic in the matter perturbations. So this is the way that we calculate gravitational waves. And you see it's parallel to the way that we compute density cosmological perturbations in this thermal state. So the cosmological perturbations are given by the expectation value of the energy density perturbations. The gravitational waves are given by the off-diagonal pressure perturbations. And so if the energy density and the pressure are comparable in amplitude, then you will actually find that the amplitude of gravitational waves that you get is fairly large. So in this setup, you will predict a fairly large amplitude of gravitational waves. Now in string gas cosmology, we have a prediction we have a consistency relation between the tilt of the gravitational waves and the tilt of the scalar modes. And the consistency relation is n sub t, your n sub t, is 1 minus n sub s. And roughly speaking, the amplitude of gravitational waves, the tensor to scalar ratio R is about 1 minus ns square. This emerges in string gas cosmology, and we are going to use the same equations in matrix cosmology.
Let me also add that Satsuko Yanagi and I computed the gravitational wave background of this string gas cosmology model, and actually you saw it in the previous my talk, and we determine an upper bound, and it can hit the Sago observability window, but cannot get higher.
Okay, thanks.
Actually, I also have a comment about that. If so, this model of string gas cosmology is in a regime below the Hagedorn temperature. There was another proposal by Anupam Mazumdar and collaborators of taking the Attic-Witten conjecture and consider a model above the Hagedorn temperature. In that case, we found that the gravitational wave spectrum has excessive amplitude and violates the BBM bound. So, do you think there is it can be explained by relation between the temperature at which the system is and the amplitude of the spectrum at the high frequencies?
Okay, so in this model, so in the BFSS matrix model, we are in the same situation that we considered in string gas cosmology. We are not in the Attic-Witten setup. So we will definitely get R, the tensor to scalar ratio, smaller than 1.
Okay. Any more questions? Okay, if not, let's thank Robert again. And next speaker is the live here. Yeah. Yeah. So the next speaker is Zhang Li, talking about primordial black holes seeded during inflation.
Okay, so first I'd like to thank the organizer for giving me such a good chance to present our recent activities. So recently, for recent 1 to 2 years, we are intensively working on one topics which is related to the kernel black holes. And today I want to summarize some of them, and I make part of kernel black holes from formed seeded during the inflation. Okay, so these are based on the series of our works. Okay, so before I go into the details, I want to explain why we talk about these kernel black holes and what are they. So we already know that these black holes already exist in our natures. So black holes are already a very solid notation for conceptions. Well, there are mainly 2 aspects of
so-called permanent house, meaning that if we divide them by the mass of permanent house, we have two series of black holes. One is this permanent house, which have relatively smaller masses. But these permanent holes, they are one of the very interesting physical properties that they may dominate over the dark matters and without introducing any new physics. So for small permanent holes, they can be a very good candidate for dark matters. And the other thing, so I mean, for those permanent holes which are massive, I mean, more than one solar masses, this kind of masses, well, they are also very interesting because one of the main interesting, characteristics, features that they are the candidates to predict to detect the gravitational wave events. And these are first proposed in these papers. Also, there are many, interesting physics corresponding to this permanent house. For example, they give us a very interesting, possibilities to detect the final power spectrum of close relatives on small scales. And also exactly there are many interesting topics on this trend. So that's the reason why the permanent house attracts much of the interest in our society. Okay, so everyone knows that now, according to this gravitational wave detections, now we have this level of Virgo, this O3 detections, and we have all this kind of series of detect events. And most of them are these mergers of binary black holes, and both of them merge and create a large black holes. And as you see, all these kind of blue dots characterize these kind of binary black hole mergers. And if you trace back all this kind of binary black hole merger event data, you will find that a very interesting behavior is that now we have 91 is for binary black hole merger events. And if you filter all these kind of things, you will find that most of the kind of around 76 out of these 91 events, they have a very interesting and or unexpected features is that firstly, the masses are always very large, saying that they are larger than 1.5, or they may even, if you see these pictures, most of them are even more than 10 solar masses, and this is an unexpected features before these detections. And even more interesting or more unexpected thing that if we calculate or trace back their data, we will find that the effective spin for these kind of events are very small. So most of them have this effective spin smaller than 0.3. So this really gives us a very surprising feature. This is because if we trace back, we all know that according to the current astronomical notions, we have this kind of approach which comes from the death of stars. But we know that most of the, for instance, the stars we have a huge speeds. So if we assume that the cracks of all these kind of stars, obey the so-called conservations of angular momentum, then basically if we go to this measure deep black hole, then they should all have very high speeds. So such small speeds may give us a hint that these kind of black holes may not originate from the cracks of the stars. So, I mean, there are two very surprising features. One is that most of them are massive, and another feature is that the speeds are very small. So how to explain such kind of features is the current issues. Of course, so in this astrophysics side, they may explain, they already propose something like probably 3 stars or so to explain this kind of thing, but still not complete explanation of that. And if we trace back, or if we go back to this kind of formation of the house, we know that except for this kind of astrophysical black holes, if we trace back to 1960s, even in 1967, the Lewis and Monaco, they have already proposed another kind of black hole, which is called permanent black holes. They do not need such kind of the basis of star crabs. What they need is only the crabs which comes from their huge curl distributions. And those black holes are called primal black holes. So why it's called primal black hole is because that they can form during the very early stage of universes. So let's give a cartoon here. So this is cartoon here, and this is the timeline is around here. So this is from the Big Bang, and it's the 0 times of the times the directions. And we know that all these things currently we know that it is around 13 billion years of the universes. But we know that our universe is divided into several very ancient, very important stages. But these kind of particles can be born even within the 3 minutes after the born of universes. So if you compare the time, you will find that we know that after say 380 some years, the first atoms were born. And maybe much after that, we have born of the first stars. And then the first stars may burn all of their fuels. And then after they burn all of their fuels, the first star will die. And the formation of this, the first actual physical black hole, may be from that time. So this is around 41 billion years. So compared with the September holes, they are really, really young, and the September holes are really very, very old, and they are within they can be born within the primordial stage of the universe. So this is called the primordial black holes.
How is the measure?
Sorry?
How do we measure the speed of black holes?
Oh, this is by the level of all the data. I'm not in this data.
Can't they do statically the speed of black holes?
No, I think maybe let's say that you have this different this curves, which gives you this kind of, you have input this kind of input this kind of parameters. One is the mass and one is the spin, and also we have other parameters. Different this kind of parameter conditions gives you different the curve of this kind of a gravitational wave data. And when you check with them, then you will get their spins. So this is the way to get their spins. They do not measure directly, but this is the parameter for this kind of waveform.
You fit it with this parameters.
Yeah, we fit, of course. These are the parameters. We can have thousands of the kind of different waveforms. And when you put when you see when this kind of waveform of gravitational wave, then you compare with all this kind of waveform, and you will find this. We will find one image which gives you this kind of a parameter on space. So this is from the knowledge of the numerical relativities. Okay, so this here actually what we call kind of parallels because they are born really in the very early universes, and this is much earlier when before this the formations of structure of universes. So this is why we are called primordial parallels. Okay, so as I said, we have two very interesting aspects of the primordial parallels. One is that for those massive primordial parallels, they are the candidates for these and local events. And first papers were done by these collaborators on 2016, where they draw such kind of pictures. So the horizontal with straight line is the extraction of PBH over all of the closed down layers. And this this line is the merge rate, which can be inferred from the light and Virgo data. And these strategy readings are the predictions from the light and Virgo data. As you can see, so depending on the parameters of the trajectories, all these kind of events, PBH events, can be used to predict within the range of the predict merge rates of the light and Virgo data. And they also predict that the FPBH, the fraction of PBH over dark matter is around 10⁻³ to 10⁻⁴. So for those large parallels, they are one of the possible also candidates for this kind of parallel mergers. So this is one effect. Okay, there's another effect, as I said, that for these small parallels, currently, so this is the current, say, a constraints on parameter holes. And this line is a fraction of parameter holes of that measures again, and this line corresponds to the measures of parameter holes. As you can see, so for those events, for those large PBH, this kind of events, they cannot dominate over the dark matters, but they are still, say, they can still exist. But the interesting thing is that for those small parameter holes, I mean, in this kind of interest range, there is almost no constraint on this in this kind of, say, range. The reason is very simple, is that if you calculate the corresponding source rate radius of such small parameter holes, you will find that their, say, the radius, the structural radius is much smaller than the counter wavelengths of the light. This means that there's no such kind of diffraction, they say, effect coming from these kind of events. So if you only use the light to do such kind of separation lenses, then almost there is no such kind of constraints over here. So this gives us a possible theoretical, say, a aspect that's possibly, so at least at the current stage, there is a window for small parameter holes to bound for all of the dark matters, because almost here is totally thin, and you can reach the fraction 1 to the equivalent dark matters. So this gives us another interesting aspect is for small parameter holes, they may be the candidate for dark matters. So this is another trend. Okay, so I talked about the motivation to consider on these parameter holes, and now let me try to discuss how to form such kind of parameter holes. So one way to form this kind of parameter hole is that they may collapse and they may collapse due to very huge amplitude of the primordial curvature relations. So let me give such kind of plot of this space-time diagram to account how to produce such kind of things. So this is the diagram of the evolutions of the universes. So this solid lines is the evolutions of the whole horizon for our universe, for our, say, a evolution of universe into current. So we know that if we accept the theory of inflations, we know that there's a long period of around 60 equal numbers of inflations where the whole horizon is almost a constant. After that, we may enter some kind of, say, a radiation dominance, and after radiation dominance, we enter the matter dominance until the current universes. So this is the current diagram of the space-time. Of course, we know that on the very large scales, I mean, on scales which is effectively larger than 1%, we know that there is a so-called CMB constraint from, well, the most recent coming from 2018, which gives a very, say, very strict, say, constraint on the amplitude, saying that it cannot exceed the value of 10⁻⁹. But the point is that when you go to the sufficiently small scales, I mean, to scales which are effectively smaller than 1%, then there's a theoretical possibility that the amplitude of the curvature ratios may be enhanced very dramatically. And if this enhancement can reach around 10 to the 6 or 10 to 6 or 10 to 7 applications over the, say, CMB scales, then, for example, when it reaches such kind of high peak at a star, then at the top of a star, if X horizons, then it is frozen until some period, let's say around some period when it's random the horizon during the radiation phases, because such kind of, say, amplitude is so huge. This means that this gravitational forces or self force is very huge. When it's enters horizons, the whole, say, Hubble patches will quickly collapse. And in this kind of, say, scenarios, these kind of, say, Hubble patch will quickly collapse and form the parameter holes. And this is one of the most natural way to form such kind of, say, a parameter holes. And the essence for producing such kind of parameter holes is a huge, say, enhancement on the power spectrum of small scales. Okay, so correct with this kind of values. So if we think about the simple single field equations, then everyone knows that the power they say the primary power spectrum is proportional to the inverse of the slope parameters. Then when we quickly think that in order to produce such huge applications of amplitude of perturbations, we really need a very flat cases. So saying that we need to fine-tune the potentials to have a very flat regions where we call inflection points. And in order to have this kind of plot, we really need the fine-tuning on the parameters. So this is so-called fine-tuning problem in order to have a PVH formations in the single field equations. Of course, there's other ways, many other ways. For example, we may say modify the field, the gravitational series to go beyond the gravitational relativities. But for the ordinary cases, such kind of product always appears. We consider those single field equations. So our idea is that if we go beyond this kind of single equation, for example, if we go to the multi-field cases, then it's a kind of a fine-tuning problem may be somehow relieved. So that's what we work with GP and Qingbo Huang and Suzuki in 2017 is that we propose a model. So the point is that we want to both preserve the good prediction from the inflations, and we want to modify the small case. How to do this? One simplest work case is that we still adopt the so-called statistical model, because statistical model gives us a very good fit on the large scales. But on small scales, there is some kind of large scale field which may dominate the next several 10 or 20 foldings in the equations. Then we propose such kind of models with the CSA R-square models and with a nominal couplings with a light field type here. So if we using this kind of simple FR series, and if we transform this into the Einstein, then such models become a biscalar and tensor series. So everything looks like this. So if we draw the effective potentials here, then you will see that the potential is like this kind of plane, where firstly you have, so around that line, firstly you have a very like the statistical model, where this R field is light, the chi field is heavy. Then it goes along this kind of R or scaling this kind of directions. Everything is goes well with the statistical models. But in the middle way, because this kind of the methods of scaling and methods of light field changes their methods, then this scalings goes into its vector trajectories. And then, because you have a non-zero velocity here, you have a huge, oscillations around here. And then it goes around with I directions. So this is the whole, pictures of the inflations. And the inflation field or inflation stage is divided into two stages. The first stage is totally solid stage, and the second stage is a chi-dimension scale, or chi-dimension stage. Between these two stages, there is a transition, and these transitions really gives a huge bump. If you translate this into the corresponding power spectrum, you will find that it's both the power spectrum look like this way. So when you have on the large scales, then it looks like the statistical model, everything is fine. But if you go to the small scales, you really have a huge bump. And this bump gives you a very large, amplifications on the power spectrum. And it is the first oscillations. So if you go back to see, we have the first oscillations. And the first oscillation gives you the largest, amplitude of the oscillations. And then you have a huge peak in the corresponding power spectrum. Then,
the background level drives the inflation. Both fields drive inflation. So the background level.
Yeah, background
which field triggers inflation? Both of them.
So this is the background. So first, this is a scalar field dominations. Everything is like Travis model, and it goes to the local minimums of this kind of say scalar field. And then you have that field, that direction, it is that high direction. So you have the transitions from a scalar field dominations to the chi dominations. And because when it goes down, you have the non-zero velocity here, then you have zero, say, damping here. And the first position is at the highest amplitude. And then if we translate into the cross section, it looks like this. And then because the fraction.
How much seed?
Sorry?
How much seed coming from topic? So in the case of integration with the.
Oh, you mean that type here, that type. Yeah, that value is around 106. Or smaller than 106. Yeah. So this is different. Yeah, this is different from the Higgs equation. Totally objects.
So it is the sign minus and C positive.
Yeah, sign is positive. Yeah. So that's you have this kind of say something like a we can say tension like this kind of area, then it will go down. Okay, so because this fractions of PBH is proportional to exponential of 1 over exponential of -1 over power fraction. So a huge this kind of say enhancement in the P really gives you a like this kind of delta like or looks like a delta like this kind of say shape of the mass function. Then by tuning these parameters, well, it's not fine tuning, but still need to some tuning of parameters. We can really have this kind of values which dominates all of the dark matters. So this is one mechanism which comes from say a double field inflation. Okay, but if you everything seems fine, but if you look more carefully, you will have two questions. The first thing is that since here we expand the potential only to the second order, then this literally means that in this kind of say a models, these diffusions have no exit. So this is one problem. Another fact is that if we see these kind of pictures carefully, you will find that this kind of thing, the increase of this concept is so sharp. The reason why it is so sharp is because we totally use the analytic form of two states and make a very rough such kind of symmetries, saying that by using the C1, analytic this kind of a measuring from it. So this gives us a very sharp increasement on the cross section. And in this paper, we don't know where it comes from, and we cannot understand such kind of things by using the totally analytic ways. So in order to have a more realistic ones, so this last year, my students and Jingpen and I and Sasaki also improved this kind of models to answer these questions. So the first question is very simple to answer. This is because we didn't expand into higher order. Then if we expand the chi field to the fourth orders, then this will give us a very a local minimum around here. Then we can very easily to stop the inflations. So this is one thing we can realize very quickly. But another thing is that if we look at this model very carefully, we will find that we have a problem of the main wall. So that's the reason why we also introduce a shift on the chi field. So I'll explain this very quickly. But the cause of such kind of more realistic model is that the inflations will be broken into two stages, where for inflation 1 and inflation 2. Between these two inflation stages, there was a break stage, we say around 1 or 2 defaulting numbers, but the inflation is broken in this kind of scenarios. So this is what we call a double inflation scenario. Okay, that explains why we need this kind of chi-zero shift field. So let's see. So we have this potentials which is projected into the chi field and this phi directions. As you see, so for the first period, it really looks like a Stabis model, right? Everything looks fine. We see a Stabis model, Stabis like potential, everything fine. And on this kind of the chi field, everything looks like, it just oscillates around this local minimum. But the problem is that if we set the minimum to here, then effectively, so when it goes to the third stage, then this kind of inflator will be set on the top of the local maximum. Then it can go both left or to the right hand side, and the fluctuations which are calculated from here is very huge, seeing that there will be a possibility that it goes here a bit and goes back again. Then it will produce a lot of probability paths, saying that domain walls will be produced around these kind of scenarios. So that's the reason why we make a shift chi0 here. A shift chi0 here will shift this kind of chi to be not on the top of this kind of local maximum. Then it will gradually, say initially, goes down and it will not go back. So in this kind of trend, we can avoid such kind of domain wall programming. And using such kind of models, everything is very similar. We have stage 1, where it's chi dominations, and we have the stage 2, where we have this kind of staging, and we have stage 3, that is totally given by this kind of chi field. And we make by using this data formalism, then we can find that these kind of more real-based power spectrum is characterized by these factors. For example, here the power spectrum is divided into 3 stages. The first stage is something still like disturbance model, and the second stage you don't have a very sharp one, but you have a k to the alpha state such kind of state increasement, and alpha is constrained to be not larger than 3. And after you go to the top, then the peaks go down, and you have also a slope to go down. So such a power spectrum is divided into these 3 forms, and in details for different choice of parameters, as you can see, the highest speed for the increasement of the power spectrum is no quicker than k to the cube. So these are kind of power spectrum, and for different parameter choices, let's say these different lines, you can have this kind of fractions, and it may either dominate of the dark matters, or it can be this kind of question wavelengths. So these are the complete versions of the previous model. Also, we know that because of the huge enhancements of the closure machines, then it will induce the so-called induced background waves. And by using these formulas, we may plot these energy densities of these induced background waves. And as you can see here, we took the data from the recent a nanograph data, and it fits the data quite well, especially in the low bound. Okay, these are the complete versions of our models. Okay, so now we are considering even one step beyond. So as you can see, so these are the broken this kind of inflationary stage. And then the primary house we talk here is here. So when it's XY amplifies, and XY amplifies, that's the last stage of mutations. We produce a lot of parallel holes. But there's also another possibility is that these parallel holes can be formed even in the first inflationary stage, saying that in the first break of between these 2 stages, a very light parallel holes can be formed. And such kind of light parallel holes will evaporate because of the Hawking radiations. And such kind of small parallel holes, it is interesting because if you consider about the energy densities, then you'll find a very interesting correspondence is that, for example, these black solid lines shows the energy density of inflator, and the red line shows the energy densities of these parallel holes. At first, it may be lower than the total energy of the energy density of the universes, but after a period, because the parallel holes they decay not so fast compared with the inflation, then there will be a period there where the parallel holes may exit and they may go beyond the amplitude of energy density of inflation or the whole universes. Then there will appear a corresponding say area where the total radiation economic areas may come from the evaporations of chemical flow into the radiations. So I mean, there is a possibility that all of or most of this radiation economic areas, most of the LRC energy comes from the evaporations of these light chemical flows. And this gives us an interesting explanation of where this radiation comes from. And this is another interesting issue in which we are still involved. Okay, so talking about all these kind of scenarios, what we know is that all these kind of, we are talking about chemical flows, which comes from around 1 to the 7th applications of this, say, power spectrum on small scales. But we want to ask whether such kind of, say, a application will exist or not. And maybe I have to say it quickly. So our idea, another idea is that if we provided that we have these kind of panels, which come from large observations on series, and if you combine this with the so-called light of the verbal data, which gives you the merging of panels, so whether this kind of scenarios is consistent or not, saying that we really want to use the light of the verbal data to reconstruct the primordial curve observations to see whether its amplitude can reach such kind of 7th applications of power spectrum or not. Provided by this, we may make some assumptions. One assumption is that we assume that at least some of this kind of modulate comes from this kind of primordial black holes, and also make some kind of simple assumptions. After these assumptions, so we took use of this expressions of the merge rates. Then we found an interesting behavior is that no matter what kind of what kind of derivations of all these kind of data we have, we really found that the power spectrum by using the library of verbal data, it really gives us a hint on around 10 to 7th applications of the power spectrum on small scales. Small scale, I mean, on small scales around 1%. So around these small scales, this kind of light of verbal data may imply that there's a kind of 10 to 7th applications on the power spectrum. And this gives us an interesting, at least it gives us a consistency check on whether this kind of field is right or not. And at least currently, as far as we know, currently such kind of light and verbal data somehow support the current and the theoretical models. So this is the current situations. Okay, last I want to quickly ask one questions. So we know that because of these huge applications of cultural inspirations, essentially we will induce this kind of induced working waves. And now we think that it may be, around, we may be used to counter for this kind of a PTA, this kind of nanograph, this kind of observations. But there are still some other explanations on it. Induced working waves is not the only explanation of it. So we ask another question is that if there's no induced gravitational waves observed at once, can we really rule out the primordial health scenarios or not? So our answer is no, because there's another very interesting interesting scenarios on formation of primordial holes. So let me explain this within several minutes. So we know that there's a so-called such kind of ternary processes, saying that if we have such kind of two local minimum such kind of models, then essentially during inflations, there's a very interesting scenario that our universe is at first located in this force vector may turn to this kind of true vector. And this kind of turning processes in very early universes will produce the so-called bubbles. So saying that inside these bubbles, it is still the true vector is after turning, and outside of these bubbles, it is force vector. If we calculate the pressures, we know that the pressures often goes from the true vector to the force vector. Then we will have the expansion of the bubbles. So when you have many bubbles, which is determined by the turning rate, and turning rate is given by the difference of height of the two, say, local minimums. And after some period, those bubbles may collide with each other, and inside this is still the force vector. And at last, you have such kind of theory where the areas are two vector, and inside is the force vector. And because the force vector, so it is always from two vector to the force vector, then such kind of force vector area will collide and form a parallel holes. So this so-called the bubble formations, such scenarios of the formation of parallel holes. But the problem is that if you assume that all this kind of say shape of potential is fixed, saying that the difference between two vectors are fixed, then your turning rate is fixed. Then, according to this kind of paper by Leighton in 2017, if you see that this parallel come from such kind of scenario, then you will have a very flat such kind of say the corresponding mass functions of parabols. Then such kind of parabols can never explain such kind of say a dark matter because it will either touch the left bound or the right bound. So there's no way to have the primordial dark matters from these scenarios. So there's no way to explain this kind of PDH dark matters. Okay, so we think that there's another way to do this. So the first thing is that we may have such kind of extension of the universe during the creation, everything is fine, but it may be that in some stage of the universes where the force vector and the two vectors, when they compete with each other, let's say, for example, when the two vector goes up and last. So during some observations, the whole picture becomes this way. The two vector become the force vector, and force vector becomes the two vector, saying that inside becomes higher than outside. Then this kind of the pressure will turn its directions so that these bubbles will stop expanding and begin to collapse. And when they quickly collapse, then it will quickly form the parallel holes. Now this is our idea. But the question is that how to realize such kind of scenario. Okay, so together with my students, the Funnel Wall and also with cell hierarchy, so we propose such kind of models where we have the filter, which is going to the field, and we have another field, which is the tunnel field, which is expansion fourth order. And we have a non-coupling between the inflaton and the instantons. So provided by this, because the inflaton is always going down, then because of this nominal couples, you may have such kind of scenario where firstly you have such kind of potentials, but because it is going down for the kite field, then the local minimum one side will go down, and it will reach the deepest say cases, which gives you the highest say turning rates. And after some stage, when inflation is still going up, to make goes up again, and gradually after the inflation, to make this part may go a little bit higher than this force vector. Then the two vector and force vector say change their rules. So by using this kind of scenarios, we know that say the turning rate is really say dominated by this kind of say stage. And if we plot such kind of say a PBH, then you will find that it's not like a flat one, but it really gives you a huge peak. This is because that the turning rate is proportional to the exponential of minus s, and it really gives you an exponential constant on some kind of regions. So this all really gives you a huge peak, and it may use to dominate over the whole domains. And this is a very interesting scenario. Okay, so let me summarize what we are doing. So currently we are mainly focusing on the topics of parallel holes, and these things may give us a very interesting and rich fix, saying that, for example, these blue line and these green lines, self-speaking, so there are many ways to form such kind of parallel holes, and probing such kind of formation mechanism is already a very interesting scenarios. And another way is that for this kind of blue lines, where the parallel holes may be used to explain so many current positions, especially for this kind of Gaussian wave data. So currently, these chemicals are very interesting, and we look forward for the further observation data to either verify or falsify such kind of scenarios. Okay, thank you very much.
Questions? You assume that the PDAs are formed after BDN, right? In order to satisfy the bounds from BDN.
Oh, okay, okay, yeah, of course. Yeah, we have this kind of yeah, you have many this kind of constraints. Or maybe here is some kind of a constraints here. And this constraints our this kind of PDH mass functions.
And concerning the lightest,
Light is already here. Yeah,
and what's the formula operation time for them?
Oh, these are really too long, and these PDH cannot evaluate. So these, I think these kind of PDH, if the mass is around 10 to the 10th gram, up to now everything is evaporated. So this is everything is calculated from the Hawking radiations, and you can very simply say estates their evaporations. And for my scenario here, so these, okay, for these PDHs here, so these PDHs are smaller than 10 to the 8th grams, and they will evaporate very, very quickly, even quicker when it's even quicker than it's the radiation dominance, the beginning of the radiation dominance area.
We have another question here.
From the call, for the first trivial model, I find the y and exit inversion because the character have quadratic potential, just like delta inflation.
Yeah, so this is because we have two different projections of this kind of such kind of two directions of this inflation now. Maybe here it is very more simple. So this is three-dimensional plot, and this direction is the Slavic this direction, and that direction is K direction. And you can see, so for the first stage, everything is very good. Every looks the summit model. But this line is around the local minimum of the scalars. Although it goes around the local minimum, but you have other trajectories. So that's the reason why you have two stages of inflations. And the transitions between these two stages gives you such kind of enhancement. You can see this stage 1 and this can stage 2.
Your first
Oh, the first one. This one.
Yeah, this we think is the projection density of in hand minus sign.
Oh, this one, yeah. Well, it's this one. This one, because here we have this form. This is because we really want this time to put the phantom, such kind of behaviors. If no phantom, then everything stops around here. If we need phantom, then it goes around that direction. Yeah, so this is this kind of phantom effect.
Questions?
I can just speak out loud. Thank you for the very nice talk. Just one quick question. You mentioned fine tuning. I think the first model you mentioned.
Yeah.
If you back to the other scenarios, how?
Oh, of course, yeah. So even if in this kind of the single field equation, you may have other scenarios. For example, if you consider this K essence, then it is not only proportional to 1 over epsilon, but also 1 over CS squared. By tuning that CS squared, you can also realize such kind of P. Yeah. So that's the reason why I said that in the simple or in traditional in this kind of single field theory, it is not good, but you can have some other theory. But in that theory, you still need to tune the parameters and tune how this kind of K file looks like.
Exactly.
Yeah.
So the question I was wondering is that in your later model that wants to two fields, how much you need to fine tune your boundaries in order to get
you here. Then you really need to tune the epsilon to like say 10 to the -7 compared with the CMB one.
Yeah.
Yeah, so this is a very say huge say tuning and to give you such a very flat pattern. Yeah.
Yes.
Okay, let's thank the speaker again. Okay, so the last speaker today is Yang Yuhan, talking about the quantum cosmology and modified gravity after the days of 2024. And after the talk, please don't run away because there is an important announcement.
So thanks for introduction and thanks for organization. I came from the University of Science and Technology in China. And today I will give a brief talk about our recent work in cosmology and modified gravity after Daisy 2024. And before my talk, I want to thank for my collaborators for their valuable discussion and hard working. They are especially Professor Tsai and Professor Dodaki. So my talk is basically about the dynamic of the dark energy and give a gravitational information about the Daisy 2024. And first of all, I will give a brief introduction about dark energy in the modified gravity theory. The story of the dark energy begins from the late 20th century. Scientists, through the observation of the Taiwan supernova, which can be used as a standard candles to measure the distance since they produce a cohesive luminosity, and through the Taiwan supernova, scientists find that these stars are accelerating away from us at an increasing pace, which means that our universe is accelerating expansion. And this observation is further evidenced by other observations, such as CMB, large-scale structure, and baryon sorting oscillation, and so on. And finally, those scientists who first find the acceleration when the Nobel Prize at 2011. And with such a shocking phenomenological observation result, people may ask, what can trigger the real-time cosmic acceleration? According to the modern cosmology, anything that cannot be explained by the conventional paradigm, it must be belong to the dark. For example, we need to explain the flatness of the galaxy rotation curve. We introduce the conception of the dark matter. Here, similarly, introduce the concept of dark energy. And through the observation, we find most of the universe is made of by the dark universe and dark energy and dark matter. And only 5% of our universe is made by the baryonic matter, which we have for meter waves, and we can see in our daily life. So to start with such a huge trend, dark energy is very important for our understanding of the universe. However, through the observation of the Hubble parameter, the Hubble constant, two different groups use two different measurements, and they have a big experiment on the Hubble constant. This one shows the values from the CMB measurements, and this one shows the value of the Hubble constant from the local distance laser by the Taiwan supernova. And this experiment has become larger and larger as our
It got heated up, the project is got heated up. So it's just starting in that. Starting. This one is starting. Just keep it will go.
The disagreement between large and large as the relation between one more factory and very efficient in factory. And together with the segmentation, we can even make it here. Let's also establish our standard understanding model, which means that this model will be very standard. And for the backend, we need the dynamic dynamic model to implement such a vision. So to calculate the dynamics of backend, we may introduce a very useful parameter we call the equation state parameter. This is defined by the ratio of the pressure to the energy density. And if we take a local expansion of the equation state with respect to the scale factor, we will get the CDR parameterization. And if we take to the near, we will get this simple parameterization like W naught plus W1 minus 4 minus 8. And we can, for the W close and W1, we can plot parameter space for these two parameters. And we can divide it into 6 different parts. For example, if we consider the energy is dominated by the cosmological constant, this is a short here. And if we consider the energy is continuous model, which means that the equation state will larger than -1, but smaller than -1/3. This will respond to the part 2 and part 3. And if we consider the energy expansion, which means that it will relative to the non-energy condition, and the equation state will be smaller than -1. This responds to the ranging part 5 and part 6. And for theoretical cases model, the equation state will be larger than -1 or smaller than -1. And the important things we are curious about is the continuous model, which means that the equation state of that energy will cross -1. And this can be divided into 2 different types. For example, if we consider the energy is cross -1 from the bottom to the top as the universe is expanding, which is from the atom to the continuous range, and we call it P2B. On contrast, if the equation state from cross -1 from the top to the below bottom as the universe is expanding, called P2A. And so the reconstruction of the energy, some scientists find, such as Professor Zhao, find that such a equation state may have a dynamical characteristic, which means that the cosmological constant may not be able to adjust the dynamics. And together, people may ask what can explain such a dynamical dynamic. And together with the rotation and the schema illustration, we turn to the modified gravity theory. It can give a very simple explanation to these equations. So when we modify gravity theory, there are many perspectives, such as quantum gravity. It generally predicts the modification to general relativity. And for the strategies of the P curve, scientists due to play into the modified utility dynamics among the theory. And the earlier universe, first and so far most successful equation model is based on the R2L model, which is also proposed by LBC. And at the cosmological scale, such as Hubble tension and sigma tension and the dynamic of dark energy I mentioned before, it can also be explained by the modified gravity theory. So I will give a brief introduction about the physics on 24 data and the cosmological reconstruction. So the data is very observation data, and it contains different samples for different redshift. But from this figure, we can see there is an overlap for the LRG and ELG. So during the analysis, we use a combined LRG and ELG for the technical operations and to lower the uncertainty during from the observation data. And for the redshift larger than 2.1 or 1.77, we consider the line alpha hoist as a sample to manage the barrier sorted data. If you want to look more detailed simulation, so need of time. And the method we use here is the Gaussian process. This is a stochastic procedure to acquire a Gaussian distribution of functions from the data. Since the data we get are some the point with advanced and different redshift, and they can be seen independently So in order to reconstruct the function, we need to construct. We need to consider some finite dimensional distribution for all x such as this. So the building process is to assume that this finite dimensional distribution are Gaussian. So then we will more detailed consider two figures, and if you want to see more, I will show you later. And we then, together with the field data we mentioned before, from this method, we can use to construct the dynamics of background evolution of the universe. This is the main result of the reconstruction of the upper parameter. And for the Bailey only result, it can be shown referenced by the original. You can show here. The value of the Bailey only result constant is very larger than any other observation constraint. So this means that the Bailey only result is not only enough to be well reconstructed. And we can see there are many information loose on this redshift piece, which means that we need to add more BL data from other surveys such as CSS and QGC. By adding some previous BL data, we call it PBLO, and the combination we can finally get the construction result, which is shown by the vector P. And we can see the blue shadow range represents the one sigma already for the reconstruction result. And the solid line here shows the best fit non-CDM model. It can fit the reconstruction result very well as a low redshift, but at high redshift, it can be well distinguished at high redshift. And also mentioned that here, the data point, which is right here, at the redshift around 0.5, this is larger than any other observation around the same redshift. This is also confirmed by others' results. So that may be something wrong with the data itself, or any other things we don't know. So then we can use the parameter we construct to reconstruct the equation 0 parameter. We mentioned here the process, the method we use for tracking process. It is a model independent way. It means that we do not need to parameterize the evolution of the equation state as a parallel, such as the W0 WA parameterization or to the tail expansion. So we only need to, from the Friedman equation, it's very simple. You can see, and together we finally reconstruct result. And for the basic only, we can see it can close 0, which means that the equation of the energy density of the back energy will become negative when this crossing happens. And for the only result, for the basic combination result, we can show that they will exhibit a quantum behavior from crossing -1, which is the beginning of the universe, from this to this is now, from the phantom range to the predicted range. This will show the quantum behavior. And we mentioned the numerical result is the main result we want to get here, shown by the black curve and the shadow range. And to fix such a result, numerical result, we will take some parameterization to get the result. Traditionally, we can take the PPR of the linear parameterization I mentioned before, with the WA parameterization of the energy, which shows in the green line. We can see that it still falls in the one sigma range as the reconstruction result, but we cannot fix the factor, the mean value of the reconstruction result very well, which means that this simple parameterization may not be very sufficient. We need to go beyond the linear parameterization. So we take this parameterization as an example to figure the result. We can see things very well. So how is our different from others? This is the result released by the basic corporations. They use the WA parameterization, and they also show the quantum behavior of dynamic in the quantum space. And this is a figure of evolution of the equation state for by them. And also some other guys use the check expansion of the equation state and for the evolution like this. You can see that they all show the same quantum behavior of dynamic. So the difference that here we use a model independent way to capture the dynamic characteristics of dynamic. So with such a phenomenological behavior of dynamic quantum B, one may ask how can we realize such a quantum B behavior of dynamic from the theory? So let's go to the theoretical implications about the quantum B. Before we go to the theory result, there is a famous theory about the quantum cosmology called the normal theory. Besides, for a single perfect fluid or single scalar, it cannot, equation state of kind of dynamic cannot cross over the cosmological constant boundary, which will finally divided. You can see here for the single perfect fluid, the equation state plus -1, and here you will become 0, and this term will become divergent. And also for single scalar, when the crossing happens, partial rho, partial x will become 0, which means that this term also will also become divergent. So this means that the convection, when we go through the -1, it will be unstable. So for single perfect fluid or single scalar, we cannot cross over the cosmological constant boundary. So in order to realize such a dynamics of quantum energy, we need to break at least one condition present in the local theory of dark energy. There are many theories about this, such as cosmological modified gravity, or interacting dark energy, or Young's model, complexity. But since we are focused on the modified gravity theory I mentioned before, so we'll go to the modified gravity. There are many modified gravity theories. If we add some variance to the general relativity related to the high order gravity theories, if we add some detail into the tensors vector set theory, and we can assume that space-time is not really like related to the measure of high gravity, let's say that Q and T gravity, if we combine the gravity unit to the quantum gravity, which is possible about quantum. But I'm not familiar with this part, so I will take a measure of high gravity as an example to take a gravity integration. So the measure of high gravity is based on the space-time geometry of the system. There are three different space-time for departure, propulsion, or electricity. And this can be three real-time geometry into the general measure of high space-time. If we consider the space-time is homogeneous and measure compatible, this will lead to a Riemann space-time, not a general relativity. If we consider the space-time is continuous, homogeneous, and measure compatible, this will lead to the microwave space-time. Similarly, for the anti-gravity, we consider the space-time is continuous and measure compatible, and for Q, the space-time is continuous and homogeneous. We mentioned for the Q gravity with constant gauge, which means that all the connection is zero, like in anti-gravity. So the background evolution of this Q theory are the same. So we take that theory as a sim theory. We mentioned just as the background level. So the general action for the measure of angle, we can actually please recognize this one. And so relate and you can find result of the Hubble parameter we get before. So we can use this one to reconstruct the action here. The result is shown by these figures. We also mentioned the only assumption we make here is just the space-time is rather depends on the curvature or torsion or electricity. We do not need to assume what the function form of the action is like or what the general function is in general. So the numerical result is shown by the black curve and the shadow region, and the red line represents the cosmological constant. You can see that the reconstructing result indicates that those actions should be beyond the standard Euclidean model. And since a value of the R, T of Q, you will gradually become smaller and smaller as the universe is expanding, which means that in the later universe, you can always do a polynomial expansion of the action, just like this. However, we mentioned this is just an effective description of the general action. Whether the general action is exponential or power or logarithmic, we do not. It's still worth considerations. And we can, from the best figure shown by the orange solid line, we can figure very well. And for all cases, we'll find the dark integration from the Euclidean favorably. So here we just show a simple example that can explain such a quantum behavior of dark energy. And there are also many theories on mechanical mechanics explain such a quantum behavior. So before the end of my talk, I want to give a second question about such a quantum. This is the prime space given almost 20 years ago. And this is the primary space given by the basic correlations just one month ago, or 2 months ago, sorry, 2 months ago. We can say it just falls into the small range of this part, and the confidence of P2B behavior became much larger. In the future, where the confidence of the P2B became larger and larger, or as I mentioned before, there will be something wrong with the data itself, so the result may be wrong. We want to know. So maybe in the near future, there will be better intention, or we call it P2B can be in the near future. So that's our look. We don't know. So let's go to the summary and look. So the summary is our understanding of the dynamic of the company acceleration remains unclear. And in the future, the highly pathetic data are expected to explore the issue of the time potential acceleration, and also more theoretical mechanism for problems to be passed. And derivation lies on the dynamic nature, and more such data are coming. So that's all on the talk. Thanks.
Thank you very much. Questions?
Yeah, just a quick question. Very good. So the basic data, there is a strange point, and actually this is the point that makes the difference. And some people say that probably there's something wrong there, and if you stood at that point there, then lambda CDN is again within 1 sigma.
Yeah.
So what do you think? I mean, this is a real data point there, and we should start looking this really seriously, or it could be something systematic and
actually such a group will based on simple data, so this is due to the online study for the method we use. Things are as I mentioned, you construction method, but very well, I'm not familiar with this. Sorry. Here is the comparative FDS and right line shows FDS and the blue line shows the map of the gradient exactly, and the green form is by the data on the effect that is totally involved.
More questions? Okay, then let's thank the speaker again, and all the speakers have
There is an announcement about the results of Boston Top selection. First of all, thank you very much for bringing so many nice poster thoughts, and the selection committee had a very hard time to select the best poster, and now I delegate the microphone to Professor Shapashnikov to announce the winner.
Good evening. So as Arnold said, we really had very hard time to make a decision. So we thought we will make the decision during the coffee break. We didn't manage, so we continued, and we even missed the talk after the coffee break. Okay, so first of all, we were very impressed by the quality of the posters, the presentation of the posters, and the science which was reported there. So we would like to congratulate all the authors for their work. Okay, maybe we give everybody 2 minutes, but then we realized this will be too difficult to organize, so we have to make a decision. And what we decided is that it would be nice to complement the topics of this conference by a talk on interaction between several types of cosmic strings by Kohei Sachikura, Savaoli and Master Yanovich. Okay, so we are looking forward with. Thank you.
Thank you very much. Okay, we are moving to the next one.
Take care of this thing and we'll fix the matter. Yeah, turn over.